in October 2020.
I greet you all from Ankara on behalf of the organizing committee. After the earthquake, we decided to organize a face-to-face meeting in Izmir with our Greek and Italian friends. We wish we could have hosted you in Izmir. However, unfortunately, the pandemic conditions didn't allow us to do so. I hope the next time we will all meet in person in Izmir. To this online workshop, we have invited 35 speakers from Turkey, Greece, Italy, Japan, Germany, the United States of America, and Switzerland. Before we commence, I would like to extend my sincere thanks to our invited speakers for their invaluable contributions. I would also like to express special thanks to Spiros Pavlidis and Ricardo Caputo for their great efforts in organizing this workshop. We are grateful to the President of the Scientific and Technological Research Council of Turkey, Professor Hasan Mandal, the President of Disaster and Emergency Management, Mr. Hamza Taşdelen, the Chancellors of partner universities from Turkey, Professors Nükhet Hotar and Alim Yıldız, the Director of the Turkish Academic Network and Information Center, Mr. Mehmet Mirat Satoğlu, for their valuable contributions. I especially thank my friends in the organizing committee here in Turkey, Professor Hasan Sözbilir, Drs. Cihan Aksop, Fikret Koçbulut, Mustafa Softa, chairs of the sessions, technical staff Murat Köreke, and many others, who showed a great effort to organize this workshop. This meeting couldn't have been held without their contributions. As a result of this workshop, we are also planning to publish a special issue of the Turkish Journal of Earth Sciences. So we look forward to receiving your contributions to this special issue. I hope this workshop will bring the neighboring countries of the Aegean Sea closer and develop scientific and academic cooperation among all countries working on this subject. Once again, I greet you all with respect. Okay, now we can move on the opening speeches. Before that, let me inform you that some of the opening speeches will be in Turkish. If you want to listen to them simultaneously in English, please click on the interpreter section at the bottom of the screen and choose the English option. Professor Eftimios Lekas, the President of Earthquake Planning and Protection Organization of Greece, is unfortunately on duty now, and instead of him, Professor Spiros Pavlidis will speak. He is the President of the Geological Society of Greece. Now I am giving the floor to Professor Pavlidis. The floor is yours, Pavlidis.
Dear colleagues, good morning, günaydın, buongiorno, kalimera. On behalf of my colleague, Professor Eftimios Lekas, President of the Earthquake Planning and Protection Organization of Greece, who is unfortunately on duty for civil protection projects now, and me as President of the Geological Society of Greece, we welcome this important scientific online meeting on the important topic of earthquakes that we often experience in our regions. Thanks to organizers, especially to Orhan Tatar, my friend Orhan Tatar, and to TÜBİTAK, we wish good success and continuation in the future. Thank you.
Thank you very much, Spiros, for your nice opening speech. Okay, now I am giving our virtual stage to Professor Roberto Paolucci from Italy. He is the coordinator of Italian Seismic Risk Sector of Major Risk Commission at Civil Protection Department. The floor is yours, Professor Paolucci.
Professor Paolucci,
are you there? Ricardo, do you hear us? Professor Pavlic is on now. Can you hear us? Professor Roberto Pavlic, floor is yours, please.
Şu anda hazır hocam.
Okay, Roberto, floor is yours, please. Ricardo, you hear us?
Yes, now I hear you. I know he had, good morning, everybody. I know he had some problem with the connection. Okay, just called me. He just called me. I hope he could join quickly.
We see him connected here in.
He is connected.
Yeah, okay.
He is connected, but he had some problem to speak, probably.
Okay, if you wish, we can just move on to the next talk, if you wish.
Roberto, ti faccio parlare al microfono io, dai. Ti faccio parlare, ok?
Okay, so can you hear me?
Hello?
Okay, Roberto, we are hearing you.
Okay, so good morning. Sorry for this problem. I don't find a way of say joining directly the microphone and video for this connection. So okay, I'm Roberto Paolucci. I'm teaching earthquake engineering at the Politecnico di Milano. And okay, I'm, as you said, I'm heading the technical risk group of the Commissione Grande Rischi, that is the scientific and technical consulting committee for the vision for the Italian Civil Protection Department, and together with Riccardo Caputo. So actually the Aegean sea earthquake of the past October is actually very relevant for civil protection. I would say that it is actually so relevant because it's out of ordinary consequences. I would say that you have to predict what are the consequences of a magnitude 7 earthquake based on standard approaches, based on standard empirical ground motion models or standard geodesic curves. You would have hardly predicted that the largest impact would have to be in the near area, so some 20 kilometers away from the epicenter. So why such out of ordinary features are these related to source to site directivity, to site amplification effects in the Izmir basin? These factors that may have played a role are typically not directly accounted for example, in the seismic norms, in the issue of seismic action design. So, understanding better those physical features may be of critical relevance for civil protection and more in general to improve risk mitigation strategies. So this is all. Wish you really all a nice and productive workshop, and greetings from Italy. And sorry for this for problem of connection. Thank you very much.
Okay, thank you very much, Professor Pavlic, for your speech. And now we can move on to another speaker. Now I am inviting Professor Hakan Yekbaş for his speech, who is the Vice Chancellor of my university, Sivas Cumhuriyet University. Floor is yours, Professor Yekbaş.
Teşekkür ederim hocam. Değerli katılımcılar, sizleri Sivas'tan saygıyla, sevgiyle selamlıyorum. Malumunuz 30 Ekim 2020 tarihinde İzmir'de meydana gelen ve can ve mal kaybına sebep olan depremden sonra üniversitemizde başta olmak üzere TÜBİTAK öncülüğünde Bu toplantı düzenlendi. Sizleri bu vesileyle ağırlamaktan ve aramızda görmekten dolayı çok mutluyuz. Teşekkür ediyoruz. Malum ülkemiz ve Ege bölgesi de tabii bunun içinde aktif bir konumda, deprem konusunda. Bu konuda yapılacak çalışmalar önem arz etmekte. Bu vesileyle başta TÜBİTAK ve AFAD gibi kurumlarımız başta olmak üzere birçok kuruluş önemli destekler vermekte. Üniversitemizde özellikle jeoloji, jeofizik, maden, jeofizik gibi yer bilimleri alanlarında ülkemizdeki ender üniversitelerden biri. Ve bu bölümleri de üniversite olarak elimizden geldiği kadarıyla araştırma fonları vasıtasıyla destek vermeye çalışıyoruz. Deprem başta olmak üzere afet zararlarının azaltılmasına yönelik önemli konuşmaların yapılacağı bu çalıştayın hayırlara vesile olmasını diliyorum. Emeği geçen hocalarımıza, başta Orhan Tatar hocam olmak üzere, katkıda bulunan 9 Eylül Üniversitemize, AFAD'a ve TÜBİTAK'a teşekkürlerimizi arz ediyoruz. Rektör hocamın da selamlarını iletiyorum. Kendisi il dışında olduğundan dolayı bu önemli programa katılamadılar. Ama inşallah yakın zamanda yapılacak bu tip çalışmalar olduğu zaman desteğimiz ve katılımımız her zaman olacak. Tekrar teşekkür ediyorum, saygılar sunuyorum.
Teşekkür ederiz. Thank you, Professor Yekbaş, for your speech. Now we pass the floor to Professor Nükhet Otar, the Chancellor of 9 Eylül University. She would have loved to have this workshop to be held in Izmir, but it wasn't possible due to pandemic conditions. I hope we will hold this meeting next year under the umbrella of 9 Eylül University, hopefully all together. So I leave the floor to Professor Nükhet Otar now.
TÜBİTAK Başkanı Sayın Profesör Doktor Hasan Mandal, değerli bilim insanları, kıymetli katılımcılar. TÜBİTAK öncülüğünde düzenlenen Uluslararası Deprem Çalıştayı'na hoş geldiniz. Güzel İzmir'imizin kültür miraslarından birisi olan rektörlük binamızdan sizlere seslenmekten mutluluk duyuyorum. Geçtiğimiz yıl Ekim ayında büyük bir felakete neden olan Samos depreminin ardından Ege bölgesinin depremselliği üzerine gerçekleştirilen bilimsel etkinliğin hem kentimiz hem de komşularımız adına son derece önemli olduğunu biliyoruz. Yine bu etkinliğin Ege Denizi'nde kıyısı bulunan ülkeler için yeni işbirliği alanlarının kurulmasında, ortak çalışmaların yürütülmesinde ve özgün fikirlerin geliştirilmesinde referans teşkil edeceğine inanıyoruz. Değerli katılımcılar, yer bilimleri alanında başarılı akademik çalışmalara imza atan ve yetkin bilim insanları ile deprem ve afetler konusunda kamuoyunu aydınlatan üniversitemiz, 30 Ekim'deki depremde de benzer bir anlayışla hareket etmiştir. Bu kapsamda kurumumuz bünyesinde faaliyet gösteren Deprem Araştırma ve Uygulama Merkezimiz, Samos deprem raporunu hazırlamış ve bunu TÜBİTAK Başkanımızın da bulunduğu toplantıda bilim dünyamız ile paylaşmıştır. Yine bölgedeki fayları izlemeye ve tepkilerini ölçmeye yönelik önemli bir adım atan merkezimiz, İzmir için deprem erken uyarı sistemi projesinde hayata geçirmiştir. Kamusal sorumluluklarımızın yerine getirilmesinde rektörlüğümüze destek olan, söz konusu raporun ve projenin geliştirilmesine öncülük eden Merkez Müdürümüz Profesör Doktor Hasan Sözbilir'e ve emeği geçen tüm hocalarımıza teşekkür ediyoruz. Elbette aradan geçen sürede rektörlük olarak deprem ve afetlerle ilgili girişimlerde bulunduk. Çalışmalar yürüttük ve önerilerimizi de dile getirdik. Bunlardan bir tanesi Deprem Bilim Kurulu'nun oluşturulması fikriydi. Yine bu felaketin toplumsal hayatımıza etkisini dikkate alarak AFAD ile Afet Eğitim Seferberliğini başlattık. Bu çalışmamızda farkındalık oluşturmayı ve vatandaşlarımızı bilgilendirmeyi hedefledik. Kısa süre önce de merkezimiz öncülüğünde bütünleşik İzmir deprem master planının hazırlanmasına yönelik bir projeye de başladık. Bu çalışmamızı kamusal kurumların, yerel yönetimlerin, meslek odalarının ve sivil toplum kuruluşlarının desteğiyle kısa sürede tamamlamayı planlıyoruz. Rektörlük olarak yer bilimleri alanındaki araştırmaları, deprem gerçeği ve afet yönetimi konusundaki çalışmaları desteklemeyi sürdüreceğiz. Bunu yaparken de bütünleşik bir yaklaşımda olmaya, farklı bilim dallarını bir araya getirmeye özen göstereceğiz. İzmir özelinde güvenli bir kentsel dönüşümün sağlanması, afete duyarlı mekansal planlamaların yapılması, risklerin ve zararların azaltılması noktasında da inisiyatif almaya ve ilgili kurumları bilgilendirmeye devam edeceğiz. Bu düşüncelerle çalıştayın düzenlenmesinde emeği geçen, başta TÜBİTAK Başkanımız Profesör Doktor Hasan Mandal hocamız olmak üzere ilgili kişi ve kurumlara teşekkür ediyorum. Büyük acı yaşamamıza neden olan depremde hayatını kaybeden vatandaşlarımıza da bir kez daha Allah'tan rahmet diliyorum. Sağlıklı günlerde buluşmak dileğiyle hepinizi saygıyla selamlıyorum.
Orhan, your microphone.
Thank you very much, Professor Hotar, for your speech. Now I am pleased to invite Mr. Hamza Taşdelen,
The President of Ministry of Interior Disaster and Emergency Management Presidency. The floor is yours, Mr. Taşdelen.
Çok teşekkürler hocam. Sayın TÜBİTAK Başkanı, üniversitelerimizin değerli rektörleri, ülkemiz dışından bu çalıştaya katkı koyan değerli akademisyenler, sevgili katılımcılar. Öncelikle bu önemli çalıştaya nazik davetiniz ve afet konusunda göstermiş olduğunuz ilgi için başta şahsım ve kurumum adına teşekkür ediyor ve sevgi ve saygılarımı sunuyorum. Bilindiği gibi ülkemiz bir afet ülkesi. Özellikle de komşularımızla ortak sınırımız olan Ege Denizi tam anlamıyla depremlere neden olan aktif tektoniğin ve sismik etkinliğin en fazla görüldüğü bir bölge. Aktif tektoniğin bu kadar etkin olduğu bir denizde geçmişten günümüze kadar meydana gelmiş depremler ne yazık ki çok sayıda can ve mal kaybına neden olmuş, hatta eski zamanlarda uygarlıkların yok olmasına bile yol açmıştır. En son örneğini geçen yıl 30 Ekim tarihinde Samos adasında yaşadığımız depremin yarattığı hasar ve can kaybının 70 kilometre uzakta ülkemizde İzmir'de yarattığı afet, doğa kaynaklı olayların sınır tanımazlığına bir örnek olduğu gibi aynı zamanda komşularımızla ortak hareket etmemiz gerektiğinin en önemli kanıtıdır aslında. Türkiye'de afet kayıplarının sebepleri ve aksayan yönler oldukça çeşitlidir. Bunlara kısaca değinecek olursak maalesef ülkemiz afet politikaları 1999 depremine kadar afet sonrası iyileştirme ve yara sarma üzerine yoğunlaşmıştır. 1999 depremi sonrası detay jeolojik ve jeoteknik etütleri içeren afete duyarlı imar planlarının hazırlanması zorunlu hale getirilmiş, doğal afet sigortası sistemi kurulmuş, afetler konusunda farkındalığın oluşturulması amacıyla ülke çapında kampanya başlatılmış, yapı denetim sistemi zorunlu hale getirilmiş, bina deprem yönetmeliği ve tehlike haritaları yenilenmiştir. Bunlardan da önemlisi ülkemizde afet ve acil durumlardan sorumlu koordinatör bir kurum olan AFAD Başkanlığımız kurulmuştur. Vatandaşlarımızın afetlere karşı güvenliğinin sağlanmasında kamu otoriteleri birinci derecede sorumludur. Fakat hepimizin de takdir edeceği üzere afetlere dirençli yerleşim yerleri ve afetlere hazır ve farkında bir toplum oluşturmak tek bir aktörün başarabileceği bir eylem değildir. Bu nedenle toplumumuz bu tehlikeleri algılamak ve bunların zararlarını azaltmak, hatta ortadan kaldırmak konusunda yollar bulmak zorundadır. Deprem ve afet gerçeği artık tereddütsüz önemsenen ve ortak eylem dahilinde çalışmalar yapılması gereken en önemli konulardan birisidir. TÜBİTAK Başkanlığımızla birlikte kamu kurumlarının teknik kapasitelerini ve ülkemizin akademik gücünü de kullanarak Ege ve Marmara Denizi'nde yapacağımız deprem üreten paylarla ilgili ortak deniz araştırmaları bunun en güzel örneğini gösterecektir. AFAD Başkanlığı faaliyete başladığı 17 Aralık 2009 tarihinden beri ülkemizde afet ve acil durum yönetim konularında ülkemizin ortak gücünü harekete geçiren, koordine eden ve uygulayıcı bir kurum olarak önemli çalışmalara imza atmıştır. Atmaya da devam etmektedir. Bugün ülkemiz deprem riskinin azaltılması konusunda ülke geneline yerleştirilen 1111 deprem gözlem istasyonu ile ülkemiz ve yakın çevresinin deprem aktivitesinin hızlı ve güvenilir bir şekilde izlenmesi ve değerlendirilmesini sağlamakta. Deprem konusunda üretilen tüm bilgi ve veriler, kamu kurumu sorumluluğu ile gerek sosyal medya, gerek internet, gerekse de AFAD'ın üniversite ve özel sektör işbirliği ile geliştirdiği web uygulamaları çeşitli platformlardan ülkemiz ve dünya genelindeki ilgililer ile paylaşılmaktadır. Ülkemizde deprem tehlikesini ortaya koymak üzere hazırlanmış, modern bilimsel yaklaşımlarla üretilmiş bir haritamız da mevcuttur. Ve Türkiye Deprem Tehlike Haritası web üzerinden tarafların kullanımına açıktır. Deprem risklerinin azaltılması konusunda en önemli araçlardan biri olan bina deprem yönetmelikleri konusunda ülkemiz dünya çapında örnek gösterilen bir yönetmeliği hazırlamış ve kurulan bir komisyon marifetiyle de bu yönetmelik sürekli güncel tutulmaktadır. Hızlı tren sistemlerinde deprem erken uyarı sistemleri, doğalgaz dağıtımında deprem acil müdahale sistemleri, yapı sağlığı izleme sistemleri ve depreme dirençli akıllı kentler uygulamaları da önem arz eden diğer projelerimizdir. Deprem konusundaki araştırmaların deprem risklerini azaltmada en önemli faaliyetler arasında olduğu bilinciyle 2012 yılında başlatılan Ulusal Deprem Araştırma Programı ile günümüze kadar başta deprem konuları olmak üzere diğer afet türlerini de değerlendirerek toplamda 57 projeye yaklaşık 11 milyon lira bütçe desteği sağlanmıştır. AFAD'ın kurulması ile hazırlık çalışmaları ivedilikle başlatılan Ulusal Deprem Stratejisi ve Eylem Planı'ndaki eylemlerin büyük bir kısmında çalışmalar başlamış, %70'i tamamlanmıştır. Değerli katılımcılar, bilindiği üzere 30 Ekim 2020 tarihinde yerel saatle 14.51'de Sisam Adası'nın hemen kuzeyinde Seferihisar ilçesinin kıyı kesimlerine yaklaşık 24 kilometre uzaklıkta bizim ölçümlerimize göre 6.6 büyüklüğünde derinliği 14.9 kilometre olan bir deprem meydana gelmiştir. Deprem özellikle zemin etkisi ve binalardaki yapısal problemlerden dolayı İzmir kent merkezinde Bayraklı mevkiinde can ve mal kaybına sebep olmuştur. Deprem sonucunda 117 vatandaşımız hayatını kaybetmiş, 1032 vatandaşımız yaralanmış ve tedavileri yapılmıştır. Ben teknik olarak fazla konuşmak istemiyorum. Bu çalıştayın konusu olan depremin teknik özellikleri buradaki değerli katılımcıların, akademisyenlerin söyledikleriyle zenginleşecektir elbette. Sayın TÜBİTAK Başkanım, sayın rektörlerim, değerli katılımcılar. Sözlerime son verirken bu organizasyonun gerçekleşmesinde emeği geçen herkese, özellikle 2 gün sürecek bu çalıştayda katkıları destek verecek değerli katılımcılara şimdiden teşekkür ediyorum. Özellikle koordinasyonda yer alan Sayın Orhan Tatar Hocama ve Hasan Sözlüyor Hocama da ayrıca teşekkürlerimi sunuyorum. Sevgi ve saygılarımla katkı verecek herkesi selamlıyorum.
Çok teşekkürler Sayın Başkanım. Thank you very much Mr. Taşdelen. Professor Hasan Mandal, the President of the Scientific and Technological Research Council of Turkey, TÜBİTAK, has just arrived from a travel, and we thank him for joining us at the opening session of the workshop. Professor Hasan Mandal accompanied and supported us in the field after the earthquake. We thank him for his valuable supports in earthquake studies and contributions to the organization of this workshop.
Now I leave the floor to Professor Hasan Mandal.
Evet, teşekkür ediyorum kıymetli Orhan Hocam, üniversitelerimizin saygıdeğer rektörleri, kıymetli AFAD Başkanım, değerli bilim insanlarımız, araştırmacılarımız ve bu çalıştayın değerli katılımcıları ve özellikle de öğrencilerimiz ve gençlerimiz. Bugün ülkemiz ve aynı zamanda ülkemizin paylaştığı ortak coğrafya için stratejik önem taşıyan deprem araştırmalar alanında düzenlenen ve 2 gün boyunca sürecek olan Uluslararası Aktif Tektonik ve Seismicity çalıştayı kapsamında bir araya gelmiş bulunuyoruz. Ege bölgesi odağında ve üzerinde sadece 6 ay geçmiş bulunan 30 Ekim 2020 depremi özelinde aktif tektonik ve Seismicity araştırma sonuçlarının paylaşılması için çalıştayda 100'den fazla bilim insanımızın, araştırmacımızın katkı sağladığı 30 farklı bilimsel çalışma sunuluyor olacak. bu uluslararası çalıştayın gerçekleştirilmesi için işbirliği sağlayan üniversitelere teşekkür ediyorum. Bu kapsamda 9 Eylül Üniversitemiz, Sivas Cumhuriyet Üniversitemiz, Aristoteles Üniversitesi ve Ferrara Üniversitesi'ne sağladıkları işbirliği için ayrıca teşekkür ediyorum. Deprem araştırmaları, deprem öncesi ve deprem sonrasında farklı süreçler kapsadığı gibi bir takım araştırma alanının katkısını gerektiriyor. TÜBİTAK'ın izlemekte olduğu stratejik yaklaşım olan birlikte geliştirme ve birlikte başarma yaklaşımının deprem alanında da gerçekleştirilmesine yönelik öncelik gösteriyoruz. Küresel salgın döneminde COVID-19 Türkiye platformunda elde etmekte olan başarılarımızı deprem araştırmalar alanında da yaygınlaştırılması için ekosistemimizi seferber etmeye devam ediyoruz. Sisam Adası yakınlarında meydana gelen 6.9 büyüklüğündeki deprem son 100 yıl içerisinde bu coğrafyada meydana gelen sayılı büyük depremler içerisinde yerini almıştır. Etkisi İzmir şehrimizde, İzmir ve Aydın'a bağlı yerleşim alanlarında ve Sisam Adası'nda dahil farklı yerleşim alanlarında ne yazık ki can kayıplarına ve hasarlara neden olmuştur. Ben bu vesileyle tekrar bu depremde hayatlarını kaybeden tüm vatandaşlarımıza Allah'tan tekrar bir kez daha rahmet diliyorum. Bilim insanlarımız tarafından binlerce artçı deprem sırasında elde edilen ve elde edilmekte olan değerli veriler, Sisam fayının daha iyi incelenmesi için stratejik öneme sahip olmaya devam ediyor. Deprem odaklı yer bilimleri araştırma alanına dayalı olarak depremlere karşı en önemli gücümüz bilimsel veri üretimi, ortak amaçlara odaklı birlikte çalışma yaklaşımı ve bilimsel verileri birlikte değerlendirme gücümüzdür. Önemli depremlerin meydana gelmesiyle bu depremlerin anında ve deprem sonrasındaki yüzey deformasyonlarının en kısa sürede yerinde incelenmeye başlanması kritiktir. Değişmeye devam eden fay hattı hareketleri karşısında depreme ve artçı depremlere neden olan fay hattı özelliklerinin tespit edilmesine yönelik eşdeğeri olmayan verilerin elde edilmesi için saha çalışmalarında zaman ve süreklilik en önemli kaynaktır. Deprem odaklı yer bilimleri araştırma alanı saha çalışması desteğimiz kapsamında 30 Ekim 2020 depremi sonrasında araştırmacılarımıza saha araştırması ve veri planları alınarak 24 saat içerisinde araştırmacılarımızın ekipleriyle birlikte sahaya intikal ederek saha çalışmalarının zamanlı bir şekilde yürütmesine destek sağlamaya çalıştık. Saha çalışmalarını yürüten araştırmacılarımızı ziyaret etme imkanımı da şahsen araştırmacılarımızın diri fay hattını yönelik çeşitli incelemelerine de şahsen tanık oldum. Bazı incelemeleri ise birlikte gözlemleme imkanı bulduk. Yürütülen araştırma sonuçlarının bir kısmı bugün ve yarın gerçekleştirilecek olan oturumlarda paylaşılıyor olacak. Deprem odaklı verilerin sadece kara tarafında değil, deniz tarafında da toplanması oldukça önemlidir. Mevcut batimetri verilerinin ötesinde yüksek çözünürlüklü deniz tabanlı profilleme çalışmalarının ileriye taşınması için platform yaklaşımı içerisinde Kuşadası Körfezi Seferi'nin ilk aşamasını 28 Mayıs yani bu ayın 28'inde gerçekleştirmeye başlıyoruz. Biraz önce AFAD Başkanımız da kendileri de ifade ettiler. TÜBİTAK olarak bu sefer için 3,5 milyon TL bir destek bütçesi ayırdık. Ve milli araştırma seferimiz kapsamında milli araştırma gemimiz olan TÜBİTAK Marmara araştırma gemimizde farklı üniversitelerden bilim insanlarımızı bir araya getiriyoruz. Dolayısıyla bu yaşamış olduğumuz güçlükte bunu bir fırsata dönüştürme noktasında tüm ilgili araştırmacılarımızı bir araya getirip normalde bunu hemen deprem sonrasında yapmayı planlamıştık. Ama daha iyi planlı bir şekilde çalışma için gerekli hazırlıklar tamamlandı ve bu ayın 28'de inşallah ilgili üniversitelerimizden araştırmacılarımız, bilim insanlarımızla birlikte bu sefer gerçekleştirilecek. Bunu da yapmaya yaklaşımımız birlikte çalışma, birlikte başarma yaklaşımıyla gerçekleştiriyor olmamız deprem odaklı yer bilimleri ekosistemi için önemli bir kazanım olacağı görüşündeyim. Bu sefer ortak amaçlar için aynı gemide bilim insanlarımızın, araştırmacılarımızın birlikte çalışmasına yönelik örnek olma özelliğini de taşıyacak. deprem odağında ekosistem seferberlik edilmesine yönelik sağladığımız diğer imkan, TÜBİTAK 1001 programımız kapsamında açtığımız deprem araştırmaları özel çağrısı olmuştur. Bu çağrımız kapsamında deprem araştırmaları alanının çeşitli temel ve uygulamalı araştırmalar konularına da özellikle yer verdik. Bu kapsamda çok yönlü yer bilimi araştırmaları, kapsamlı senaryo çalışmaları, öngörü ve analiz çalışmaları, deprem mühendisliğine yönelik dijital teknolojiler, arama kurtarma faaliyetlerinde robotik sistemler, yenilikçi inşaat modelleri ve ileri malzeme teknolojilerinin kullanımı, mimari tasarımlara yönelik mühendislik çözümleriyle depremin sosyoekonomik ve toplumsal yaygın etkilerine yönelik araştırma proje önerilerini aldık. Dolayısıyla oldukça geniş bir alanda ve özel bir çağrıyla yürüttüğümüz bir süreç oldu. Ayrıca ilk kez deprem araştırmalar çağrısı kapsamında getirdiğimiz bir yenilik olarak da eşgüdüm projelerine ekstra puan imkanı sağladık. Yani birden fazla proje önerisini ortak yol haritası kapsamında etkileşimli olarak bir araya getiren eşgüdümlü projeleri teşvik ediyoruz. COVID-19 Türkiye platformunda olduğu gibi insan kaynağı ve altyapı paylaşımı dahil olmak üzere ortak hedeflere katkı sağlayan eşgüdümlü projelerin oluşturulmasına yönelik öncelikler verdik. Deprem araştırmaları ekosisteminde eşgüdümlü projeler oluşturarak temel bilimlerden yükselen teknolojilere kadar geniş kapsamlı platform yapısının inşa edilmesini sağlıyoruz. Bu vesileyle buradaki elde edeceğimiz deneyimi ileride diğer bizim ülkemiz ve bölge için öncelikli olan alanlara da taşımayı hedefliyoruz. Bugün başlamış bulunan Uluslararası Aktif Tektonik ve Seismicity çalıştayının 4 farklı oturumunda 30 Ekim 2020 tarihli Sisam Adası depremine özel atfedilmiş olan oturumda deprem öncesi, deprem anı ve deprem sonrası elde edilen gözlemlerin ülkeler arasında paylaşılıyor olması, ortak olarak paylaştığımız Sisam fay hattının işbirliği içerisinde incelenmesi açısından önemli bir adım olarak ön plana çıkıyor. Bu özel oturumda Türkiye ve Yunanistan'dan katılacak olan araştırmacılarımızın katkı sağladığı bilimsel sunumlarda makrosismik ve jeoteknik gözlemler dahil olmak üzere depremin meydana geldiği alana ilişkin gözlemler, deprem öncesinde yeraltı suyu ve jeotermal kaynaklarda gözlemlenen düzensizlikler, deniz seviyesi değişimleri, uydu tabanlı hızlı hasar tespit çalışmaları ve depreme daha dayanıklı bina çalışmalar için veriler paylaşılacaktır. Aktif tektonik ve sismisite oturumlarında ise 30'dan fazla bilim insanının katkı sağladığı sunumlarla kıyı ötesi jeomorfoloji ve aynı anda tsunami, deprem ve küresel salgın gibi birden fazla tehdidin birlikte yer aldığı çoklu tehlikelere yönelik yaklaşımlar da ele alınacaktır. İlgili konular çok disiplinli araştırmaların önemini bir kez daha ortaya koyuyor. Jeodezi ve aktif tektonik araştırmalar oturumunda ise birbirini tamamlayıcı farklı araştırma yöntemlerinin paylaşılması bu coğrafyada deprem araştırmalarının geleceği için umut vaat ediyor. Yaklaşık 60 araştırmacının, bilim insanının katkı sağlayacağı sunumlarda saha çalışmaları, interferometrik, sentetik açıklık, radar ve küresel konumlandırma sistemi tabanında toplanan veriler dahil olmak üzere veriye dayalı olarak aktif tektoniğin daha iyi anlaşılması ve modellenmesi için önemli gelişmeler sağlanmış bulunuyor. Sismik ve tsunami risklerine karşı değerlendirmeler, uyarı sistemleri, tsunami riskine karşı hazırlıklı olunması için mühendislik yaklaşımlarının paylaşılacağı tsunami oturumunda da Japonya ve İtalya dahil 4 farklı ülkeden bilim insanlarımızın katkılarını içeren sunumların paylaşılıyor olması bu alandaki ortak araştırmaların arttırılması için önem taşıdığı görüşündeyim. Bu çalıştayın araştırma sonuçlarının paylaşılması ortak oturumların ötesinde deprem araştırmalar alanında birlikte çalışma yaklaşımının arttırılmasına yönelik önemli bir adım olacağını öngörüyorum. Yer bilimleri araştırma alanında iklim değişikliği gibi sınır tanımayan diğer önemli bir araştırma konusunun da bilim insanları arasında sadece işbirliği yerine birlikte iş yapma kültürünün gerçekleştiriliyor olması önem kazanmıştır. Her yeni bilimsel bilginin paylaşılarak daha değerli olduğunu, birlikte iş yapma yaklaşımı içerisinde de etki sağlama odağında da yeni imkanların önünün açıldığını vurgulamak istiyorum. deprem araştırmaları alanında birlikte çalışma ve birlikte başarma yaklaşımı ile, bir diğer ifadeyle co-creation, yakalanması mümkün olan imkanların altını çizerken çalıştaya katkı sağlayan tüm bilim insanlarımıza, araştırmacılarımıza teşekkür ediyor. Ve özellikle toplantının organizasyonunda emeği geçen hocalarımıza yine teşekkür ediyor. Ve etki odaklı araştırmalar ile birlikte kendilerine başarılar diliyorum. Hepinizi saygıyla, sevgiyle, hürmetle selamlıyorum.
Çok teşekkürler Sayın Başkanım.
Many thanks to Professor Mandal. And thank you very much for all other distinguished speakers at the opening session. Yes, we have completed our opening session.
Now we can start our first session. This session will be chaired by Professor Spiros Pavlides. He is the one who will give both the opening and closing speeches of this workshop.
And now, if Spiros is ready, we can open the first session of the workshop.
Professor Pavlides will chair this session. He is my old friend.
We first met
Each other in Izmir at the ESCA meeting almost 30 years ago, together with
Ricardo Caputo. He is the first speaker of this session.
So I am very glad to introduce him to you. He will be speaking
On active tectonics of the broader Aegean region, an overview and new challenges. The floor is yours, Spiros.
Thanks, dear friend Oran. Can you give me the permission to share my screen with all of you?
Sure.
Because you are the host. And I would like to ask Ricardo Caputo. He sent a message that Gian Maria Boccini is not here, isn't it, Ricardo?
No, he should be. He's connected as a spectator, and I asked to the technicians to switch him into the speakers. Spiros, you have the bar below with the green bottom. Okay, you got it.
Sorry. Sir. Can you see my
Yes.
picture?
Yes.
Okay, I return to the full screen now.
Okay, that's great. You can start now.
Great. So, this presentation will be highlight on what has been achieved on the Aegean active tectonics in a nutshell, in brief. We live in an earthquake region, and we have some models which are very simple. The area is geodynamically very complex, naturally it's complex, and our models simple. Some of the most important achievements of the explosive development of geosciences, in particular on the Aegean region, are the earthquake-related faults, faults relieved by their strange signature, the morphotectonics and landscape, the pre-instrumental seismicity, and especially paleoseismology, satellite geodesy, the understanding of the seismogenic layer, the active fault maps and databases for seismic hazard assessment, and important, the earthquake science and engineering, which are joined. From the first world's mapped seismic fault in northern Peloponnese in 1861, we realized, we understood what is strike-slip fault, and especially the North Anatolian fault that 60 years ago, it wasn't there wasn't this knowledge that it was a strike-slip fault. Various proposed models, when converging or diverging views have been developed for the Aegean, many different faults with similarities and differences, while we know the active stress pattern, both from geological data from earlier of 80s and seismological focal mechanism, and recently geological. And this is a very simple picture of the neotectonic, the older and the active stress field on the Aegean. The satellite geodesy and the blocks are very important, but you have the opportunity to see my colleague Alexandros Hatzipetrous to speak on this subject a little bit later. Now let's see some characteristics of active faults of the Aegean. First of all, I would like to pay your attention for the new definition of the active faults in Greece, which give emphasis on the from Aegean to late Pleistocene mainly, Woermian and Holocene, and it is a very detailed definition. It separates the seismic fault, that of observed surface seismic ruptures, the potentially active faults, and inactive faults or unknown activity faults. These faults should not be considered in the design of technical works except as discontinuity surfaces. The Aegean type fault, characterized by Hancock and Stewart, they have a repeated seismic activity which does not produce surface ruptures along the same fault strand. A fault activity deviating from the characteristic earthquakes, and we have earthquake clustering, as we know also from paleoseismological research, fault segmentation triggering, an important issue, and the displacement is a few tenths of centimeters. As we can see in these pictures, the normal is 10 to 20 centimeters vertical displacement, and rarely is 1 meter or more. The prehistory of faults from seismologists, in fact, they are seismogenic sources related to recent earthquakes, and many faults, many maps of active and possible active faults have been published by different authors for the Aegean. Here you can see the most spectacular active fault in central Greece, which have been characterized by Jackson and Mackenzie as the best exposed worldwide normal fault. In northern Greece, the main active faults of the northern Greece, and especially in the area of Thessaloniki, surrounded by many faults and earthquakes, as you can see in these pictures, and the fault ruptures, the coseismic ruptures, which been for the first time studied in detail after the 1978 earthquake by different groups of scientists. And in addition, in combination with paleoseismological results, which the first paleoseismological research from Greece started from this area after this Thessaloniki earthquake, we have this great parameter of slip rate, paleoseismological, historical, and instrumental earthquakes. The creep also have been studied in the area. We have seismic movements along the same faults after 10 and 25 years after this important earthquake. And as you can see in these trends, you can see the increase of displacement by 8 to 10 centimeters after 20 years of the earthquake. An important fault, the Krupnik fault, is associated with the so-called Kresna earthquake, which was believed to be the strongest European earthquake in the 20th century. It's from the Bulgarian territory, very close to the Greek border. The active segmentation of 1904 earthquake, where our team has been used morphotectonic criteria like the triangular facets and to study that it was a displacement, a vertical displacement of 2 meters. And the strange thing is that the gas pipeline passes from this point. Morphotectonic criteria and methodologies have been applied in the nearest to Thessaloniki active faults, like that of the 1932 earthquake sequence, the Stratoni fault, a typical active fault. Here you can see some profiles, and especially the methodologies for a segmentation of this fault. Mapping offshore fault is still problematic. We will see later by my colleague Sakellariou, except in the areas who have enough data, like in the North Aegean basins, the North Aegean trough. Here is from Papanikolaou the publication, and additional data for deformation that appeared after strong earthquakes like this earthquake. Here you can see in example how we approach the North Aegean trough active faults. They are the extension of the North Anatolian fault, and you can see this Samos race, which is surrounded by active faults, and especially its southern part with the North Aegean fault trenches, a very characteristic uplifted hanging basin, the waterfalls on the fault surface. An important thing is also the urban geology, the urban active tectonics geology, like in Attica and its faults, and Thessaloniki, which also is surrounded by faults. Understanding active fault behavior, you can summarize a few words that repeated seismic activity does not produce surface ruptures along the same fault. Fault activity seems to deviate from the recurrence intervals predicted by the past earthquakes, but we don't know why. The paleoseismological research, which has been studied from our team at our university, it's still in academic level in Greece, and not like in Turkey and other countries by geological. I will show you our last work in central Greece in a fault in a plain where the last earthquake of March have occurred by our team. This research shows that the faults of the southern Greece and northern Greece, they have different recurrence intervals and different slip rates. All this, the paleoseismological regards, they give the slip rate. I will give a little bit more emphasis on the archaeoseismology, and I will give you two examples, one from northern Greece, which possibly associated with a strong earthquake, the known in bibliography of Edirne Andrianopoulos earthquake of 1752, possibly, and you can see the tumulus of the second century during Roman period. You can see here the subsidence, and after the excavation, the ruptures of this earthquake, as well as the seismic faults and its profile. A second example, among many others in the Aegean, is the Troia, which is characteristic, the Homeric landscape. It was a bilateral project between the Onsekismat University of Çanakkale and Thessaloniki Aristotle University. Here you can see the Scamander basins, the Troia fault, where also applied the same criteria for segmentation of this fault. geophysical data by our colleagues from Çanakkale University, and public data, shallow boreholes, and we have some large trenches, and we have some preliminary results and dating results for this area in order to understand the Troya landscape in 3D. Another example of archaeoseismology comes from the famous Delphi Oracle, northern part of the very active area of Corinthian Gulf, where you can see an important fault, and especially the smaller faults that affect the archaeological site. So among the greatest achievement was that we have understood the brittle processes of the uppermost crust, and especially the seismogenic layer. And now we know that the majority of the surface earthquakes occur in a depth of 10 to 20 kilometers. We have modeled now the active faults, and the recognition of the blind strike-slip faults. Here is an example from Northwest Peloponnesus, which recognized studying the surrounding faults, and it is important that it is a blind fault. And another area, which is simply, according to seismologists, the strike-slip fault of Cephalonia in Ionian Sea, in fact, is a very complex area, similar to that San Andreas, which is a compressional area with reverse faults, very complicated, and thrust faults. New techniques have been applied in order to detect faults in plains, like in Thessaly plain. This is in progress, a new PhD thesis in our university. And another important issue is the growth of normal faults in the Aegean area. Normal faults, they 3D, which are commonly consist by numerous faults that they interact and make more complex the system. This is a work in collaboration with a fault analysis group of the University College of Dublin, with the Logos postgraduate students, and all these have been summarized in databases, systematically collection, quantification, homogenization, and integrated view. The prehistory is of Faust project, data from different sources, and we have the individual seismogenic sources in this example, which were well studied. Also from, they based on the INGV, Basili et al., composite seismogenic sources, and fault traces, fault scarps, etc. for this a very important North Greece Servia fault and its extension to the seismic fault. Here you can see the fault surfaces in 3 graphical traces combination. You know, there are many fault length, earthquake size, empirical relationships on the subject, and are with Riccardo Caputo, which needs to be improved. Another database in Greece exists of National Observatory of Athens and the new Seismotectonic Atlas, but now a new database of active faults and seismogenic. The Seismotectonics of Greece is in progress by the Earthquake Planning and Protection Organization. Also, all this included in the European and worldwide databases. Concerning the ground deformation and especially the liquefaction phenomena. There is also by our group a database and all concerning the database DALO for liquefaction phenomena, historical and from recent earthquakes like that of Kos Bodrum as well, all in a database. Concerning the South Aegean, and a well-known area, here you can see from Sakellariou and Nomikou maps and our tectonic map of Santorini, where faults and dikes are in close association. The stress inversion methods here applied, and we distinguished two different simultaneous extensions affected, associated with the fault segmentations of these strong earthquakes and volcanic ascendants, and all this summarized in the Aegean area as according to the fault time. The data have been used for the new zonation, not only in seismological data, including geomorphological and especially the active faults and recently geodetic data. And an example of application was in the Trans-Adriatic pipeline and in seismic hazard assessment. Now, concluding challenges. The new generation of earthquake scientists have to solve new problems, such as the geometry and growth of faults in 3D, water fluid and seismogenesis, an important issue, the accurate slip rate measured in geological times for the most of the active faults, fault rupture propagation, and especially the nearest segments, displacement gradient on the bed parallel slip surface, formation of relayed zones, a complicated distribution on the fault surfaces. An important issue is that fault earthquakes and constructions, we have learned what engineers need to design and what they expect for us. An open issue in my country, and I think worldwide, is the ban of building constructions along the active fault zones. So our understanding of the mechanism that drive extension in the Earth's lithosphere, and we have collectivity to be revised all the variety of these existing models of the Aegean. Now we need to summarize one model. Most of these questions center on how uppermost crustal deformation linked and related to meet the transition layer and especially the lower crust activity, as well as the lithosphere and mantle processes, because magma bodies, especially in South Aegean, they drive through the heat from upwelling and asthenospheric mantle beneath the Southern Aegean. And the last and not least for me is how inherited complex structures drive active crack deformation. In this picture, you can see how complex is the pre-alpine and alpine basement, and we will see in our next, in the last talk for the last earthquake in central Greece. Thank you. Grazie, ευχαριστώ. Teşekkürler. Your microphone.
Yes, teşekkürler, Spiros. Thanks very much for the great opening speech. So we have not received any questions for your speech. So I think everything was very clear, I guess. I can just only remind you that the participants can ask their questions through comment section on YouTube channel or by using the Q&A section at the bottom of their Zoom application. So We can leave.
So the next is Gian Maria Boccini.
Yes, I think he's online now, and I just leave the floor to you, Spiros. Thanks very much for your speech.
Yeah, I'm not able to share my screen. I don't know why.
Σπύρος, πρέπει να σβήσεις εσύ. Να βγεις έξω. Όχι από εκεί, από κάτω.
Stop share. Yes.
Yes.
Yes.
Okay.
Yes. Sorry.
Yeah, it says the organizer disabled the sharing of your screen. I don't know why. So I have the option to share the screen, but I cannot do that.
The host can give you the permission. Try again to share.
Yes, now I can. Yeah. So can you see my?
Yes, we can.
Slide? Yeah. Okay,
yes, we
cool.
can. So everything is perfect.
Okay, so I am Gian Maria Boccini, a postdoc at the University of Bochum in Germany, but the work that I will be presenting today has been carried out mostly during my PhD at the National Observatory of Athens and in collaboration with the University of Kiel in Germany. Before starting, I would like to acknowledge the contribution of several colleagues that are listed below. And I also like to thank the organizing committee and Professor Caputo for having invited me to give this talk on slab dynamics and seismicity distribution in the Hellenic arc. So the term Hellenic arc is often used to refer to the arcuate shape of the Hellenic subduction systems, which is nicely visible by the curvature of the Hellenic arc of the Hellenites, which is the orogen associated to the Hellenic subduction system, and even by the distribution of the seismicity. So the Hellenic subduction system lies in the Eastern Mediterranean region, a region character at the boundary between, at the convergent boundary between the African and the Eurasian plate. The area is characterized by strong deformation, as we can see from geodetic data, and which depict the spectacular counterclock rotation of Arabia, Anatolian, and Aegean with respect to Eurasia. So with the velocity and convergence that reaches 4 centimeters per year at the Hellenic Trench. If we look a little bit more carefully, we see that these vectors increase towards the Hellenic Trench due to rollback of the slab. So the high deformation is translated in high seismicity in the Aegean region, with some of the most seismically active region being the North Aegean Trough, the Corinth Rift, the Kefalonia Transform Fault, and all the area in the outer forearc from the Kefalonia Transform Fault to southwestern Turkey, where the interplate seismogenic zone is located and where the largest earthquake on Earth are expected to occur. And here, if we also pay attention, we see that the Central Aegean doesn't exhibit strong seismicity, while stronger seismicity we observe in the Southeastern Aegean and at the border between Turkey and Greece. Here, I also want to point on the presence of the Hellenic Trench, which is a peculiar feature of the Hellenic subduction zone, not seen at other convergent margins. And that at the beginning was considered to be the subduction trench. Now we know that is a morphotectonic feature. To the south of Crete, it takes the name of Ptolemy, Pliny, and Strabo trenches. So how this beautiful area developed, it has a very long history, and seismic topography results tell us that the slab is visible down to 1,500 kilometer depth, which has been reconciled with the subduction of 3 oceanic basins and 2 interposed continental platforms since middle late Jurassic, so more than 200 million years of subduction. So the last oceanic basin is still subducting nowadays, while the last continental platform is still subducting to the north of the Kefalonia Transform Fault. So since the development of the subduction system, it has been migrating south-southwestward. Here I want to focus on the last 35 million years and looking at the reconstruction proposed by Jolivet et al. In 2013. So if we look at 35 million years, it's more or less the time when the Pindus Ocean closed, namely the last oceanic basin subducted, consumed. We see that the trench, this line with barbs, was pretty straight, and as well as the slab, this thick line here, it's the 100 kilometer slab as a depth reconstructed by the deposition of the volcanic arc. At 2350 million years ago, we see that the oceanic lithosphere, which is still subducting today, started entered the subduction. The curvature of the trench increased, as well as the slab increased and started to migrate southward. And here we see at 50 million years the appearance of a discontinuity in the slab between Turkey and the Aegean. At 10 million years, we see that the North Anatolian fault appears in the system, but only at about 5 million years it starts to interact with the Aegean tectonics. At 5 million years, we also see the development of a second discontinuity in the slab in the area of the Corinth Rift. So this is the current situation where we have our subducting slab separated by two discontinuity, which represent the eastern and western termination of the Hellenic subduction. So how do we know about this discontinuity in the slab? A good method to look for them is seismic tomography. So at the eastern termination, we have almost no doubt about the presence of a tear between the Hellenic and the Antalya slab. However, what is still debated is the geometry of this feature. And since the pioneering work on step fault by Goovers and Wortel, it has been proposed that the eastern termination is a step northeast southwest striking step fault, forming as a result of the deeper tearing in the slab in the same direction. The western termination is a little bit more complex in terms of that slab detachment, horizontal detachment, vertical tearing, or even smooth transition between oceanic subduction to the south of the Kefalonia fault and continental subduction to the north of it can be present. And so, moreover, another kind of discontinuity has been also proposed, looking at this based on the distribution of intermediate depth seismicity. And in particular, some people thought that the slab could be segmented somewhere between Crete and Rhodos, based on the geometry of the Wadati-Benioff zone and also in the intensity of seismicity. Here, if we look at this figure, we see a pretty well-defined Wadati-Benioff zone down to 180 to 200 kilometer depth. We see a steeper slab in the area of Rhodos, number 4 here, with respect to the west of it. And also we see in this Rhodos area a much intense intermediate depth seismicity. And also, as I mentioned before, we see a slab down to 1,500 kilometer depth, while the Wadati-Benioff zone reaches 180 kilometer. So from this short introduction, I formulated some of the open questions that I will try to address during the rest of my talk. So which is the geometry of the slab at its western and eastern termination? What causes the sharp increasing of the Wadati-Benioff zone dipping angle from west to east? What controls the down dip limit of the Wadati-Benioff zone, and how are subduction-related processes reflected in the distribution of seismicity? To do so, I used seismicity hypocenters from global and local networks. About the local networks, I had access to some of the best catalogs available for the southeastern Aegean. And the idea was to refine the geometry of the seismically active slab, starting from available models, and then with the refined geometry go to related to the distribution of seismicity, both at shallow and intermediate depth seismicity. Here I want to clarify that the resolution of the slab, the model that we have, is higher in the southeastern Aegean than to the west, because in the southeast we have access to local catalog from local seismic networks. So now I start from the western termination. So here we see a plot of intermediate depth seismicity at 20, at ranges of 20 kilometers from 60 to 80 to larger than 120. So here is the location of the Kefalonia transform fault. So if I would trace an ideal line on the continuation of the Kefalonia transform fault, we see that south of it, we have a seismically active slab, while north of it, we have a seismically not active slab, and this reconciles well with the presence of continental lithosphere and oceanic lithosphere. So the Kefalonia transform fault can be interpreted as step fault link at the boundary between oceanic and continental lithosphere. So if we look in the literature, this prolongation of the Kefalonia transform fault, it could be the Tesprotico-Alakmon fault zone, which activity terminated about 3.5 million years when the Gulf of Corinth started to open. So here also, if we see that, and so the Gulf of Corinth, could have caused the migration of the strike slip deformation from this on-land structure to the Kefalonia transform fault, and may even control the fact that the Kefalonia transform fault doesn't prolongate more inland. So here it's also nice to notice how the Corinth Rift is located in an area separating to the south. We have a deeper Wadati-Benioff zone, while north of it, the Wadati-Benioff zone reaches only 100-120 kilometer depth. So in the area of Peloponnese, we performed some tectonic reconstruction, and we could see that the down deep extent of the Wadati-Benioff zone is consistent with the amount of subducted oceanic lithosphere since about 15 million years ago. I didn't put more detail on this, but I have some slide in the end. If you like, we can discuss about that. If we move at the eastern termination, which is more relevant for the workshop of today, we see beneath south, in the area of Rhodos, the presence a clear northwest dipping Wadati-Benioff zone, and which it's not compatible with the presence of a step fault in this area of the Pliny-Strabo Trench, because if a step fault is here, then we don't expect subduction in this direction, while we see it from seismicity. Then we have a northeastward dipping slab beneath Turkey. This is the Antalya slab. And then between them, we see an area depleted in intermediate depth seismicity, which corresponds with the slab tear. So we can refine the geometry of the tear down to 180 to 200 kilometer depth. As I mentioned, at the eastern termination, we had also available local seismic network catalogs. In particular, this is the Agelados catalog and the SICNET catalog here. So we see refined models of the Wadati-Benioff zone, which is less steep and less active in the area of Crete, profile 1 here, while it gets steeper in the area of Rhodos and more active. And then if we look, we notice that in between these two segments, we started to observe a double seismic zone that we went then to investigate a little bit more. And after, here we see an overlapping of the seismicity along profile 1 in the area of Crete and the area of Karpathos, Rhodos. Here we see at depth larger than 60 kilometers, a clear offset in the Wadati-Benioff zone, and also a clear distinction in the activity rates. So after excluding that it could be a double Wadati-Benioff zone, we interpreted the upper plate of our double seismic zone as the top of the slab in the western part in the area of Crete, while the lower seismic zone as the top of the slab subducting in the eastern part. So if this is true, then this will be also compatible with the long strike shortening of the slab, which is nicely visible from the inversion of focal intra-slab focal mechanism solution. So by combining all the information coming from the seismicity, we propose a new refined slab geometry. So I walk you through the most important part of the model. So in northern Greece, we used published data from receiver function because the slab, the continental slab here is not seismically active. Then moving towards source, there is a vertical discontinuity separating this continental slab from the oceanic slab. Then we have the Kefalonia transform fault that lies along north edge of the oceanic slab and represents a step fault. Then moving towards east, we have the first order segmentation of slab, which is visible at depth larger than 60 kilometers, separating a shallower and wider segment from a narrower and steeper segment. And the causes of this segmentation could be due to the aging of the slab from west to east, as nicely shown by also, for instance, magnetic data, which indicate a younger slab in the Ionian area and an older slab in the Rotubus basin. And then we have the tear in the slab separating the Hellenic slab from the Antalya slab. So the formation of this tear in the slab, together with the first order segmentation, enhanced the curvature of the slab and also the asymmetry in the curvature that we see today. This is nothing else than a 3D model of this 2D map view, and with the gray are the expected mantle flow in gray here, and while in white we have the relative motion between the different segments. So we wanted to check how this the geometry of the slab relates with the distribution of seismicity. What we see in this picture are several seismic profiles along strike. We tried to separate interplate seismicity from intermediate depth seismicity along this fault profile, and we see a clear inversion in terms of released seismic moment in the segments lying above the western slab segment and in the segment lying above the eastern slab segment. Namely, to the west, most of the seismic moment is released by interplate event, while going to the east, we have a more and higher release by intermediate depth events. So this slab segmentation affects the moment release of interplate and intermediate depth seismicity in the Hellenic subduction system. Also, we wanted to check, if you remember in the first slide, I showed how the central Aegean doesn't exhibit strong seismicity, while stronger seismicity and stronger deformation is visible in the southeastern Aegean. Here, we tried to reconstruct the deformation pattern, combining seismicity data, focal mechanism data, and geodetic data. And altogether, this seemed to indicate the detachment of the southeastern Aegean with respect to the central Aegean and Peloponnese. Here we see these velocity vectors with the velocity increasing towards the trench that would be compatible with the presence of a steeper slab in the area and with enhanced rollback. And also this focal mechanism, some also from recent earthquake here, they are compatible with this interpretation of detachment of the southeasternmost part with respect to the central and Aegean and Peloponnese. So this slab segmentation seems also to affect upper plate deformation, giving rise to high deformation in the southeastern Aegean. So here I come to my conclusion that I wouldn't go to them, to leave a little bit more time for discussion and question you have. Basically, it's a summary of what I have been telling during my presentation. So I would like to thank you for your kind attention, and I'm here for trying to answer your questions.
Thank you very much for your interesting presentation. I have a question from Alexandros Katsipetros. Do you have any information on slab tearing or slab delamination in Central Aegean, north of the area you presented? Gian Maria.
I'm not sure if if I have some evidence for slab tearing and segmentation north of the area I presented. Is it this the question?
If you have any information on slab tearing or slab delamination in central Aegean, north of the area you presented.
I mean, there are now some new studies from full waveform inversion where they present these nice models for, but it's more about the area of the Kefalonia fault and the Corinth rift. About slab delamination, I think in the northern Aegean, I mean, people can see that, and it's the only way that you can explain also the subduction of continental lithosphere, which is going down somehow.
By the way, the strike slip fault you presented of the Aliakmon in central continental Greece is questionable. There is no clear field evidence for this fault.
Yeah, that's why I put a dot line and I mentioned that it could represent this fault, but I mean, we don't know if this could be the answer.
Okay, thank you very much for your interesting presentation. Please stop sharing, share, while the next talk is from the Dimitris Ankelariou and Tsambouraki Kraunaki, offshore geomorphology and seismic profiling data indicate active extension, transtension, and strike slip tectonics in the Aegean region. Dear Dimitris, take the floor.
Thank you very much, Spiros, and many thanks to the organizers of this very interesting workshop. Well, the aim of this presentation is to display some old but also new data on the geomorphology and geophysical structure of the area of the Aegean, and then try to extract conclusions on the style of deformation of the Aegean back-arc area. As we know, around the globe there are many back-arc areas, and some of them are characterized by extensional deformation, some other display compressional deformation, while there is also back-arc areas where we see transtensional or even transpressional deformation. So at the end of this presentation, we will suggest that the deformation in the Aegean back-arc area is mostly dominated by horizontal shearing in northeast southwest direction. So let's move on. And okay, we have seen these maps with the GPS vectors and the let's say flow of the Aegean area, the stretching of the Aegean back-arc area towards the south-southwest. So according to these geodetic surveys, the area is characterized by textural strike slip tectonics, mostly along the North Aegean, Marmara Sea, and along the Kefalonia transform fault. There is a sinistral strike slip tectonics along the Strabo and Pliny trenches in the southeastern part of the area. There is the north-south or north-northeast, south-southwest extension in central Greece, like the Gulf of Corinth, for example. And also, geodetic studies have recognized a kind of rigid block that exists in the central southern Aegean that also includes Peloponnese, which is supposed to translate with almost no internal deformation towards southwest. So a very recent paper by Briol et al. Has also tried to quantify lateral movements along the North Anatolian fault in the Aegean Sea, but also along the Movri and the Katuna strike slip faults in Western Greece. And the new thing is that they recognize also a textural transtensional motion in the South Aegean, and actually between Amorgos and Astypalea Islands. And this translational movement is in a northeast southwest direction. And this is, I think, the first time that such a movement has been recognized geodetically. In terms of seismicity and fault plane solutions, things are really clear in the North Aegean, where textural strike slip dominates along northeast southwest striking faults and fault zones. Also, the textural character of the Kefalonia transfault fault is evident, and the sinistral character of the Strabo and Pliny trenches. And then the dominant knowledge is that we have an east-west extension and northwest extension in South Aegean. So as early as in the 90s, we had the expression of the two major hypotheses on the deformation pattern of the Aegean. The one of Armijo et al., which suggests that fast extension is taking place at the terminations of the North Anatolian fault branches, and slow extension takes place in areas in zones which run parallel to the arc, these yellow zones here. And the other hypothesis, which was expressed by Musk and Martin, says that the Aegean region is broken in slabs, in blocks, which are oriented in northeast southwest direction, and they are separated by strike slip zones or oblique zones, which control the deformation and the stretching of the Aegean. So let's see the Aegean itself. So this is the newest bathymetry or digital terrain model of the seafloor of the Aegean, as conducted in the framework of EMOTNET bathymetry project. This is the right map here, and then in the left, we can categorize the bathymetry classes in the Aegean Sea. So we can see that something like 27% of the Aegean is shallower than 120 meters, while 90% of the Aegean is shallower than 1,000 meters, and only the 10% of the Aegean Sea is displays depths between 1,000 and 2,500 meters, and with the deepest depths occurring in the southeastern part and the southern part of the Aegean Sea. This is a slope map here, and we can see that something like 70% of the area is a flat, displays a flat seafloor, and this includes shelf and basins. And if we add on the map the basins, the actual basins, independent of what depth they have, then we see that the basins represent the 12 or 13% of the total surface of the Aegean Sea. And they are, of course, they are surrounded by the slopes, steeper or less steep. And we can see, if we put on this map the active faults that we have mapped in the area, that the steep and less steep faults coincide with the slopes of the area. That means that there is a genetical relationship between the presence of the basins, the development and the development of the slopes with the active faults, which was expected. Let me say that the orientation of the slopes and the faults as well is mostly northeast southwest. Then a second category is northwest southeast, and there is a third category which runs east-west. So what we did is we exploited the available data in the literature from the early days until very recent, and we also processed and reprocessed and interpreted the available seismic profiles, which are in the database that we keep in the Hellenic Center for Marine Research, in order to map active faults and also the post-Miocene sedimentary basins in the Aegean. So I will skip the North Aegean Sea because it is well constrained that extensive dextral strike slip along northeast southwest striking zones is well proved. And I will move on directly to the South Aegean, where situation seems to be more vague. The blue map shows the bathymetry of the South Aegean Sea. You see the depth contours every 100 meters. These are the thin black lines, and every 500 meters, the thick black lines. And what we can see is that the area is characterized by the occurrence of isolated basins and also by elongate ridges. Basins may have different shapes, may be elongate, may be spindle shaped or kind of irregular shape. The thing is that we observe here that the morphological directions again focus on three categories, which are, the main one is the northeast southwest one, the second one is the northwest southeast one, and the third one is the east-west direction of morphological features. And this is also verified by the slope map of the South Aegean here at the bottom left. So we came up with this map that displays the active faults in the South Aegean Sea as derived from the interpretation of literature data and also recent surveys in the area, and also with the occurrence of sedimentary basins. These are the yellow flakes, which are scattered in the South Aegean Sea. So you see there is no let's say, extended back arc basin in the reality. What we observe here is a pattern of isolated basins, both morphological and sedimentary basins, which are scattered in the area in a, let's say, more or less irregular way. If we move on to the geophysical data and seismic profiling data from the early days, this is a site that was drilled in the 70s in the framework of the deep sea drilling project. This is site 378 in the South Aegean Sea, somewhere between Iraklion, between Crete to the south and Santorini to the north. And this site penetrated for a bit more than 300 meters below the seafloor and met two prominent unconformities. The lower one is the Messinian, which marks the top of the Messinian evaporites below that, and the Pliocene sediments on top of it. And the second one is the one with the blue line, is an unconformity which was dated somewhere in the boundary between Pliocene and Quaternary. So interestingly, this second unconformity, the Pliocene Quaternary unconformity, can be observed in almost all basins in the South Aegean Sea. This is a collection of seismic profiles from the publication of Barthollet et al. In 1983. But you can also see other papers like the ones of Rossi, Maskell and Martin, Piper and Perisoratis, and others, which provide strong evidence for an unconformity in most of the basins in the boundary between Pliocene and Quaternary, or somewhere there, as you know, chronological constraints are really not very strong, but it seems that this blue unconformity is somewhere in the boundary between Pliocene and Quaternary. So recently we completed a survey in the area of Santorini, Amorgos, Astypalea in the central southern Aegean Sea. And we came up with this nice morphological map, which says us that this Santorini-Amorgos zone is a morphologically composite one. It includes 7 smaller basins, and which are, for example, this Anidros, the Anafi, the Amorgos South, the Amorgos North, the Kinneros Basin, Astypalea North, etc., which are separated by steep slopes and also by 2 ridges. The one is this one, is Astypalea Ridge, and the other one is this Anidros Ridge. So this interesting and complicated morphological configuration has been also surveyed with seismic profiles, and this is one profile crossing the zone from Amorgos to the north to somewhere close to Astypalea to the south. And this displays again this unconformity, which here is shown in red color, which exists in all basins, or almost all basins of the zone of the Santorini-Amorgos zone. And this separates two different phases of evolution of the basins. The early phase below the unconformity, this is the one which includes units 4, 5, and 6, 4, 5, and 6, etc., shows something like a single unified basin with symmetrical subsidence. The later phase, the one above the unconformity, displays enhanced subsidence along the south-facing faults, and also new faults that have been created and deformed the older part of the basins, and also gave rise to ridges that broke the earlier basin and have given rise to new sub-basins. If we put all the faults on the map, then we came up with this fault network in the area where we have major faults running northeast, southwest, like the Amorgos fault, like the Eos fault zone, like the Anidos Ridge south zone, the Astypalea Ridge fault zone, etc. And minor or secondary faults which run in almost east-west or west-northwest, east-southeast direction. So the two best examples are this one and this one for that. So if we simplify this map and put also the direction of the GPS vectors, is this red vector here, we can extract some conclusions on the kinematic character of the zone. So the GPS vectors show actually the direction of stretching. So what we see here is a direction of stretching which coincides with the direction of rifting, is at roughly 30 degrees angle in respect to the direction of the rift itself. So this drives us back to the nice model of oblique rifting of Whitsack and Jameson, which is shown here as a drawing, which says that in oblique rifting of this type with 30 degrees angle between the rifting direction and the rift axis, then we expect a dextral horizontal component along the northeast-southwest direction faults and an extensional character along the east-west trending fault zones. So what we think and we conclude is that this Santorini-Amorgos zone is actually a shear zone which displays dextral horizontal movement and in northeast-southwest direction and extension in northwest-southeast direction. The data that we have allow us to propose a model for the evolution of the area, which, according to which this Santorini-Amorgos basin initiated in early Pliocene as a more or less east-west basin, east-west tending extensional basin, and then sometime in the boundary between Pliocene and Quaternary, or in the early Quaternary, a change of the geodynamic regime led to reorganization of stress and strain, led to initiation of new faults that broke the older initial basin, gave rise to uplift of ridges, and enhanced subsidence in the sub-basins. So this, the lower sketch displays the situation as it is today, with the several sub-basins which are northward tilted, the uplift of the ridges, and also the occurrence of volcanic activity along and within the Anidos basin. So Similar observations we had from the area a bit to the southeast of the Santorini-Amorgos zone, and in particular between Astypalia and Nisyros here. This is a seismic line shown here, and what we see, we have a very peculiar seafloor with multiple ridges and elongate funnels, let's say. And if we put the interpretation here, we come up with multiple steep faults which produce this nice relief here, and this complicated structure here with extensive southward tilting, which is responsible for the creation of this, let's say, basin and range structure. That area, for that area, in the literature, there are conclusions and hypotheses which point to a sinistral shearing since, let's say, in the early 2010. So let's come up to the entire Aegean Sea. So this map shows the sum of all the faults that we have mapped in the Aegean Sea, and also all the sedimentary basins which display thickness more than 500 meters in Pliocene and Quaternary. So what we see here actually is that, again, the major category of faults runs in northeast-southwest direction. Then the second category displays northwest-southeast direction. And then there's a third category which strikes west-east. And this third category also includes the fault that has given the recent earthquake north of Samos in last October. Well, if we superimpose the GPS vectors and the faults that we have mapped, then we can start thinking what is the relationship between the direction or the strike of the faults and the direction of stretching. We propose that the angular relationship between the strike of the fault and the direction of stretching may be responsible for the kinematic character of the faults. So we think and we propose that faults which strike parallel or subparallel to the stretching direction should display mostly horizontal component, while faults which are at a high angle to the stretching direction should display mostly vertical component. In that sense, okay, the deformation is also confined between the two major boundaries of the, let's say, Aegean microplate. The northern boundary, which is a dextral strike slip boundary, which includes Kefalonia fault, North Anatolian fault, and Central Greece, which in this sense is represents a kind of pull-apart basin between the two edges of Kefalonia and North Anatolia fault, and the southern fault, which displays a sinistral sense of movement. So what we propose is that the northeast southwest striking faults, which mark the majority of the faults in the Aegean Sea, represent the segments of larger fault zones, like the ones which are shown here in black color, and they display in most of the Aegean, they display a dextral strike slip sense of movement. Interestingly, there is a zone which is shown here with a dust yellow line, which separates southeastern Aegean Sea with sinistral sense of shear from the rest of the Aegean, which displays dextral sense of shear. Then the northwest southeast striking faults should work as conjugate faults to the previous ones, and then they display a sinistral sense of shear, and that was nicely proved with the Skiros earthquake some years ago there. And finally, we have the faults which are which strike east-west and display more normal character. Now, the question is, when did this deformation style established in the Aegean Sea? The unconformity that we saw earlier and with the age of somewhere in the boundary between Pliocene and Quaternary or in early Quaternary coincides with other major events in the broader Aegean region, like the initiation of fast subsidence in the Gulf of Corinth, for example, which is in early Quaternary. Also, the data that we have from the North Aegean Trough, which indicate major deformation since early Quaternary, and this also, as far as I know, is the case for the Marmara Sea. So we think that this type of deformation with a northeast-southwest extensive shearing was established in early Quaternary and is associated probably with the propagation and arrival of the North Anatolian Fault in the North Aegean Sea. Thank you very much for your attention. I'm open for questions as you like.
Thank you, dear Dimitris Sakellariou. I think there are no questions in the question and answer room. Only Tunçay Taymaz sent us three very recent publications, both for the SLAP and the Aegean, published recently in 2020. I would like also to ask if there is a last minute question. So, thank you, dear Dimitris. The next speaker is Massimiliano Maghini and Riccardo Caputo, 3D rheological modeling of the Aegean region, its implication for the seismotectonics of the area. Massimiliano, you have the floor, and
okay.
Please share your screen.
Yes. Here I am. So can you see it?
Yes, we can.
Okay, and can you hear me properly?
Turn to full screen. Okay. It's okay.
Okay. Very good. Thank you, Professor Pavlidis, for introducing me, and thank you to the organizer for inviting me. So now I am Massimiliano Maghini. I'm right now a postdoc at the University of Urbino. While the project, the talk that I will give you today is related to my PhD project that I carried out in Ferrara with Professor Caputo. So the main topic of this talk is the 3D rheological modeling in the Aegean region and its relative implications for the seismotectonic features of the area. So the main objectives of this work are, first of all, the assessment, the evaluation of the most important parameters for what concerns the realization of 1D rheological profiles. And then obviously the realization of this complete 3D rheological modeling for the Aegean region with a specific focus on the BDT, so the brittle to ductile transition depth. And finally, also the assessment of rheological modeling as a tool, an effective and reliable tool to link to the seismogenic behavior. So, for what concerns the geodynamic framework, I will just go quickly here because the previous speakers have already thoroughly described it. And so it is generally the study area just corresponds to the broader Aegean region, including also Western Anatolia region. So now for what instead concerns the rheological profiles, here we assume the classical approach with the brittle and ductile deformation being respectively represented by the frictional sliding, which is here represented by the equation at the top, and by the power law creep for the ductile deformation, which is the middle equation. And also shown here at the bottom is the equation for the geothermal gradient calculation, which enters directly the exponential term of the power law creep. So it's very important, it's very relevant for obtaining a reliable logical profile to determine appropriately the geothermal gradient. And then you see here on the graph on the left, this small red square here indicates the position of the brittle to ductile transition, so the position of the BDT. And we will focus mainly on this, on the depth of this brittle ductile transition, especially in the crust, so that the shallowest, let's say, brittle ductile transition, if there are more than one, because we are interested mainly in the upper crust seismotectonics. So you see circled here a lot of the parameters from these equations, and for all these parameters we had to collect data mainly from the literature in order to proceed with our modeling. So I will just show you some of this data now. So the concept behind this work was first the collection of data mainly from the literature and from tectonic geodynamic consideration, and at the same time we also developed a MATLAB script in order to proceed with our modeling. So for what concerns, for example, the heat flow data, here we took into account data from different scales and sources, and we obtain a final weighted average map highlighting, for example, the highest values along the volcanic lenic arc. Similarly, for the strain rate, again, different sources of data, we try to merge them into a final weighted average map, highlighting again the concentration of strain along the main deformational belts. For the crustal thickness data, here we took into account more depth maps as obtained with different geophysical methods. And again, the final weighted average map indicates a very thick crust below the Hellenites and a thinner crust below the Aegean Sea extending region. For the tectonic regime, instead, we use mainly the indications given by the GREDAS database from Caputo and Pavlidis. So the database of the seismogenic sources, we considered the respective rakes of each source and try to define this tectonic regime map with the red colors indicating prevailing compression, the blue colors the extensional region, and then the yellow colors the strike slip regions. Moving on, for what concerns the geometry of the subduction zone and the slab, we considered some recent models, one from Bocchini et al., another from Apap et al. We tried to merge them together and try to obtain a slab top depth surface that we used for the modeling of the subduction zone geometry. And finally, for the pore fluid pressure, we generally assigned an hydrostatic value to the bulk of the study area. But for a specific region, as for example, the region corresponding to the submarine accretionary complex of the Mediterranean ridge or the continental accretionary wedge close to the Albanites, we selected slightly higher values, indicating suprahydrostatic conditions. So now let's move on to the next step of this talk, which was the sensitivity analysis that we carried out as a first stage of this research. So what we did was try to evaluate the impact, the influence of the variations of any single parameter in the governing equations for the modeling by varying them, by varying every parameters while keeping all the other constant in a first stage. And so, for example, you see here the frictional sliding parameters that are changed with respect to a reference value, which is shown with the magenta curve. And you see that each parameter is changed by 50%. And you see that for the frictional sliding parameters, the main effect of the variations of these parameters on the resulting strength envelope is the change of the BDT strength rather than the BDT depth. So you see the changes the coefficient of this curve rather than the BDT depth itself. Instead, if we consider the creep parameters, you see that in these cases, the variations of these parameters, including the thermal ones, they cause these variations both in the BDT depth and in the BDT strength. And you see that also the most influential parameters seems to be the thermal ones, especially surface heat flow and thermal conductivity. Now, to carry out our sensitivity analysis, we selected 2 case studies in different tectonic settings of the Aegean region, one being to the Kefalonian Trasmon fault region, so a slightly transpressional setting, and the other being the Callidomo region in central Greece, so a purely extensional setting. And we realized the corresponding rheological profiles with the selection of our preferred values for each input parameter. Then what we did was to use a kind of statistical analysis approach similar to, let's say, a Monte Carlo analysis, where we generated more than 100,000 runs by varying all the input parameters together this time, so simultaneously, and varying each of them among its respective uncertainty range. And we try to verify whether there could be synergistic effect maybe with these joint variations. So in terms of the statistical analysis results, we compared them with the values given for 3 variables, being the BDT depth, the BDT strength, and the BDT temperature. We compared them with the values obtained from the reference profiles that I showed you before, which are written here in blue. And you see that the peak of the statistical distributions for all these 3 variables, they tend to fit quite well with the values obtained for the reference profile. And this is observed for both test sites. So we can safely say that effectively there are no real important synergistic effect. And also this kind of variation and uncertainty can be also viewed in this sort of graphical representation of the uncertainties. So you see that for both test sites, this is for the Callidomo one, for example, you see that the darker is the color of the blue cloud around the reference profile, the higher is the concentration of the number of curves falling in that region. So in this way, you can also try to give a first order estimate of the potential uncertainties related to the realization of strength envelopes. And for example, for the BDT depth parameter, in this case, the potential uncertainties is around 1.52 kilometers. Now, at this point, I would like to recall one long-known concept, which is the link between rheology and seismogenic processes at depth, which is has been studied since the 80s from Simpson and Scholz. And the concept here is that the BDT depth could be used as a down dip as a limit to the thickness of the seismogenic layer. And we tried to verify this whether this concept could hold for the Aegean region by comparing the modeled BDT depth according to our modeling for more than 60 test sites in all over the Aegean region in different also tectonic settings. We compared this modeled BDT depth, which is here shown with the dotted purple line. We compare with the seismicity cutoff depth, which is here represented instead by the red dashed line. The seismicity cutoff depth as obtained from relocated seismicity catalogs available in the literature. For example, this is taken from the Lake Trichonis area. You see that western central Greece, you see that there's a good agreement between the BDT and the seismicity cutoff depth. And I will just now show you a couple of examples. We have actually recently published a paper on Journal of Structural Geology about this comparison, if you want to have a look. But anyway, here's another example from offshore Chalkidiki region, so northwestern Aegean Sea, in a transtensional regime. In this case, we consider a background seismicity relocated catalog. And again, there's a good fit between the two indicators. The same could be seen also, for example, here in Lefkada instead, so a transpersonal regime, and considering a sequence seismicity relocated catalog in this case. So we also had the information on the magnitude for this test site, and for all the test sites where we had also this information, we tried to verify how much of the seismic moment was released above the BDT, so within the brittle layer. And almost 100% of the seismic moment was effectively released above the BDT. So we were quite satisfied with these results. So now at this point, I'll move on to the 2D modeling. In this case, we had also, since we work now on a more regional scale, let's say, we had to consider also large-scale processes such as the subduction one. So we try to also take into account the thermal perturbation, for example, related to the subduction process. And we modeled the subduction zone thermal features, and they're quite consistent with other models from literature. So for what concerns the 2D modeling, we focused mainly on the Hellenites and on the potential differences that there could be in terms of logical and then interpretation of the northern Hellenites, which are here characterized by a geodynamic continental collision setting, and so transit from A to C, while instead in the southern Hellenites transit from D to F, the setting here is more typical of an oceanic subduction setting. So we had to assume obviously some very simplified geological models for the continental collision and the oceanic subduction settings. And then in terms of the results of our modeling, here we are focused on the BDT trends, so the variations from southwest to northeast in each case, so moving from let's say, the lower plate to the upper plate. So here are the results for the continental collision transect, A to C, and you see that among them, the three transects are quite similar, but you see that moving from southwest to northeast, the BDT tends to be at around 30 kilometers in the Apulian plate, let's say, and then it moves to shallower depth at around 20 kilometers in the mainland Greece. Temperature instead remains quite constant at the BDT, because the BDT always occurs actually here in this case in continental lithosphere, so it mainly depends on the onset of plasticity for quartz and feldspar minerals. And then the strength tends to decrease because of the shift from the southwest to northeast from a compressional to an extensional setting. For what concerns instead the oceanic subduction transect, D to F, you see that there are some differences from the continental collision settings, in the sense that, for example, in the lower plate, the BDT here lying in the oceanic lithosphere is deeper, is at around 40 kilometers, and then becomes very much shallower in the back arc in the overriding plate at around 10-15 kilometers, mainly because of the very high geothermal gradients in this area. And also the temperature has a different trends, because in the western sectors here the BDT occurs in the oceanic lithosphere, with very much higher temperatures for the onset of plasticity of mafic minerals. And then the strength instead has these similar trends, actually with very much higher differences. So now in terms of the real distribution of brittle and ductile layers and the comparison between the continental collision and the oceanic subduction settings, the main differences that we can observe here, or the blue layer indicates the brittle layers, the red one the ductile layers, and the whitish color indicate the brittle to ductile transitions. So the main difference is, I was saying, is represented by the fact that in the continental collision setting, more than one brittle layer, especially in the eastern sectors, could be observed, mainly because the difference with the oceanic subduction is that in the oceanic subduction setting, there's a very much higher geothermal gradient, especially in the back arc region. So ductile deformation tends to prevail below the first thin brittle layer in the uppermost crust. So now let's move on to the 3D model, the final 3D model that we realized for once seen the 1D strand envelopes and then the 2D transect. this is a representation of the BDT depth and its 3D variations for the Aegean region. So as I said, we were mainly focused on the BDT depth, especially the first BDT depth, the shallowest one. And this is viewed from the south. So just to give you some references, this is the Puglia region in Italy. This is the Albanian coast. And then here is the Western Anatolian coastline. You can see for this representation that in the lower plate, the BDT generally lies at around 40 kilometers for the oceanic sectors, while in the continental counterparts, it is a little shallower at around 33 kilometers, while for the upper overriding plate of the Aegean Sea and mainland Greece, Western Anatolia region, the BDT generally lies at much shallower depth, around 10-15 kilometers, with obviously some local variations, mainly due to heterogeneities in parameters such as the surface heat flow, the strain rate, and so on. So now this is the same representation, but view in map. But here the main point is that we could try to from this map we could try to link to each geodynamic setting a kind of representative typology of profile according to our modeling. So, for example, for the Folding Thrust Belt, the Northern Hellenites region, a kind of jelly sandwich model with more than one brittle layer is the most representative one, while instead the creme brulee model with a very thin brittle layer in the upper crust is generally associated to the extending and Aegean Sea region. Instead, the caramel slab with a very thick brittle layer extending down to the mantle is more typical of the cold and old oceanic crust of the lower plate. Now, for what concerns BDT strength, as I just already showed you in part with the transect phase, with transect slides, you see that the higher values are observed again in the oceanic sectors at the BDT, also because the BDT is deeper here, so the strength is higher. And while very much lower values are observed in the back arc region, even lower than 100 megapascal. Then for BDT temperature, so the temperature at the BDT, this mainly depends on the nature of the lithosphere where the BDT occurs. So the main differences are among the oceanic lithosphere and the continental one. So now, once seen the modeling that we carried out, we try to apply the results to different fields. And here in particular, I will focus on the determination of on the estimation of potential maximum magnitude for seismogenic sources in the Aegean region, which is a sort of an exercise using the constraint given by the BDT. And I will focus on this just later on. Now, I would just also like to mention some other potential applications, which could be, for example, using again the constraint of the BDT, the calculation of seismic strain rate while having better defined the seismically deforming volumes, or also using the results of the modeling to calculate the total integrated strength, for example, for the upper and the lower plate. But now let's focus on the BDT constraint. Again, the concept is that if we have a varying BDT, above it we will have the seismogenic brittle layer, and below it the seismic ductile deformation. And so the variations of the BDT imply variations of the thickness of the seismogenic layer. And then if we add some information on the main seismogenic sources, we can try to calculate the width and then the maximum expected magnitude for these sources in a sort of independent way. Obviously, there are some uncertainties related to the application of the empirical relationships themselves, and also to the BDT determinations, as I just showed you. But also we assume, for example, a complete rupture of this potential seismogenic layer, which does not always occur, obviously. But this is a sort of an exercise to verify how the BDT could give us information on maximum potential magnitudes. So we use the sources as presented in the GREDAS database from Caputo and Paulides. And these are the results. Obviously, we give them with these intervals because, again, we have to take into account the potential uncertainties. The general picture given by this exercise is the fact that the higher values are obtained along the thrust and compressional structures here in the external sectors, while it's more in general, the normal and transtensional strike slip faults of the mainland Greece, Aegean Sea, and Western Anatolia region are generally related to magnitudes between 6.5 and 7. So now to sum up, what I presented here is the logical modeling of the Aegean region, starting from the 1D strand envelope analysis, and where we identified the predominant parameters being the thermal ones. Then, for what concerns the 2D modeling, we realized some transect, trying to focus on the variability of the rheological features, especially of the presence of brittle ductile layers in continental and oceanic subduction settings. And then we presented a 3D model with a shallow BDT, generally around 10-15 kilometers for most of central Greece, Aegean Sea region, and Western Anatolia, and then a much deeper BDT in the lower plate. And finally, we applied the results to different fields, and in particular to the calculation of maximum potential magnitude. The concluding remarks that I would like to make is that generally the strand envelopes could effectively be reliable indicators for the logical behavior at depth that could also be linked to the seismogenic behavior. But obviously, a very careful selection of the input parameter is needed because of the uncertainties. And then also for the 3D modeling, this could help to detect some large-scale trends in logical and seismotectonic features, and could be applied to different fields. So thank you. Now I'm here for questions, if there are any.
Grazie. Thank you, dear Massimiliano, for your work and results presented here. I cannot see any question. Orana, are there questions in the YouTube?
No, I don't see as well, Spiros, so we can have a short coffee break.
And we can start the next session at 11:55, if you wish.
Okay. Let's thank all the speakers of the first morning session, Active Tectonics and Seismicity, and we will continue with the same subject, active tectonics and seismicity, in 15 minutes. Okay, Oran?
Okay, and that will be chaired by Massimiliano as well.
Okay.
Massimiliano will chair the session.
Yeah.
All right. Okay, thank you very much. So see you in 15 minutes.
Yes.
Okay, Massimiliano, I think Ricardo is ready now.
Just open your...
Okay, Massimiliano.
Okay, yes. I can hear
Okay,
you.
now we can start if Ricardo is ready.
Okay, yes. So we can start now the second part of this first session. So the first speaker is Professor Riccardo Caputo from University of Ferrara, Italy. He's also a member of the Major Risk Commission, and he will present a talk with title being Earthquake Geology for Seismic Hazard Assessment in the Aegean region, Single Event Effects versus Cumulative Effects. So now I'll leave the floor to Professor Caputo, if he's ready.
Open your microphone, Ricardo.
Okay, can you hear me now? Thanks.
Yes.
Okay, good morning, everybody. I will not present data or results. I would like just to leave a message to seismic hazard practitioners. Now, let me take this pointer. Okay. Seismic hazard assessment analysis, and especially their products, commonly used in building codes or for insurance purposes, largely depend on either shaking functions and like the GMPs and seismic rates, both local and regional ones. In Mediterranean regions like Italy, Greece, Turkey, but also at the European scale, seismic rate estimates are generally affected by several biases. Firstly, seismic rate estimates are commonly dominated by instrumental and especially historical information that cannot last longer than few decades or few centuries, respectively, in terms of completeness. As a consequence, faults with longer seismic cycles do not and cannot contribute to these estimates. Second bias. Large earthquakes often attract the interest of many researchers, and consequently, the literature corresponding to the causative fault becomes rich and abundant in a short time. On the other hand, silent faults and faults associated with minor events are much less investigated, commonly with the consequence that their degree of seismotectonic parameterization is generally poor and scanty. Accordingly, even when seismogenic sources are included in seismic hazard assessment analysis and their seismotectonic parameters are exploited for estimating the seismic rates, the latter are necessarily affected by a similar bias. A further bias is due to the fact that geodynamic rates in the Mediterranean region, along with slip rates of active faults, of course, are commonly low, while recurrence intervals are quite long. It is therefore obvious, though objectively difficult to quantify, that the fault reactivated a few decades or few centuries ago is likely in its initial stage of the new seismic cycle and far from critical conditions for a possible reactivation. If historical information dominates seismic hazard assessment analysis, hazard values for the next 50 years, for example, commonly used in hazard maps, in building codes, are certainly overestimated in areas affected by recently reactivated seismogenic source, and conversely, underestimated in areas with apparently silent faults without any major seismic record during the historical period. I would say that also this trivial observation likely explains the frequent surprises in the occurrence of recent events. An example already shown by Spiro, but I commonly use, in 1990 was published this map solely based on seismological data, both historical and instrumental, and this map could not predict two major events. In particular, the Kozani 1995 events occurred in an area that was characterized as a rigid aseismic block. Okay, think about it. This is, I would say, the smoking gun that solely historical instrumental information is not sufficient. Now, preliminary conclusion from these premises is that seismic hazard assessment analysis need more, and especially complementary, information to fulfill this gap and to reduce this bias. A few years ago, with my friend Bruno Lee, we reappraised the topic and categorized, grouped the most common and most important sources of information commonly used to study past earthquakes and seismogenic sources. You see here a list of. We could say that earthquakes are certainly complex polyhedric phenomena where each facet of the solid represents a distinct source of information, and each source of information should be approached with the proper tools and methods, the proper assumptions, the proper expertise, being aware of the different resolution and the different degree of uncertainty each of these disciplines could provide. For example, instrumental, historical, archaeoseismological approaches, and earthquake geology. Earthquake geology in its broadest sense, earth sciences, if you want. Now, today I will mix up a little bit these sources of information and discuss their use in other terms with a different perspective, with the aim of contributing to the seismic hazard assessment analysis. In particular, I will focus on how earthquake geology, in its broadest sense, again, I mean earth sciences, could improve our knowledge on seismogenic sources, and hence could contribute to better and more realistically estimate the seismic rates used in seismic hazard analysis. So different sources of information, different approaches, different disciplines, but a common target. That is to say, the recognition of seismogenic sources and their seismotectonic characterization and parameterization. We will see the competition between the different sources of information. These sources of information are commonly organized in databases like this for Italy, GREDES for Greece, EDSF for Europe, and other ones. And they contain as many as possible crucial seismotectonic parameters, geometric ones, kinematic ones, dynamic, chronological ones. So keep in mind this list, because this list is our topic. We have to fill this list of parameters. We have to quantify these parameters. Now I'll recall you the title of this presentation. And as an exercise, the sources of information have been subdivided into two categories. On one side, those providing information related to a specific earthquake, and on the other side, those providing information on the seismogenic source that caused that earthquake, but also past ones. In other terms, single event effects versus cumulative effects have been independently considered and analyzed. It is useless to stress that while single event effects could be approached and analyzed based on different disciplines, like instrumental seismology, historical seismology, earthquake geology, the analysis of cumulative effects could be based solely on earthquake geology, at least in the Mediterranean region. So the exercise was to consider some major past events, both historical and instrumental ones, and the corresponding causal sources in order to quantify the seismotectonic parameters of these sources, okay? To estimate their degree of uncertainty, we consider a quality index, and thus to populate the database according to single event effects and cumulative effects for the different case studies. Obviously, today there is no time to describe and discuss in detail the specific values attributed to each specific seismotectonic parameters for each specific source, nor to estimate each quality index for each single parameter. There's no time, of course. I will just show you very quickly a few examples of the different sources of information used for analyzing the two types of effects and thus defining the preferred values for populating this database. The first one is the most recent, the Kozani event. We have, for example, as a source of information, we have macroseismic maps with their orientation along axis. We can get information about the strike of the fault. We can get information from the density, about the depth, the magnitude, and so on. We have at that time we have obviously instrumental information. So we have instrumental epicenter. Beyond the macroseismic one, we have focal mechanism. We have also ground observations allowing to quantify the displacement, the length of the fault trace. We also have in modeling, better constraining the dimension of the fault, length and width, the distribution of the slip with the maximum slip, the average slip, and so on. In this recent case, we also have dynamic information, nice dynamic information with the distribution of the moment of release on the fault plane, for example. Here we have also geodetic sources of information using, for example, leveling profiles, and with the proper modeling and interpretations, we can get some constraint on the seismotectonic parameters of depth. And in recent times, we have also the new entry of the differential interferometry. And again, here from this information, we can get we can better quantify the seismotectonic parameters, or some of the seismotectonic parameters of the seismogenic source at depth. Next example is the Thessaloniki event. Again, we can have macroseismic fields, get information, as I told you, about the depth, the magnitude, the macroseismic epicenter. We have also the instrumental epicenter. We have also focal mechanism. We also the distribution of the seismicity associated to the major event, both areal distribution and at depth distribution. And as Massimiliano has shown very, very nicely, the cutoff of the depth distribution here in section or cumulatively, the cutoff is a nice proxy of the brittle dotile transition. And with this, we have a good constraint of the down deep dimension of the possible seismogenic sources. So we can constrain some of the tectonic parameters. So also here we have the reconstruction of the slip, so allowing to better constrain the dimension of the fault. We have also mesostructural data or kinematic data independent from ground ruptures, so documenting the direction of the stretching direction and the kinematics of the fault. Next, I'm going quickly. We go back in time, 1954. You see, macroseismic field here is a little bit more debated. It's not so clear. It's not unique, but also in this case we can get anyway some information about the dimension of the fault, the epicenter, macroseismic epicenter. Here we have also in this case a nice interesting descriptions of field observations, documenting, allowing to document the displacement, the fault trace length. And here we have the first, although obtained 20 years later, the first focal mechanism available for, still debated, not well constrained, but some focal mechanisms we can get even 50 years ago, more or less. No much more information for single event effects. The last example is from the Valimitica 1861 event, nice macroseismic field, direction of the long axis of the isoseismals, so some information about the magnitude, the location, and the orientation of the major fault. But we have also nice observation, as Spiros shown, nice observations of the ground ruptures, so we can have, we can constrain somehow the displacement, the length of the fault. No much more anyway. It's obvious if we go even back in time, more back in time, the sources of information become poorer. It's obvious. Now, I will compare the same seismogenic sources, the analysis carried out on the same seismogenic sources, analyzing only cumulative effects, assuming that the four events I've shown you before did not occur yet. I mean, the geologist or the earth scientist altogether went there in the field, analyzed data before the event, okay, without considering the event. What kind of information we can get from this kind of analysis and this kind of approach, earthquake geology approach. Again, the first fall, yeah, good geological, morphotectonic, structural mapping could allow us to map nicely the fault with several segments over steps to characterize whether the segment boundaries are soft segment boundaries or hard segment boundaries. Mesostructural data can provide some information, kinematic information. We can constrain very well the kinematic information, geologically and structurally. Of course, we can carry out paleoseismological trenches, documenting the occurrence of the ultimate, the last, the penultimate, or the third last, and so on, past events. You know, get some information of the slipper per event, get some information or some constraint about the recursive interval for this fault. But we can also use macro seismicity. Okay, forget the seismicity, the aftershock related to the main shock. In every region here, there is some sort of background seismicity, macro seismicity, and again, we can use the cutoff depth in order to constrain the brittle data transition, and so to constrain the down deep dimension of the faults. Now, next example is from Mygdonia Basin, good mapping, several branches with steps, with segments and so on, mesostructural data, mesostructural data documenting the kinematics, also in this case, the distribution at depth of the microseismicity, so documenting again the cutoff depth of this, and also, for example, seismological investigations. Okay, this trench shows the last event, but this trench also shows a previous, a penultimate event that could have been documented even before the 1978 Thessaloniki earthquake. We move to the third example. South Karditsa Plain is bounded by a system of faults, clearly highly segmented. Also, in this case, geological mapping, morphostructural mapping, morphotectonic and structural mapping could allow to document this. To document also morphometric analysis can contribute to document the location of the segments, so the dimension of the segments, and to see if these segment boundaries are soft or hard, or at least tentatively suggest if these segment boundaries are soft or hard ones. We have also in this case microseismicity distribution of depth, so providing information of depth. We have mesostructural data provided the kinematics, different structural data, slicking lines, slicking planes, and so on. We have paleoseismological trenches. We can do as many as we want, and providing information about the seismic history that affected in recent times that seismogenic source. Move to the last example. In the South Corinth, mapping could show clearly the segmentation, east and west the leaky fault. We are in the coastal sector, so we can exploit also based on cumulative effects and earthquake geology approaches. We can also exploit the occurrence of marine terraces in this case. Marine terraces provide uplift rates. Uplift rates can be transformed into throw rates in slip rates. So we can document long-term slip rates of these segments and see their variability, for example. But even in Holocene times, so where the coastal sector is rocky, we can have notches and Holocene notches, so we can document also a shorter uplift, throw, and slip rates. Again, we are in a coastal sector, so we can use seismic reflection profiles. Obviously, we could use also on land, but the example here now shows that it is nice. It is obvious, more obvious for offshore areas to use this kind of earth sciences tool. So we can map better the faults, so we can see the distribution of the deformation, the amount of deformation. We can get some, together with stratigraphy, we can get also some information about the slip rates and long-term slip rates on these faults. We can also exploit microseismicity distribution, constraining in depth the dimension of the fault. Again, and obviously also paleoseismological investigation can provide information about the cumulative effects of along this seismogenic source. So all this information I very briefly, shortly and quickly shown you, could help to populate the database separately for the two types. We investigated separately. I will show you the results separately. Okay, here are the numbers. Forget the numbers. Don't look at the numbers, please. Too many. Just look, if you want, at the letters in parentheses corresponding to the quality index. So I made this screening for you, and emphasizing in blue the value among the two approaches, the value which a better rank. Let's say B versus D, C versus C, and so on. Okay. If we consider the most recently reactivated seismogenic sources, let's say this, Saliakmon and Mygdonia, respectively with Kozani and Thessaloniki events, where recent events, so many different sources of information were available and many tools, I would say that if you look at this, I would say the competition is open. Okay. However, if we go back in time, we consider older events, historical information is getting poorer and instrumental information progressively disappears. Earthquake geology approaches analyzing cumulative effects are clearly more successful and performing. Going farther back in time, it would be even more clear, this disparity. Now, I'm going to conclude, Massimiliano, and I would like to, I told you I didn't want to show you results of data, but just to leave a message. And I would like to emphasize a few points. First, seismic hazard assessment analysis based on seismicity, both instrumental and historical, are certainly biased, at least in the Mediterranean countries. Second, I would suggest a change of paradigm for seismic hazard assessment analysis that should focus more on seismogenic sources and not on past earthquakes, which obviously does not mean that we should neglect the latter, but only we should emphasize the former. Third, and this is an invitation to practitioners of seismic hazard assessment analysis, they should invest more and more on the analysis of cumulative effects based on as many as possible earthquake geology approaches. With geology, I mean earth sciences approaches. Finish saying that I'm sure that if all available sources of information would be properly exploited and historically and geologically based seismic rates would be properly balanced, mixed, the next generation of seismic hazard maps would be more realistic, possibly reducing the seismic surprises and better supporting mitigation policies. Thank you for your attention.
Thank you, Professor Caputo, for your presentation. There are no questions at the moment on the question and answer section and on YouTube. I don't know if anyone wants to ask any last minute question. Otherwise, we can move on. So, okay. I would now ask Professor Caputo to stop the sharing of the screen. So
I'm asking to disappear. Can you?
Okay. Sorry. Very good. So now the next speaker is Professor Hasan Sozbilir from the Quds Elul University of Izmir. here is the title of his presentation is Active Tectonics and Paleoseismology of Seismic Sources Located on Land in the Vicinity of the City of Izmir, Western Anatolia, Turkey. And he will present on behalf of also his colleagues. So now I leave the floor to Professor Sosbilir, and you can go.
Thank you, Massimiliano. First of all, I would like to say welcome to everyone. Sorry. Yeah. Yes. Now I will present you the first results of our study that conducted within the scope of the TÜBİTAK project. This study includes scientists from Dokuzeli University, Afyonkarahisar University, Kansas State University, Ankara University, and Çukurova University. The study area is located at the intersection of the northeast trending İzmir-Balıkesir transfer zone and east-west trending Gediz-Graben and Küçük-Menderes-Graben, and resulted in a very complex structural pattern in that area. As you know, from the Samos earthquake, the Samos fault was ruptured, and the destruction site of the Samos earthquake was in our city, near Bayraklı district, 70 kilometers from the epicenter. So what about the historical earthquake, which fault caused to this earthquake, we don't know. So this is the first paleoseismological result that conducted on the Tuzla fault, İzmir fault, Seferihisar fault, Yağcılar fault, and Gülbahçe fault. The question is, what are the seismic sources of this historical earthquake that occurred around the city of Izmir? I mean, which fault is responsible for which historical earthquake? To solve this problem, first of all, we worked on the regional geology and tectonic setting of the area. Then we create a local earthquake catalog for Izmir city by using national and international original resources and earthquake catalog. Then
so
we
you share the screen.
Sorry.
You share the screen, yeah.
Don't share.
That's fine now. That's fine. Full screen, please.
Yeah. Sorry. You hear me?
Yes. Carry on, please. Yeah.
Okay. Let me show you. You see the first slide now?
Yes, yes, you can see it. Yeah.
I repeat this slide only. The study area is located within the intersection of the İzmir-Balıkesir transfer zone with the Gediz-Graben and Küçük-Menderes-Graben, and here there are a number of faults that oriented east-west or northeast or northwest trending stochastic faults, and the area has a very complicated structural pattern due to the transfer zone and the graben structures. Here is this main problem is which fault is responsible for historical earthquake in that area. To solve this problem, we study on the regional geology and tectonic cycle of the area, and we create a local earthquake catalog for Izmir city by using national and international earthquake catalog. Then we made field geological studies for mapping the fault zone that we worked on, and then we used geomorphological markers by using a photograph and satellite images to find suitable trend site for paleoseismological purposes. And we use optiluminescence and radiocarbon dating to date the event in the trenches, and to determine number of events, we use observe program and compare the result with the historical earthquake that developed in the region. And finally, we want to know which fault will be ruptured in the near future around Izmir city. Here is the brief description about the regional geology and tectonic setting of the area. As you see from these figures, we can say that Izmir-Balıkesir transfer zone has a very important role since late occupations in the region. It acted as a transform fault during the Neolithic closure, and then later in the Miocene acted as a transfer fault that divided the different extended terrain in the west, the Tectonic Massif, and in the east, the Menderes Massif. And during the Pliocene, when the North Anatolian faults came to Western Anatolia, the area is characterized by strike-slip dominated critical shear zone. And today, this fault pattern is also continued to create moderate size earthquake. The most important one is the 1992 Doğan Bay earthquake that occurred on the Tuzla Fault with magnitude of 6.0, and 2003 earthquake, Urla earthquake on the Seferihisar Fault, also a right lateral strike slip fault, and the last one during the 2005 Sağcı Bay earthquake with magnitude of 5.9. As you see, no destructive earthquake can be found during the instrumental period, except for the Samos earthquake. However, historical seismicity has not been studied by means of the paleoseismological purposes. To fill in this gap, we study a combined paleoseismological analysis of Tuzla Fault, İzmir Fault, Seferihisar Fault, Yağcılar Fault, and Gülbahçe Fault, and to know seismic hazard of the region. Here is the collected nation and national catalogs. There are 4 to 5 historical earthquakes that play important role during the historical period. The first one is the 178 earthquake that developed on the near Izmir Fault, or can be observed on the Tuzla Fault. The other is 688 earthquake. It's also close to Izmir Fault. And as you see, most of the historical earthquake is shown on the Izmir Fault, or close to Izmir Fault, or on the Tuzla Fault. So to study on this fault by means of paleoseismology is very important. Let us give you a brief description about this fault. Izmir Fault is a 35 kilometer long east-west trending deep-sea normal faults that border morphologically the Izmir Bay from the south and merge with the Seferihisar Fault. The Seferihisar Fault is a northeast-southwest trending strike-slip fault that continue toward the Sağcı Bay, and here is the Gülbahçe Fault and Yağcılar Fault. Is also forms the structural boundary between Urla Basin and Karaburun Peninsula. All of the fault is Holocene fault, except its Holocene fault with respect to Turkish active fault map of Turkish. Here's the paleoseismological studies we conducted on the Izmir Fault. We opened 2 trenches on the Izmir Fault, first on the Balçova segment and the other on the Pınarbaşı segment. Here you see on this photograph the Holocene phase of the fault, and here is the open trench on this trace. It is the Balçova trench walls and trench logs. As you can see from this trench, data, we can say that there are 4 events that develop on the Balchova segment, and it is the 2 events that develop on the Pernambuco segment. However, we cannot find any data about the corrosion activity on the Pernambuco segment. 2 of the event is Pleistocene in age. When we put data to timing past earthquake occurred on this fault, we can say that the most recent earthquake on this fault was generated between 1980 BC and 180 BC. As you know, the most known earthquake in Izmir region was the 1688 earthquake. Seismicity map created by us for 1688 earthquake. We can say that this fault is caused by the Izmir fault. However, we cannot find any data on the Balchova trenches because of this trench is very close to the footwall. Here is the surface structure of the 1688 earthquake. Here is the trenches on the Seferisar fault. As you see, we opened 3 trenches, one near Ulamış and the other near Çamlı and Belki villages. As you see on the field photographs, we can say that the Seferisar fault has a stratigraphic character, stratigraphic character, and cut Pleistocene alluvial fan deposit. And here is the one trench opened on the Seferisar fault that's separating Borneo melange from the Guatemala and alluvial fan deposits. Here is the Çamlı and the Belki trenches. As you see in these trenches, we cannot find several events. Only one event can be found here, and this can be dated to 4,000 years ago. And here is the Ulamış trenches that we opened parallel to each other, and we can see here 2 events can be developed during the Holocene, and the other developed during the Pleistocene. And here is the Tuzla fault. Tuzla fault consists of 3 fault segments from the south to north. These are the Doğan Bey segment, Orhanlı segment, and Çatalca segment. We opened on this segment each trenches, and you see the field photographs from the Tuzla fault zone. As you see, second-sided fault can very well developed and strikes the character of the fault. Here is the Çatalca and Yeniköy trenches. When you see the Çatalca trenches, we can say that there are 2 events can be defined on these trenches, and on the Yeniköy trenches also 2 events were defined, and the last event is corresponding to the 1070 years ago. And here is the third trench on the Tuzla fault. Also here we find 3 events. First one is here, and the second one is here, and the third one can be found as a polyar wedge at the top of the units. When we see about the timing of the past earthquake occurred on Tuzla fault, we can say that the 178 earthquake was caused by the Tuzla fault. This is very important for the region. And here is the Yağcılar fault. As I said, I did mention to you before, Yağcılar fault is 12 kilometers long and also right at lateral successive faults. And when we look at in the field, we can see that oblique 2 strikes the character of the fault. We opened also 3 trenches in the middle part of the fault, and the first trench is opened on the fault band, where is the oblique steep dominant. We can see here that 2 polyval packages on each other. The older one is Pleistocene in age, and the younger one is Holocene in age. And there are 5 polyval wedge representing 5 events in the Yajalar trenches. And the other trenches on the Yajalar fault, we can see that nearly vertical Miocene units covered unconformably by the Holocene unit, is the base of the Holocene unit, represented by a paleosol, and cut by the display of the Yajalar fault. Here we found 2 events during the Holocene. And here is the last trench on the Yajalar fault. As you can see, there are very small neck here, and when you look at the fault branch, you can see say that there are negative flow structure that developed on this fault. Here we see 3 events that form during the Pleistocene. And here we can say that the Yajalar fault was caused by 1040 earthquakes during the historical period. And the last one is the Gülbahçe fault zone. It is characterized by north-south trending faults and bifurcate into 3 splays toward the north, forming new negative flow structures in the Gülbahçe group. And when we look at the fault on the fault, you can see a very high fault scarp that are during the fault. And here is the middle branch of the fault, and shear. And you see a very wide deformation zone developed across the fault, and some splays is very close to the surface, representing 4 events that developed on this branch. And here is the eastern and western branch. On the eastern branch, we can see that 4 polyval wedge that indicate 4 events for the eastern branch and 3 events in the western branch. When we made timing of past earthquake on the Gülbahçe fault zone, we can say that 1389 earthquake was developed on the Gülbahçe fault zone. Here, as you see, we create an isostatic map for 1389 earthquake by using intensity catalogs. And as you see, most of the destruction was here around the Gülbahçe fault zone. And we can say that the Gülbahçe fault zone was responsible for the 1389 earthquake. And here is the conclusion. In this study, French-based paleontological studies were carried out on İzmir fault, Tuzla fault, Gülbahçe fault, Seferistar fault, and Yajalar fault, which they are present for the İzmir city center. We opened 14 trenches on this fault to know earthquake recurrence interval and elapsed time since the recent earthquake for each fault segment. Our findings indicate that historic earthquake that occurred in the region in 178 and 1040 and 1389 and 1688 were generated by Tuzla fault, Yajalar fault, Gülbahçe fault, and İzmir fault, respectively. These results show that the investigated faults produce earthquakes in such a way that they trigger one another, and that on average there is a devastating earthquake in the region every 300 years. Considering that the last destructive earthquake in the region occurred in 1688 it is highly likely that a devastating earthquake will occur in the city of Izmir in the near future. When we look at the earthquake recurrence interval, as an average, we can say for Izmir fault, 2075, and for Tuzla fault, 1098, and for Yağcılar fault, 2200 year, and for the Bahçe fault, 4400 year, and for Seferihisar fault, 3100 year. With respect to these results, we can say that Tuzla segment is have seismic risk in the near future. Yes, this is the first paleoseismological result obtained on this fault. So 14, and this is very limited for to study this fault because we can open 3 or 2 trenches along this fault. So we should much more open trenches on this fault. Thanks for your attention.
Thank you very much, Professor Sosbilir. There are a couple of questions from Tariq Ilan, and I will just read them to you from the question and answer section. He says, after the October 2020 earthquake, our citizens who want to learn about the earthquake risk of their apartments in its mere districts where earthquake damage occurred, say that different prices are given from private companies and authorized university professor. In this situation, does the Earthquake Research and Application Center provide foresight and savings? And then I will read the second. I don't know if you can read it yourself from the question and answer section, because it's quite long actually, and I don't know if it's strictly related to the presentation, however.
I cannot understand what they mean. So
then the second question is you said that after the 4.3 and 4.2 earthquakes in Menderes yesterday, the Gumuldur fault could create an earthquake of 6.8 magnitude. What is the source of this guess?
Yes, this question is not related to this presentation.
Okay, say that.
Massimiliano would like to make a question.
Okay.
Dr. Sosbilir, thanks for the presentation. I would like to have your opinion about the geometric and kinematic connection of this of the Izmir-Balıkesir transfer zone, mainly transparent, with the east-west trending deep slip normal faults like the Büyük Menderes, Küçük Menderes, the Kemal Pasha faults, and other faults, which is their kinematic and geometric relationship.
Yes. Can you see the figure?
Yeah.
Yeah. As you see, here is the normal fault of the Gedizgraben. As you can see, contain up to Manisa fault. Here is the Kemal Pasha fault, continue toward the west and merge with the northeast trending Seismicity fault. And also for Gümüldür fault, as you can follow Gümüldür fault, and then it merge with the Tuzla fault. Geometrically, all of the northwest east-west trending fault is related to the northeast trending fault. And when we look at when we study on the kinematic analysis of this fault, we can see that most of them in that area is characterized by pure extension, and here is most of them is characterized by transtensional tectonics, mostly dominated by Seismicity faults, and normal faults. So these two faults has the same age, and during the same tectonic setting that they developed. So regionally there is a north-south extension. However, in Izmir area, most of them are in strike steep character. So we can say that the area here is dominated by strike steep tectonics and here by extension tectonics.
Do these faults have a connection with the northeast southwest trending faults northeast of the Geddes Graben, Alashair detachment? You know, the old faults modeled by Jalal Shangor and with the double extension. Are they inherited as well, but active in this case?
Yes, if we say something about detachment fault, we should look at a big picture because Geddes detachment fault is a very long fault for Western Anatolia, cut through Western Anatolia in east-west direction, and it has a big prolongation, northeast prolongation that may form Gördes, Demirci, and Selendi Basin during the Miocene. But today, the detachment fault on the surface we can map it was not active. Most of them cut by high angle normal faults, and most of the fault has migration toward the basin. The most active fault in the between the quaternary alluvium and Miocene, and the older one is on the Ozda mountain. So we can say that today, recently, or most of the fault is high angle normal fault, cut and displaced the detachment fault, and the some configuration that was began during the Miocene is replaced and cut by quaternary tectonics. I mean, in the area, quaternary tectonics is different from the Miocene tectonics because of the North Anatolian fault came to the Western Anatolia during the Pliocene and onward.
Thank you.
Okay, thank you, Professor Sozbilir. You can now, if there are no other questions, I think we can now move on. So you could stop sharing your screen. And thank you again. Okay, so now the next speaker is Dr. Spiridon Mavroulis from National and Kapodistan University of Athens, and he will present also on behalf of his colleagues the presentation with the title Multi-Hazard Approach in Managing Earthquake Emergencies Amid the Evolving Biological Hazards, Lessons from the 2020 Samos Eastern Aegean Earthquake Amid the COVID-19 Pandemics. So I will now leave the floor to Dr. Mavroulis. Okay, we can see it. Good.
Okay. Good morning, everyone. I'm Spiros Mavroulis from the University of Athens. I'm going to present you the multi-hazard approach in managing earthquake emergencies amid evolving biological hazards and the lessons learned from the 2020 Samos earthquake amid the COVID pandemic. This is a collaboration of the Department of Geology and Geoenvironment of the University of Athens with the Earthquake Planning and Protection Organization of Greece and the Department of Microbiology of the Medical School of the University of Athens. Samos earthquake is the event with the largest magnitude in Greece in general and the Aegean Sea in particular for the last 52 years. The last destructive earthquake happened on 1968 in Agios Efstratios Island with moment magnitude 7.1. The Samos earthquake was the largest event in Europe and Turkey in 2020 and the most lethal event worldwide as it resulted in 119 fatalities in total, 117 in Turkey and 2 in Greece, from attributed to partial or total building collapse. Moreover, it is the largest earthquake in Greece since the initiation of the COVID-19 pandemic. A few words from the pandemic in Greece. The novel virus knocked the door of Greece on late February 2020. The first national lockdown was imposed on March 23, taking into account the low numbers of the daily cases in the following period. Activities were gradually reopened from the early May to early July of the same year. The second wave started. The second wave of the pandemic started on August 2020, and the second national lockdown was imposed in November after a gradual increase of patients and fatalities. The national lockdown was imposed 6 days after the generation of the Samos earthquake and the subsequent tsunami. And nowadays we are on the middle of the third wave in Greece with the largest numbers of cases, patients and related fatalities from the onset of the pandemic. The emergency response actions after the Samos earthquake occurrence comprise initial notification of the earthquake alerts and announcements, guidelines through 112 emergency communication service, first assessment of the impact and mobilization and response of the state authorities, search and rescue operations, first aid treatment and medical care, psychological support for the affected population, hazard mitigation in the affected area, raising awareness and education for the earthquake effects and protective measures due to the continuous aftershock sequence, provision of essential emergency supplies and emergency shelters, as well as procedures of housing restoration during the post-disaster period, and immediate financial relief measures for the affected population. The multi-hazard approach and management of the Samos earthquake and its related phenomena amid the pandemic was a challenge for all involved in the scientific community and the civil protection personnel. This challenge arose from the finding that many emergency response actions require direct communication with the local population, contact and interaction in the disaster-affected area. The observed incompatibility between the emergency response actions and the pandemic mitigation measures made the Samos disaster management look like a puzzle with many pieces, different colors to match and solve. The first contradicting issue in the emergency response phase is related to the first reactions of the local population when earthquake strikes. Residents rush out onto the streets and gather either in assembly points or in open spaces away from the adverse earthquake effects. The gathering and overcrowding at assembly points is incompatible with the COVID pandemic mitigation measures, and there is a direct contradiction between overcrowding and maintenance of physical distancing. As regards the second contradicting issue is related to the mobilization of civil protection staff and setup of operation coordination centers. Civil protection staff should be on time in the earthquake-affected area in order to implement the emergency response actions plan. The operation coordination centers in the pre-pandemic era were established indoor sites specially designed for accommodating many people for many hours, and the coordinating meetings take place usually indoors in unaffected buildings with the participation of civil protection staff involved in disaster management. Amid the COVID-19 pandemic, these meetings should be avoided as many people gather indoors for several hours without a break, which constitutes an ideal condition for the transmission of the novel virus among participants and then in the affected community. The next contradicting issue is related to the search and rescue operations. which comprise a relocation of rescue teams from different areas with different viral loads and different infection rates, interaction with the affected local population, cooperation of many teams from different affected areas with different viral load and infection rates, and use of many tools and equipment by many members of the rescue teams. All these actions pose a higher risk for transmission, not only in the community, but also among the members of the rescue teams due to the fact that the movements during the pandemic are restricted and personal hygiene measures, including regular cleaning and disinfections of items, of hands, tools, items, and equipment, must be applied. The next contradicting issue in the emergency response shelters is the provision of temporary accommodation in emergency shelters. In the pre-pandemic era, the gathering of many people in emergency shelters can lead to COVID clusters and outbreaks, which can affect to infectious diseases outbreaks and clusters that can affect not only those accommodating the emergency shelters, but also those contribute to the operation of these facilities. This risk is even higher, greater in overcrowded emergency shelters amid the pandemic, as the coexistence of many people in a place over a long period of time is incompatible with the pandemic mitigation measures. As regards the contribution of volunteers during the emergency response, they contribute in a lot of actions in the emergency phase and interact with many people and for many hours. Prior to the pandemic, their activity did not pose a risk to public health. Amid the pandemic, the majority of actions conducted by volunteers is incompatible to the preventive measures, comprising maintenance of physical distance, regularly cleaning and disinfecting hands, and avoiding exchanging items and using common equipment. The next issue has to do with the donation of emergency supplies to the affected population. Until now, when a major earthquake struck with considerable impact in an affected area on people, buildings, and infrastructures, people from around the country and worldwide are mobilized in order to donate essential emergency supplies to the affected population. This nationwide mobilization in the pre-pandemic period constitutes a strong message of solidarity and hope to the affected population. However, amid the pandemic, the whole process, from the first phase of the collection of emergency supplies to the final step of the distribution to the affected population, involves a risk for the public health due to touching and sharing undisinfected products with unwashed or unsanitized hands. The next contradicting issue is related to the hazard mitigation in the earthquake-affected area. Among others, the most important thing is the evacuation of the population from severely affected parts of the affected area. This action poses higher risk of spreading the virus in the community, as the interaction with the local population is required, starting from the announcement of the evacuation to residents until their final transfer to temporary emergency shelters. This process comprises actions that are incompatible with the many pandemic mitigation measures. Another one contradicting issue has to do with the psychological support provided to the affected people. It comprises support and counseling sessions provided by mental health professionals from public health services, as well as by volunteers with similar specialized knowledge and expertise. Prior to the pandemic, these activities were carried out in person and indoors with the presence of both mental health professionals and the affected people. Amid the pandemic, these sessions pose a risk of spreading the virus among participants and then in the community. Another issue is the raising awareness and education activities on the earthquake effects and the protective measures. These activities include seminars which take place indoors in educational facilities, properly designed to accommodate many people for many hours and with appropriate equipment for displaying educational material. Amid the pandemic, these actions should not be carried out indoors, as the physical distance between participants cannot be maintained, and they can contribute to further spread of the novel virus among the participants and then in the affected community. In order to effectively deal with both hazards, the geological hazard of the earthquake and the tsunami and the biological hazard of the evolving COVID-19 pandemic, the measures of the emergency response had to be adapted to the new conditions formed by the collision of the Samos earthquake and the emergency and the evolving pandemic. As regards the mobilization of civil protection authorities, the following measures were taken. 2 exclusive flights operated by civil protection transported all the required personnel a few hours after the earthquake. All the necessary safety measures were taken during these flights, masks throughout the whole journey, 1 person sitting in each seat row, hand sanitizers available everywhere. Moreover, application of preventive measures comprising mandatory mask wearing, hand washing, and maintaining physical distances during interaction with local population and authorities. As regards the search and rescue operations, the measures included keep physical distance from the local population when possible, mandatory use of masks not only indoors but also outdoors, frequent use of antiseptics, and disinfection of equipment and tools used by many people. As regards the provision of temporary accommodation in emergency shelters, different types of emergency shelters were used, comprising hotels, tourist facilities, cars, vans, and container-type shelters. More emergency shelters with military-type tents were organized outdoors. Isolation facilities were designated in the emergency shelters in order to isolate suspected COVID cases. As regards the provision of basic necessities and emergency supplies, the modification of food distribution process in the emergency shelters was considered mandatory amid the pandemic. In the pre-pandemic period, food in emergency shelters were served buffet style and self-service, but now meals were packaged and served by staff which wore masks and disposable gloves throughout the preparation and the distribution of the meals and the emergency supplies. Similar modifications were also applied in the provision of emergency supplies from individuals and voluntary teams. Regarding the hazard mitigation and the building inspections, information activities were carried out for participants in civil engineer teams in open or closed spaces with adequate ventilation in the affected Samos. The appropriate physical distances between the participants were maintained. Moreover, building damage documentation centers were set up in open spaces. In these centers, especially during the first hours and days of the emergency, it was impossible to maintain physical distance due to the fact that many residents gathered to report building and property damage. In this case, the use of masks and hand sanitizers was vital. The psychological support amid the pandemic was provided by remote communication via teleconference or video conference. In case of in-person meetings, wearing masks and giving the appropriate physical distance was mandatory indoors and outdoors. As regards the raising awareness and education activities, they were conducted by the staff of the Earthquake Planning and Protection Organization of Greece for certain population groups. They were held outdoors where the protection measures, including maintenance of physical distance and wearing masks could be applied. They provided information, including training and guidelines, not only for the protection by the aftershock period, during the aftershock period, but also from the further transmission of the novel virus. Moreover, the coordination, as regards the coordination of the civil protection authorities, the emergency operation centers were set up outdoors and all protective measures, including masks, hand sanitizers, and disposable gloves were applied and available for both the affected people and the civil protection authorities. In addition, food supplies, including bottled water and packaged food, were also immediately available and distributed to those in need by complying all precautions against COVID-19. After these measures adopted during the emergency response phase in Samos affected area, we present the study on the evolution of the COVID-19 pandemic in the earthquake-affected North Aegean region. We based on laboratory confirmed and daily recorded COVID-19 cases from the National Public Health Organization of Greece for the regional unit of for the affected regional units of the North Aegean region. This is Samos, Ikaria, and Chios regional unit. We took into account that the estimated incubation period of the SARS-CoV-2 ranges from 2 to 14 days. The median incubation time is 5 days, and SARS-CoV-2 was detected up to 21 days after onset of symptoms by PCR in infected patients. We studied the daily cases 1 week before the earthquake and 3 weeks following the earthquake. First, for the Samos regional unit, 7 confirmed cases were reported during the selected pre-earthquake period, while 12 cases were reported after the earthquake period. They could all be attributed to the adverse effects generated by the earthquake. In Ikaria regional unit, only 1 case was reported during the selected pre-earthquake period, while no case was recorded after the selected post-earthquake period. And for Chios regional unit, 86 cases were reported before the earthquake, the week before the earthquake, and 68 cases were recorded during the selected post-earthquake period during the 3 weeks after the following the earthquake. Based on the post-disaster trends and the factors affecting the evolution of the COVID-19 pandemic in the earthquake-affected North Aegean region, it is concluded that the impact of the Samos earthquake on the pandemic evolution was low. This impact is strongly related to the pre-existing low viral load in the disaster-affected regional units, to the measures adopted by the responders to protect themselves and the disaster-affected population during the first hours and days of the emergency response, to measures adopted by the authorities involved in disaster management for the immediate housing of the affected population, and more specifically of homeless people, to the intensity of the studied events and their effects on the local population, on the natural environment and on the built environment, and to the ease of access before the disaster and the accessibility to the affected area after the disaster. In conclusion, there was no burden on the viral load and the infection rate in the affected area, so we consider these measures adopted by the involved authorities as a good practice and an important lesson learned for the management of a natural hazard and related disaster amid an involving biological hazard. These measures can also be adopted in other areas with similar environmental and epidemiological characteristics. Thank you.
Okay, thank you, Dr. Mavroulis, for your presentation. At the moment, there are no questions in the question and answer section, so I don't know if anyone wants to ask any last-minute question, or otherwise we finish this session.
Okay, the next session will start at 2 o'clock in the afternoon, and Ricardo will chair the session. So see you at 2 o'clock in the afternoon.
2 o'clock Greek and Turkish time, 1 o'clock Italian time.
That's right. Okay, you know that. Okay, thanks, Ricardo.
Thanks to you.
See you at 1 o'clock in the Italian time.
Okay.
See you later.
Bye-bye.
See you later.
Thank you. Thank you, Massimiliano. Hi, Dr. Margaris.
Hello, how are you?
Thanks very much. Nice to see you online. Yeah, I think
you managed to share your screen?
Sorry?
Did you manage to share your screen?
Yes, everything is okay, yes.
Okay, that's fine.
I just have a call from Professor Caputo. Everything is fine.
That's great. That's great.
It is 5 minutes to 5 o'clock, so we wait for the audience.
Yeah, just.
run?
Yes, Ricardo.
I would like to say, to remind to all participants about questions before starting. If they have some questions to the speakers, they should use the chat in Zoom, which is in the bar below. Okay, they use the chat, or if they are connected with YouTube, they should use the small window on the right, similar to the chat.
Well,
I will read to the speakers the questions.
They can also use the Q&A section, Q&A button.
Yeah, they can also use this.
On the Zoom application, yeah, okay.
Okay.
Yes, I think we can start now, yeah?
We can start, yes, yes. Now we enter we make this section, this afternoon section is focusing on the Samos 2020, October 2020 Samos earthquake. There will be first four presentations first, and after the coffee break, other four presentations focusing specifically on the earthquake. The first presentation is by Sotiriadis and colleagues, but will present Dr. Margaris, analysis of strong ground motion data recorded in Greece during the Samos Island earthquake MW 7.0. Dr. Margaris.
Thank you very much, Professor Caputo. Also, at the beginning, I would like to to acknowledge also Professor Orhan Tatar for this invitation, participating in this very interesting workshop. Also, Professor Spiros Pavlidis for the same reason. And of course, many thanks are to my co-authors, colleagues from various research organizations in Greece contributing to this work. Can I share the screen, Professor
Yes.
Caputo? Okay,
Yes,
thank you very
yes.
much. Thank you very much. Okay, can you see my
Yes,
screen?
perfectly, thanks.
Perfect, thank you. I'll try to also to use a kind of laser pointer. Fine. This work have been done just after the strong earthquake occurred in Samos Island, close to the Samos Island, magnitude 7. And in this part, 4 different universities and research institutes have participated: Democritus University of Thrace, Civil Engineering Department, University of Patras Geological Department, National Observatory of Athens Geodynamic Institute, and my organization, Institute of Engineering, Seismology, Earthquake Engineering in Thessaloniki. In the next slides also, it would be a great omission not mentioning a coordinated project by 4 international associations and research organizations in order to create a technical report within the framework of this seismic activity and the aftershock studies. The organizations are the Hellenic Association of Earthquake Engineering, Earthquake Engineering Association of Turkey, Earthquake Foundation of Turkey, Earthquake Engineering Research Institute of University, USA, and the Geotechnical Extreme Events Reconnaissance Association, creating a very comprehensive technical report with the number 069. Parallel to this, my group and also some distinguishing professors from different universities in Turkey, Professor Sinan Akar, Bogazici University, and Professors Ayşegül Askan and Zeynep Gülerce from METU. We had the coordination of chapter 3 in this technical report. So all the parts of this presentation, of this talk, is from this chapter, and I will try to give our activities from the Greek side. The main topics in this presentation is at the beginning, I'll try to describe you the two strong motion networks and what kind of sensors we use for recording the strong motion, the strong ground motion. Also, I'll try to give you an idea about the detectability of the Greek strong motion networks, especially and focusing for Samos 2020 earthquake. Also, I'll try to emphasize in the recorded strong ground motion in the near field, quite important for the engineering community and of course for the other specialities of engineers in order to repair any casualties, any fatalities in the epicentral area. And finally, I'll give you the evaluation of the ground motion predictive models applicable in the Greece or worldwide versus the observed data. In the first slides, we can see that in this map there are the two strong motion networks. With the black triangles are the instruments belonging to National Observatory of Athens, Geodynamic Institute, and with the white triangles, the instruments belonging to my institute, covering quite enough the mainland of Greece. But you can understand that the problem with the seaside is that we cannot install instrument at the bottom of the Aegean or in this extensive area of sea. In the next slides now, I'll try to give you an idea about the real evolution of our strong motion networks. So with the two different colors, the red color depicts the real-time stations 24-bit recording systems, and mostly continuous recording that send immediately the strong motion recording to our organizations. And with the black triangles, all generation low resolution sensors that mainly are trigger mode instruments. And so now using a kind of telemetry, we can transfer also the data in our organizations. In the third this map, I'll try to focus in our area. So in October 30, 2020, Samos main shock was recorded by numerous recording stations located at the epicentral area up to 600 kilometers. The broader area around the epicenter is characterized by the continental part of Asia Minor to the east and to the Aegean Sea to the west. 11 strong motion instruments located in a distance from the epicenter up to 200 kilometers. The two cycles they have a different radius, 100 kilometers and 200 kilometers. And we use this to demonstrate, let's say, a recording acceleration time histories for amplitude spectra, response spectra, 5% damping response spectra. The two stations close to the epicenter, located at the Samos Island. One is operated by my organization, and the other from National Observatory of Athens Geodynamic Institute. Another subset from 9 stations utilized for the evaluation of the strong ground motion values in comparison with the set of ground motion, empirical ground motion predictive equations we use in this analysis. Parallel to this, I would like also to mention that in order to present more adequate comparison between empirical predictions and data from and observed data, I will use also data from the Turkish strong motion network AFAD in collaboration with my colleagues, as I mentioned before. Now focusing at the in our area, in the epicentral area, We can see that according to the preliminary simplified source model proposed in this report by Cetin et al. 2020, both stations are within distance of one source dimension of and on the footwall side of the causative normal fault. In addition to this, spatial distribution of the two stations to the stations in Evathi, Samos Island, the capital city, located in this area, and you can see the two orientations. The two stations are not located far away, but they have, as you can see, quite different site characterizations based on VS30 velocities. The red one is almost in a very stiff soil, and the other one is in intermediate stiff or maybe stiff or soft soil. Both measurements have been done by Professor Pelekis from Patras University, and also both buildings are public buildings in order to have free connection with the internet. And unfortunately is not the latest generation instruments, and they have not absolute timing, but they have a kind of timing code in order to recognize the event one from the other. What can we do with the data? Basic processing with the strong motion data in order to prepare them for the engineers and for the other specialities is to make a kind of detrading of the strong motion recordings. Also with the visual inspection for glitches and other non-standard errors and appropriated corrections where they were necessary. And finally, filtering to suppress noise and to ensure proper integration of the original acceleration signal to displacement from acceleration, velocity, and displacement as well. We follow our latest work based on our Greek database and our recent work published in seismological research letters just a month ago. So the visual screening to identify records with non-standard errors that should be screened out, not used, or should be subjected to a specific treatment by subsequent processing. Also, a windowing of the records, it is necessary to identify the time intervals containing the acceleration traces. And finally, mean removal and low-cut filtering to reduce noise, any kind of noise effects. Visual screening of the accelerograms is applied to find out records with malfunctions, with low resolutions, and so on. And the component windowing is used to capture the time interval containing a measurable signal from the event, including multiple events at the same time. After the screening and the windowing application, the mean over of the pre-event portion of the record, if existed, or the mean over the whole record length, if pre-event portion does not exist, was removed, and a low-cut filtering procedure is applied. Some notes, many strong motion stations in Greece uninstalled, as I told you, in a public building, are orientated with the respect to the building, especially the older generation of those instruments. The new one, they can orientate it to the north and of course, or to the east-west. And few, but all generation instruments lack of accurate time code, as I told you, for the case of Samos Vathi city. Now, in this transparency, and also in the same acceleration time histories for the two stations in the epicentral area in the Vathi city, Fourier amplitude spectra for the three components, and also 5% acceleration response spectra are compared with the design spectra from previous versions of the Greek National Building Codes or Eurocode 8. And you can see that in this particular case, we have a kind of having greater values from the design codes for this specific earthquake. Also, peak ground motion amplitudes, significant duration, areas, intensities, Hausner intensity, and some other energetic characteristics of the motions have been calculated in Cetin et al. 2020 technical report, and you can find it in the internet. The same for the next station in the epicentral area. You can see also is 18-bit ETNA instrument triggering mode, oriented along the building axis, taking into account the long axis of the building. The VS measurement, the site characterization of the station, the PGA and the component recorded this peak value. And finally, for this, we also plotted some particle motion plots in order to see the displacement motion close to the epicenter and mainly close to the recording stations. Now, moving after collecting all the data, I have presented in my presentation only the two epicentral stations in order to save time. And now I'll try to give you an idea using all the data from Greece and Turkey as well, thanking also the Turkish colleagues for this collaboration again. And in this, we can see that the characteristics of the recording stations. You can see that some very, very simple results is we have the main classified, the main site classes that we have all the recordings are concentrated between class C and B according to INI 98.1. Moreover, taking into account the distance metric, majority of the data were recorded at distances greater than to 50 kilometers. So that means we have a lack of data in the near field, places due to the scarcity of the strong motion instruments. So using this and having almost 77 instruments, 66 from the Turkish acceleropographic network and 11, as I told you, from the Greek. I'll try to give you an idea about the evaluation of the distance attenuation in terms of ground motion predictive models. For this reason, we use three different empirical predictive relationships. One is the latest one deriving in the area of Greece for shallow earthquakes, a project which is completed under the supervision of Dr. Boer and Jonathan Stewart from USA. And the ground motion predictive model and the database for this, for the horizontal component, we calculated, we use peak ground acceleration, velocity, and also 5% damped pseudo acceleration response spectra for 105 different periods. So some specific effects related to the rapid attenuation or the wicked magnitude scaling of the Greek motion that are not captured in the global ground motion predictive models were captured, modify this specific relation using a kind of a bias factor. So this bias factor, can you see the difference between the ground motion predictive equation with and without bias factor. Blue line is without and red line is with a bias factor. Also, we use another worldwide ground motion predictive model from Boer, Seihan, Stewart, and Atkinson in 2014. 14. And you can see also the data that is separated, taking into account the site characterization for each stations. So stations with a VS30 less than 360 meters per second are in blue markers, and with greater values with the red markers. Finally, we use, in order to have a kind of comparison with the previous comparisons and previous ground motion predictive equations, we use a Greek relation proposed by Skarlatoudis et al. In 2003. So you can see that the two latest ground motion predictive equations are predict very well the observed data, instead of the third one that is not so available now for taking into account all the attenuations, inelastic attenuation, or maybe the geometrical spreading and so on. Now the same results for the two five damped pseudo acceleration spectral values for two periods, 0.2 and 1, and also the same comparisons for the Buretal 2021, and also BSSA 14 also for the worldwide data set. You can see that for the higher periods, the data have a very huge deviations just after 80 kilometers. And of course, you can observe the lack of data in the near field. Finally, just before the concluding, some residual analysis, taking into account the GMROT 50 for the two horizontal components observed data, minus the ground motion predictive models media it's estimated. We use the same ground motion predictive equations. You can see that we have a huge deviation in the distances close up to 50 kilometers. And for the rest of the distances, we can see that we have the data are in a good agreement. Also for the same, we can observe also for the preliminary residual analysis for 5% damped pseudo acceleration values. And this is, I think, just before closing, we can find all this data in at the beginning in the European Integrated Data Archive ADA in this website address. Also in ITSAC website address with this in this address, and also in the National Observatory of Athens Institute of Geodynamics, and some conclusions. Great scarcity of the strong motion data, and we need some densification of the strong motion network is quite indispensable. Distance attenuation of BSSA 14 low Q regions and Buretal 21 models is consistent with the recorded data for the Samos earthquake. Also proportional results and conclusions using the residual analysis. And finally, residual effects control the ground motion attenuation towards long source-to-site distances. And in this point, I would like to close. Thank you very much, Professor Caputo. I hope to be in my time. Thank you.
Thank you a lot for your time. We have time for questions, if any. I don't see in the chat nothing. No, interesting, good data, dense data are always important.
Yes.
Okay. No questions? If there are no questions, I would like to move to the second. We are in time, yes. I remind to everybody here, to the participants, if they want to make some questions, to chat either in the Zoom window and using the Zoom button, or in YouTube. And so I'm going to present the second of this session. This presentation of this session is made by Recep Çakır and colleagues. Rapid damage assessment in and around the city of Izmir by using NASA area damage proxy maps. Case study for the 30 October 2020 Samos earthquake. Dr. Çakır, you have...
Yeah, so thank you for the organization committee and then Dr. Caputo. And I'm joining this workshop from United States, Washington State, and it's 4:30 a.m. around here. Anyway, so I'm going to present this rapid damage assessments around the city of Izmir we experienced during the right after the main shock of 30 October 2020 magnitude 6.9 Samos earthquake. Okay, so the earthquake location, and this is the yellow box, is the mostly affected by this earthquake. And here's the small thing showing that small picture, the regional tectonics in Hellenic Arc, in Cyprus Arc, and then Northern Anatolian Fault, and then going to the westward direction, and then speeding up here the abductions of those Hellenic Arc. So in the even this earthquake, we knew I was in the calls and communicating with Dr. Sözbilir and Dr. Altun from Aegean University and Dokuz Eylül University Izmir. So we knew that it's all things affected all the way to felt in Istanbul even, but in this zone was the case. So this earthquake area, and this is European database of seismogenic faults. So these are the Seismicity fault is already marked in 2011 by European in the European database of seismogenic faults, and that's a well predicted one. Even the magnitude, maximum magnitude was 6.9 moment magnitude. So that's a 2011 prediction. It was known and expected, and as well as expected for the surrounding faults, and hoping these collaborations will keep going for these next earthquakes, and we will be experiencing in common borders. And that's well predicted. Here's the USGS moment tensor solution, and that's exactly in the fits of the what is predicted in the database. Here's the NOAA, that's the National Observatory of Athens shake map, and I prefer this better than USGS and more detail. And so it shows that shaking directions in the valley areas mostly showing there's more shaking would be expected in this after the main shock. So, and also I put the AFAD's and the Republic of Turkey Ministry of Disaster Emergency Management, the Department of Earthquake Data. That's the strong motion stations. That's the distribution of the peak ground accelerations. And then I did some horizontal to vertical ratios, and this standing out as a 3.8 is the highest value of the ratios. That's the horizontally shaken, well shaken place. So it's expected here more shaking, and obviously nearby epicenter and other shaking, and then all others are distributed in Iran. And then other products are coming from USGS ground failure prediction maps. And these are very handy maps. And that's a completely prediction. And it says something expected in the significant limited portion for the liquefaction. And then and the landslide portion is in the limited sections, mostly is nearby epicenters, is the high peaks. And then also is the southern end of the Cheshme Peninsula and southern coastal area in the Sepharis are mostly closer to the epicenter area. Some landslides also experience. But this is interesting, and liquefaction in here is highlighted more, and we'll see later in how that plays out. So another product that's similar way, like NOAA's shake map and USGS products like ground failure maps, and as a parallel, this might be the very handy one, damage proxy maps, and released by the Advanced Rapid Imaging Analysis ARIA team at NASA's Jet Propulsion Lab, California Institute of Technology. This map shows these type imageries show likely earthquake damage areas, and maps are available within a day or several days, depending on the how that frequency of the image downloadable of the radar images, mostly SAR images, and produced the damage proxy maps from the SAR images, this ARIA team, and to support the search rescue efforts and damage assessment efforts. These efforts to use the DPM for, we used the in our efforts to this DPM images for after the shock of the 30 October 2020 Samos earthquake. Sorry. So damage proxy map came to us as a version 03. So that was the rapid one. And then later on, ARIA team updates it and then increases the enhances the imagery's resolutions to detect the more damages. So it is available from NASA ARIA Disaster Information Portal. And the pre-event images used were obtained on October 18th and October 24th, 2020 after event. Image was taken on October 30th, 2020. So that was the lucky time. The second satellite passed before and after. After one was just after the shock, main shock. And also we did mapped in QGIS these images and provided these images in the in different portions of the images and in the Google Earth Pro environment, and provided as a geospatial images based on the desired formats for reconnaissance teams. And they were mostly civil engineering department at the Aegean University, Izmir, Turkey. And few municipalities we also submitted, but we don't know how they used, but we only know how the Aegean University used this. And also used the GER report by Chatin and et al. 2020 to validate these damage proxy map prediction, damage prediction images. So the ARIA team is this, and Sang Ho is the behind the whole image provider during the Samos earthquake, after Samos earthquake, and the Jung Ho Jung was another person that generated those images. But the ARIA team manages leadership is in this group, and they provide science data products like INSAR data products, and then the other one urgent response products, just like damage proxy maps. So how damage proxy map images generated, the methodology is summarized in these two papers. This is in the, sorry, where is disappeared? Anyway, this is SRL, Seismological Research Letters paper. And this is in press, and this is coming out. And so simply is what they do is they take the complex SAR images, most of the Sentinel one is provided by ESA, European Space Agency, Copernicus. And then, so they take the before and after the main shock images and closed images, and then they take the complex image and SLC format and convert it to, okay, wait a second. Okay, so and then they get images and coherency images after that. Just convert the coherency images, and then those coherency images registered and resampled to tie to before and after images, and differentiated and color coded, and we get this type of red dots and differentiated images like this. And these are the two versions of that, and this is enhanced image. It shows some more details. However, there are some false positives. They may not be the damaged areas. So I focused on the Izmir Bayraklı district, and this is where that the extensive damage happened, and then loss of lives and economical losses was tremendous. So here's the first image came out, and so we see those red spots, and they are showing simply where those damaged buildings are. And also in the vegetated areas, you see those more red spots. They are the false positives, because they are more vegetated areas than the living environment in downtown area. But here is simply is the Sentinel C band is more sensitive to vegetated areas. And that's why we recommend not to focus on these areas, but focus on this portion. And this is a recommendation by ARIA team. And so to validate these images, if they are correct, and this is a great report came out by Chetin et al. And it's a well coordinated, and most of the reports and summarized well, and in both sides of Greek side and Turkish side. And so the images will use that for both sides and check the spots and how these damage proxy images are useful and in the area. So another well prepared report, and mostly is most detailed damage assessment done in the Bayraklı-İzmir area was by report by Republic of Turkey Ministry of Environment and Urban Affairs. And their report is also online and as given here. That gives the extensive what the damage is on the ground. Also, from this portion, Izmir portion was taken care of by Bayraklı site, taken care of by the government of Turkish government, and that damage assessment. And these are the ones the outside of this area, because it was restricted and most of the people and scientists focused on other areas and outside of the Bayraklı. And these are gathered from the Çetin et al.'s GR report and also the Bayraklı area's government report. And here's a Bayraklı district and the overlay on the DPM, the damage proxy map. And these are the red spots we expected the damage or collapsed buildings. And exactly it covered those red spots and scattered around. And then most of those damage observed. So the stars from the Turkish government damage assessment team and team report, and then triangles from the Ege University civil engineers group, civil engineering department group. And so this is the covering, and some of those enhanced images is still giving like false positive, but most of the area captured by this DPM images. And especially most of those collapsed and images and killed about 117 people is in this areas. So I tried to zone these. The green portions are showing the first version of the damage proxy map, and then the second hatched white ones is the second version, enhanced version of that. So it's only this portion is not captured, except a few of the highly damaged structures. These are actually light damage reports came out. So the yellow stars and yellow triangles showing the light, and then pink ones showing the moderate damage buildings. But the purple and red ones is highly and collapsed building, highly damaged and collapsed buildings. So it's pretty good, except this portion. And I'm not sure if there is anyone checked that, but according to government report, and there's no damage in this area. However, I checked I lived in this area before, and I checked my relatives and a couple of apartments. I saw these in the Bornova section, and that's called Çarşı section. And I called uncle, and then I said if there is any damage on their apartment, because I saw a couple of spots of red spots nearby their apartment. And they said that was collapsed, not apartment, but some collapsed walls near the apartment and covering, surrounding the apartment exterior. So that they were not also reported. Okay, so here's the Bayraklı district, and here's the liquefaction prediction map released by the USGS after a few hours after the main shock. And here's some spots from the damage proxy map. These are red spots we can see, and showing like a heavily and a good amount of liquefaction expected here. However, there's no ground or checkpoint and done in this area. And if there is one, I would be happy to have it. So the other thing is in this area, so here's the Izmir and here's Seferihisar, and then here's that Gulbahçe. And then there's a university, Izmir high-tech university, and few people went there in the check, and then it is a soil settlement or lateral spreading and liquefaction. I combine them, and here's that liquefaction observed, and exactly the also USGS liquefaction prediction map shows a few patches in this area. Also, I have a few red spots from the damage proxy map from NASA, but it's not dominant or prominent in this area to say this is a lateral spreading or liquefaction. Some surface change happened. So here's the slope failure observed, and then we saw a few good scattered around the some damage proxy map highlights. But here is another one. So what that means is there is on the road between the 6 days of gap in the images, it might be something like road construction inside road constructions. And but in this area, there's no road construction, and this is open area, and possibly we can put a suspicious location in that and to look and check after the earthquake. These liquefaction and landslide or post-earthquake maps are critical in this area. So we can, we have to document and all the post-earthquake cases because they are called perishable data. And if you speed up in this after earthquake, post-earthquake reconnaissance efforts, and that will be ideal to capture all of those as early as possible before the people cover those and or fix the liquefaction or useful data. And here's the landslide prediction map. And we can see some of those spots are really well shown and detected by the damage proxy maps. And here's the false positives, and mostly is the mountain or vegetated areas. And here's the some areas we have some damage proxy spots. And so it's closer to epicenter area, the landslides, that's the surface deformation is changes or change detection of this type will be picked up by this damage proxy map. So it's the zoomed area, and you can see it's covering well in this area. And another show, and so this is landslide prediction, is the landslide probability and the values. And here's the displacement map from, again, NASA ARIA group. And you can see the high displacement in the Samos Island in this section. And then, so I got this displacement map, and then other report by reported locations. And here's the soil settlement, and here's some rock falls, detachment in the rocks, and here's the slope failure in this area. And then here's the zoom to the Samos downtown area. And so it's well covered in this DPM image also, and it's the liquefaction reported.
Dr. Chakir?
Yes.
Time is, you have 1 minute.
Okay.
Thank you.
So to tsunami also in the Sajik region, and here's another spot. And so this NASA Advanced Rapid Imaging and Analysis team produced these DPM showing areas in Izmir, Turkey that were likely damaged from the earthquake, and publicly released DPMs that highlight areas of potential damage. These are publicly released. Anyone can reach those images, and NASA ARIA DPM can be good supportive satellite imagery product for damage assessment, but requiring a practice and good coordination prior a big earthquake and for emergency response operations. These images may be used as aid for assessing direct economical structural losses, and DPMs can be used as a guidance to identify damaged areas. As seen in the displacement, the western part of the Greek island of Samos moved upward by as much as 10 centimeters. The map can be used as guidance to identify areas of significant ground displacement, and liquefactions and landslides, rockfalls were detected in Samos Island. Mostly they are nearby the epicenter area. USGS landslide liquefaction model maps released a few hours after the main shock can be well predicted by adding DPMs or vice versa. And DPMs showed some good correlations with USGS liquefaction predictions in the Izmir Bay Area, but one observation reported in this area. And DPMs are very reliable to detect damage levels of high collapsed buildings, highly damaged and collapsed buildings in densely populated areas, and to detect ground failure, liquefaction and landslide rockfall near the epicenter areas. And tsunami inundation zone is observable in Sajik south of Izmir, and also DPM gives some images on that.
Thank you, Dr. Chakir. Thank you for your presentation. Very interesting about the application, the methodology, satellite methodology. Unfortunately, I'm looking for chat questions. No questions. So thanks again. We move to the next speaker, which is Yorgos Karakaisis, together with Cordelis. He will present about seismicity variations preceding the Samos earthquake at the Eastern Aegean. Can you share the screen?
Right now.
Okay, thank you.
Okay.
Fine, thanks.
Okay. Thank you, Professor Caputo. We are indebted to Professor Tatar and Pavlidis and you yourself for coordinating this workshop. I'm afraid that this presentation is not going to be so interesting as the previous ones, but I will do my best. We have examined with Manolis Cordelis the seismicity during 10 years before the Samos main shock. This is typical for-place solutions compiled by several seismological centers. They show that the fault that generated this earthquake has an east-west orientation, and additional aftershock data show that it dips to the north. More formally, we will show you examples of spatiotemporal seismicity patterns probably associated with the Samos main shock. We will use the DAS model And we will take into account data that have been taken from a catalog compiled in our laboratory, which is homogeneous in respect to magnitude. Now, a brief introduction to the accelerated moment release or accelerated seismicity. There has been an amount of observations which reported that the seismicity in a broad region around an oncoming main shock increases going towards to this generation. In recent years, I mean recent during the last 2 or 3 decades, this increase has been termed as accelerating seismicity and has been modeled according to a critical process which culminates to a critical point, the main shock generation. The first efforts to quantify this accelerating seismicity started by Buffy and Varnes, who examined the time-dependent seismicity in the broader San Francisco Bay region before the Loma Prieta 1989 earthquake. They used earthquakes with magnitude larger or equal to 5, which occurred in Northern California from here to here, almost, starting from 1852. That means 2 years before the strong Fort Tejon earthquake, which occurred there. So, in these 3 graphs, we can see the cumulative seismic moment, bending of strain, and number of events as a function of time. The dashed line here corresponds to the occurrence year of the San Francisco earthquake with magnitude 7.9. The bending of strain is nothing more than the cumulative square root of energy calculated by the magnitudes of the events considered. They examined in more detail the seismicity, that is, the seismic moment and the bending of strain, after the 1927 Lombok earthquake, which occurred west of Los Angeles with a magnitude 7.3 close to Santa Barbara, and they follow a time to failure analysis. They came up with this power law relation, where the exponent is smaller than 1. In the upper plot, we see the cumulative seismic moment, and the lower one, the bending of strain. They fit this power law to the data, and they came up with these occurrence times, these predictions. In the seismic moment approach, the prediction time has been 1996, whereas in the bending of strain approach, the prediction time was 1989.9. It was for this reason, that means the very good prediction time based on this power law, that from then on, most of the researchers use the cumulative bending of strain and not the cumulative seismic moment, as we see. Then, assuming that the acceleration pattern is valid and is a fact, the problem is to define the region where this accelerating process takes place. That means to define the critical region where intermediate magnitude shocks occur in such accelerated manner. So, Bowman and his colleagues proposed a parameter, the C parameter, curvature parameter, which is nothing less than the RMS error of the power law fit divided by the RMS error of the linear fit. It can be seen here in their example. The center and the star corresponds to the epicenter of the Kern County earthquake in 1952 with magnitude 7.5. They draw some circles here, 200 kilometers, 325 or 350, and 600 kilometers. They consider the earthquakes within each circle. They computed the cumulative Benio strain, and they tried to fit this data with the power of it, the solid curve, and the linear fit, the dust line. So, for the circle with radius 325 kilometers or 350, this is a parenthesis, it means that no matter how many times, excuse me, how many times you check carefully a proof, there will always be typing errors. Continue. For this region, for this circular region, the curvature parameter had the smallest value. That means that this seems to be the critical area for this mention, for the Kern County mention. Now, when a new methodology is proposed in seismology, as in other disciplines, it's not uncommon for the groups of scientists to apply, at least for validation purposes, these methodologies to several areas of the world. Here you can see examples of such work here. However, in addition to the observations of increasing seismicity before a strong main shock, there have been observations of decreased seismicity before a main shock, like the Moji pattern. More recent evidence have shown that in a narrow region around the fault, which is going to give a strong main shock, there is a seismic excitation which is followed by a decrease of seismicity, a quiescent period. So global data show that this indeed happens. So a model has been, here we see how this works. The dust ellipse here represents the critical region, and this is the accelerating earthquakes which occurred here. Within this critical region, there is another smaller one where the cumulative Benio strain shows that there is a decelerating pattern. As the time progresses, both patterns continue and are destroyed by the generation of the mention. Here is the critical region, and this is the seismogenic region. So, the model which we have used in this study is based on the concept that main shock is a critical point. It means it is the culmination of accelerated generation of intermediate magnitude earthquakes, which are called pre-shocks, and intermediate magnitude means about 1.5 or 2 units of magnitude smaller than a main shock magnitude. This is the power law. Tc is the Tf time used in Batty and Varney's original equation, and A, B, and M are parameters calculated by the available data. On the other hand, a similar power law holds for decelerating pre-shock, but in this case, the power is more than 1. So the critical region is the region where accelerating pre-shocks occur, and the seismogenic region is this one where decelerating pre-shocks occur. We use the curvature parameter, but not only this curvature parameter, as we'll see together. By using data from all these regions, several empirical relations have been derived, which scale the dimensions of the critical and the seismogenic regions, the size, with the magnitude of the main shock and the seismicity level, and the duration of the accelerating and decelerating sequence with the seismicity level as well. We have calculated and modeled snippets. So the duration of both sequences depends on the seismicity level, which is expressed by this quantity, is the cumulative Benioff strain per year and per surface unit. The surface unit is 10,000 square kilometers. The size of both regions scales with the magnitude of the main shock, of the future main shock. And I want you to remember, for the elder ones, the soft inclusion model proposed by Dobrovolsky. This is the size of the region where precursory phenomena are observed. These relations are almost identical to this one for the critical region. So there is a theoretical background, a more physical background for this critical region. Then, here we see an example of the application of this model, the accelerating Benioff strain before the Skiros 2001 earthquake in Central Aegean. Here we see a proposal of Randall that during going towards a mesoc occurrence, the rate of the small magnitude seismicity is stable, but the rate of the intermediate magnitude seismicity increases as we approach the main shock occurrence. And here we see these frequency magnitude plots for 3 consecutive time periods as we approach the 2001 main shock. This is the last period, just before the main shock. Procedure now. We search for the critical and seismogenic region, not only on the basis of the curvature parameter, but we use as well an additional parameter which shows how much the data fit the constitutive equations of the model and their standard deviation. This new parameter is quality index value, and you will see this in the following maps, which is nothing more than the probability that the data fulfill the global relations divided by the curvature parameter. We also found that the value of the curvature parameter, of the quality index value, varies with time, both for the acceleration and the deceleration pattern. It means that several years before the main shock, the accelerating pattern and decelerating pattern are more intense. That means the Q value is higher, and then gradually these patterns, both patterns, the accelerating and the decelerating patterns, are destroyed. So we cover the study area with a grid of equally spaced points with the required density. Each point is considered as the center of a circular region here. We collect all earthquakes with epicenters within these regions, and we use their magnitudes to calculate the cumulative bane of strain. Calculations for each geographic point are repeated for a combination of various values of sizes of the critical order seismogenic region, of the main shock magnitude, the target magnitude, that means the starting year of the accelerating or the decelerating sequence. The best solution for each point is found and kept, and it's kept. All solutions from all grid points are examined, and we come up with the largest quality index value, either for acceleration or for deceleration, and this point is considered as the center of the circular regions where accelerating or decelerating pre-shocks occur. The basic focal parameters now for the prediction are the epicenter of the probably expected main shock is the mean epicenter of the decelerating pre-shocks. That means pre-shocks which occur in the seismogenic region. The origin time is the mean origin time calculated by both these relations, and the magnitude is the mean magnitude calculated by these two relations. And the uncertainties are of this order of magnitude, 0.3 in magnitude, 3 years, give or take, for the origin time, at about 100 kilometers in the epicenter or less. In this map, you can see the epicenters of strong earthquakes that occurred in the examined region during this decade. And here we see several plots, maps. Decelerating maps are in the upper part of each slide, and accelerating maps are in the lower part. This is the legend for the quality index values. Remember that the higher Q value, the more intense the phenomenon. That means more intense deceleration takes place here, and more intense acceleration takes place here. You have also to keep in mind that the deceleration occurs close to the epicenter of the probable ensuing main shock. So, you see here the magnitude range of the expected main shock. That means we have combined different maps for different target main shocks, as we see here. And at the next maps, we will see just a snapshot. Observe, please, this region of Samos here, as we go. Starting in 2016, we see that for such target main shocks, there is a growing decelerating pattern here and here. It continues. Of course, this decelerating pattern is associated with the course 2017 earthquake. And you see here that there is no deceleration now. And going on to the end, we come up with these final maps. If you remember that we said that several years before the main shock, the Q values attained their highest values, the Q indexes, the quality indexes attain their highest values. So 3 years before the main shock, we found the highest QD and QA values. This is the critical region, and this is the seismogenic region. red circle is the epicenter of the observed main shock. The blue star is the epicenter of the predicted main shock, which is the mean epicenter of all the decelerating events. And here is the decelerating and the accelerating cumulative Benioff strain. So the average value of the two respective equations for the origin time suggests a generation time 2020.4, a main shock magnitude of 6.5. That means that we are not correct as regards the magnitude of the main shock, since its error is 0.3, and the difference between the predicted and the observed epicenter is of the order of 30 kilometers. Okay, thank you for your attention.
Oh, many thanks, Professor Karkaisis. I'm looking for questions. No questions, nor here, nor in the chat, YouTube. So I thank you again for your presentation. Interesting prediction. You should apply it to more situations. And move to the last presentation of this afternoon session. Tagunzelli and colleagues, possible precursory anomalies, again anomalies and precursory anomalies on groundwater level and geothermal resources associated with before and after the Samos earthquake. Dr. Zelli?
Thank you, Professor Caputo.
You share the screen, full screen, please.
Can you see?
Yes, thanks. Fine. You have the floor.
Okay. Good afternoon, ladies and gentlemen. My name is Tagunzelli. First of all, I would like to thank the organizing committee of this organization and this important workshop. And also thanks for inviting me. That's a good opportunity to share our findings and research with many researchers around the agency. Today, I will talk about the possible precursory anomalies in groundwater level and geothermal resources associated with before and after the October 13, 2020 Samos earthquake. Here is our team. I feel lucky because we have a team of very special researchers who supported and contributed me during this study. I would like to thank Esra Bilgiç, Bahadır Öztürk, Professor Alper Baba, Professor Hasan Sözbilir, and Professor Orhan Tatar. As seen from the team, this study conducted in cooperation with different universities such as İzmir Institute of Technology, 9 Eylül University, and Sivas Cumhuriyet University. Within the scope of this presentation, I will first talk about the aim of the study and the location of the study area. Next, I will speak about the groundwater studies in Bayraklı region, then the geothermal fields, and finally, I will end up my presentation with results and discussion points. The purpose of this study was to examine the effect of the Samos earthquake swarm in Izmir. Observations made within the scope of this study are mostly based on relationships between earthquakes and water level changes, and also anomalies in geothermal activity, physical and chemical properties of geothermal fluids. In this context, our studies have started in Bayraklı district, Gülbahçe and Tuzla geothermal fields. We started working immediately after the earthquake. We went to Sığacık region where the tsunami event took place, and the tsunami was an earthquake effect occurs in seas and surface environment. So at this stage, the following question come to our minds: how were groundwaters and geothermal systems affected by this earthquake? To answer this question, we choose three study areas. The first one is Bayraklı district. The second one is the Gülbahçe geothermal field. The third one is the Tuzla geothermal field. Let's have a look at the Bayraklı groundwater studies. After the Samos earthquake in Bayraklı, buildings on quaternary alluvium saturated with groundwater were seriously affected, and 17 buildings were collapsed, and severe damage and casualties occurred. This region also affected by the destructive earthquakes in historical rivers. In this figure, you can see historical coastline changes and all the riverbeds. The white-colored region you see now correspond to the places thought to be under the sea during the time of the ancient city of Smyrna, and even in the 1900s. Actually, we were so lucky and prepared as the Izmir Institute of Technology. We were actively monitoring the groundwater in the Bayraklı district. In Bayraklı, 10 groundwater observation wells were installed in the alluvial plain to assess responses in groundwater level. The groundwater level in this area is very close to the surface. All wells were drilled to locations where building and groundwater interaction is intense. Some buildings that collapsed after the earthquake are very close to the well locations. This situation shows how accurate the well selection was made. You can see the conjectural old coastline in Bayraklı, old riverbeds, and also collapsed buildings after the Samos earthquake, and our sampling wells. These are images from our study. You can see the drilling phase, diver placement process, and diver data collection process. We use 3 types of diver data loggers in 5 of the observation wells, and these divers can take measurements with desired time intervals. Divers were set to read the data in every 1 hour, and TD diver was located in 4 of the observation wells, and Baro diver and CTD diver located in 1 well. These are our monitoring parameters: water level, temperature, and electrical conductivity. These parameters also periodically correlated with divers' measurements and verified by classical field measurement methods. Within the scope of this study, earthquake data of AFAD were used for correlation. There is an important information about our observation process. During this study, there was a period without precipitation in Izmir. There is no other working wells near our observation wells. So for this reason, water level change not affected from these factors. In this figure, a time-dependent graph of temperature measurements taken from 5 different wells at 1 hour intervals are given. You can see the Samos earthquake time. During the period of 1 and 2 days before the Samos earthquake, changes in the temperature of the wells were detected. While these anomalies were in the form of temperature increase in wells such as S1 and S3, temperature decreases were observed in other 3 wells. The situation indicates that there was a temperature-based change in groundwater before the earthquake. During the Samos earthquake, the temperature values in all wells decreased significantly for a short time and then rose suddenly to a level close to or higher than the previous level. It is thought that the reason is entry of the waters with different temperatures from the outside into the stagnant well with the earthquake waves. Similarly, the temperature change in wells before the 20 November earthquakes can be seen and figured. Our divers recorded some pre-seismic indicators, and they show that the water level rises 2 days before the event, and this is approximately 10 to 20 centimeters. And this situation took about 7 to 10 days after the main shock for the water levels to recover their former static levels. You can see again the water level change before and the time of the Samos earthquake. We also observe electrical conductivity in well number S9. The electrical conductivity observations show that the bottle-rock interaction has increased with the tension before the earthquake, and then waters with high electrical conductivity, it's possibly the seawater intrusion in the Bayraklı, mixed into the well. After the earthquake, the water left the well with the shaking, and the water level started to return its former state. Our observations indicated that the dates of the earthquake swarm and the time interval when water levels remained higher are almost the same, and both lasted for 7 to 10 days. This is an important indication that seismic activity can keep water levels under control for a certain period. In previous studies, we know that the groundwater in Bayraklı are of the calcium bicarbonate type. So as can be seen in Piper on the left and Schöller in the right diagrams, S9 and S1 wells have higher sodium chloride concentrations than other wells, and this situation shows that these wells affected by seawater intrusion after the Samos earthquake. Temperature changes in S1 and S3 also can be associated with seawater intrusion and consistent with this situation. Let's have a look at our geothermal fields. Tuzla and Gülbahçe geothermal fields are located on the north of the earthquake epicenter. As a result of observations made in the fields after the earthquake, there are some anomalies detected in geothermal fields, such as the responses in chemical and physical properties of geothermal fields. You can see our monitoring parameters. We have some field observations, such as new source formations, gas leakages, and liquefaction areas. Gülbahçe geothermal field, structure contours by right lateral strike slip and normal faults of the Gülbahçe fault zone. Geothermal sources form in the regions where faults intersect with each other. Secondary permeability in these zones controls the fluid circulation. With the seawater intrusion, there are sodium chloride type hot springs with a temperature of nearly 35 degrees Celsius. After the Samos earthquake, new spring formations whose temperature reached to 40 degrees Celsius can be observed. And also there are some gas leakages in the sea after the earthquakes. You can see some examples of our observations, and you can see the sand volcanoes on liquefaction site in the Gülbahçe Bay. In the Tuzla geothermal field, geothermal fluid comes from the basement units through the fault segments. It is possible to see hot water springs on the right lateral strike slip segments of the Tuzla fault zone, where the faults step over and/or bend. Fluid channels on the fault plane gained activity after the earthquake. A new hot water outflow started on one of the fault segments. You can see the images from the fault planes, while you see the first activity 2 days after the earthquake on the left top side, and you can see the new sources formed after 5 days on the right image, and this is the zoom-in view of the fault plane. In addition, there are some mud and fumarole outlets were detected in the field. The temperatures of geothermal fluid reach the surface from the fault plane range from 78 to 99 degrees Celsius, and this activity still continues. Temperature and electrical conductivity increases detected in the field studies, and these values as the same as the deep geothermal wells values. We have sampled this region. You can see the Piper and Schöller diagrams of our samples. The sample A and sample B are taken from the geothermal fluid samples on the Tuzla fault segment. These resources is the same as the natural hot springs in the how can I say? There are lots of hot springs in this region, such as Doğan Bey, Karakoç, and other springs. But and this geothermal fluid also have a sodium chloride character. However, they have higher iron concentrations like fluids in the geothermal wells of the region, because they quickly came from the deeper reservoirs along the fault plains after the Samos earthquake. As a result of studies carried out, some obvious results and observations have been revealed. 10 wells with 10 meters depth were drilled in Bayraklı region before the earthquake. Temperature, water level, and electrical conductivity automatically measured at regular 1-hour intervals by the divers in all 5 of wells, especially the water level rise steps observed in shallow wells in Bayraklı, and this is possibly due to the compaction of the geological units during the earthquake. It's a significant finding that changes in temperature, water level, and electrical conductivity in these observation wells were detected before and after the Samos earthquake. Geothermal anomalies in Izmir city have been studied in detail, and significant anomalies were determined during and after the earthquake in 2 important geothermal fields, Tuzla and Gülbahçe geothermal fields, and related fault zones affected by the Samos earthquake. New hot springs formed in the Gülbahçe field. We observed some liquefaction and gas leakage areas on the seafloor of Gülbahçe Bay. Similarly, in the Tuzla geothermal field, we have some new hot spring outlets along the Tuzla fault plains. In addition, as we see from the yesterday's earthquakes, this activity in the region still continues. If more observation stations are established in the different geological units with networks, higher quality and accurate groundwater level, chemical and physical responsiveness will be obtained. So these monitoring studies can be very useful in the long term in predicting future and earthquakes. Thank you very much for your attention.
Okay, thanks for the presentation. Interesting observations. Have a look. Congratulations. Questions on your interest in innovative work. What kind of studies are you planning to do on this subject in geothermal fields in the future? That's the question from the audience.
Yes, thank you for the question. As mentioned in the presentation, this study contains preliminary findings of our newly started monitoring process. We are currently monitoring these regions. As a priority, we are trying to increase the number of the wells, the divers, and also the samples in the study areas. In addition, if we may convert this monitoring process to a monitoring via an online system, instead of reading this data from the field weekly, we will have able to analyze it more faster. So with future projects, I hope we can make our studies more comprehensive with more innovative and new approaches such as other methods and radon measurements, isotope measurements, etc. Thank you.
Okay. We have a few minutes. If there are some questions also for the previous presentations. Some curiosities and questions. No. Okay, Oran, I would say.
Okay, so we can have a longer coffee break.
Just a little bit longer, yes.
Longer coffee break, yeah.
We need some relax. And we will be back in time at 15:55 Greek and Turkish time, which is 14:55 Italian time, I remind you. Be in time, please. Thank you.
Δημήτρη, εγώ είμαι στο πόστο μου. Καλημέρα.
Γεια σου Στάθη μου, σε έχω δει, το είδα.
Όλα εντάξει?
Νομίζω πως πάμε καλά.
Ναι.
Όλα καλά.
Εσύ είσαι στην Ανάβησο τώρα? Όχι.
Τώρα είμαι σπίτι. Συνεχίζουμε τηλεεργασία.
Μάλιστα.
Γύρισα χτες από ταξίδι με το πλοίο.
Ωραίο. Σε αυτή την εποχή το να κάνεις ταξίδια με το πλοίο είναι...
Πράγματι.
Hello, Dr. Tatar. Nice for me to be here with you. Very nice opportunity and very well organized. Congratulations.
Hello, Stathis. Nice to see you after a long time.
Πύρο μου, πού είσαι? Δεν σε βλέπω.
Δεν χρειάζεται να με βλέπεις, θα με ακούς.
Και να σε ακούω και να σε βλέπω και να σε καμαρώνω όλα.
Θα ακούσουμε εσένα τώρα.
So, Orhan, do you think we're ready to start? Okay, unmute your microphone, whatever. So, welcome back, everybody. I would like to welcome you to the last session of today of this very, very interesting workshop. We have 5 very interesting presentations in this session, and we start immediately with Stathis Styros. Stathis, please, you can start sharing your screen, and the microphone is yours.
Thanks very much.
For those who wish to ask a question, please click the icon Q&A at the bottom of your screen and type your question, preferably before the end of the presentation so we can read the question to the speaker. So, Stathis, please.
Mr. President, Mr. Chairman, thank you very much. And first of all, I must congratulate the Turkish, the Italian, and the Greek colleagues who had this very nice idea, which seems to work very, very well. And thank you for the invitation to participate. The Samos earthquake is very particular for me because I come from Samos. So I'm very close to people from Izmir. And I'm going to discuss the implication of this earthquake for the modeling of ancient historical earthquakes, which are usually used to understand modern future seismicity. And also there are some implications for ancient monuments. Some years ago, or many years ago, I was studying coastal changes in Samos, and it was nice to find that several raised shorelines that are found at the western part of the island here, shown in 2 locations here or here. They indicate raised shorelines who have been uplifted during earthquakes. The last one was about 500 years ago, and the other one recorded was about 3,000 years ago, rough dates. And these uplifts indicate large earthquakes, cannot be small earthquakes, 6.5 earthquakes, etc. So when I heard in the radio and television that an earthquake of magnitude 7 or nearly 7 occurred, I was horrified. The earthquake of this magnitude was not a surprise, but when I heard that it was just north of Samos, where there is one of the deepest basins in the Aegean, which are associated probably with raised shorelines there, I was expecting the worst. So my first predictions were that at least the northern part of Samos was destroyed, like this one village here, which is the village where I come from, and also that this damage was extending to the coasts around Usada Sea in the Turkish, in the continental coast there, where this fault continues, this fault zone better. However, in both these points, I was wrong. And I'm very happy for that because I shall have the opportunity to go for holidays in Samos. Of course, Samos have suffered much damage. This photo here shows the landslide. It was before the earthquake. This landslide was reactivated during this event, and still produces serious problems in the circulation of the main road of the island. This is one of the examples. The other problem is structural damage. About 10% of the total number of about 28,000 buildings that exist in Samos were affected by this earthquake, from small, moderate damage to collapse. However, statistics do not show the whole truth, only one side of the truth, because most of the damaged structure were semi-ruined already before the earthquake. An example is here. It was nearly ruined and abandoned and then collapsed. Or this building here, again, this is before the earthquake, and you can see the dam that is ready to collapse, perhaps, and it is dangerous for people to stay there. This is the main square of one of the villages in Samos. And so even a cat, if walks on these roof tiles there, is possible to produce some major problems. There have been damage in bigger structures like churches, but also the situation is somewhat clear. For example, this church in the village of Leka here was badly damaged, but as you can see, it is of poor construction, mostly without mortar. Another big church in the northern coast of the island, which is a very good construction, also has signs of damage in certain parts. But a closer look indicates that these parts here were constructed without the necessary care. It was an old church, about 100 years old, and there were no stiffeners against earthquakes, etc. So it is expected. The other problem is that the environment along the northern coast of Samos was very unfavorable environment. I mean, the geological conditions. This map here shows geological conditions. This gray here is recent alluvium, mostly sandy layers with the ground level near the with underwater level near the ground level. So it is very unfavorable conditions for buildings to withstand even moderate earthquakes. This comes from this village here. I saw it before, Konstantinos, and the other from a major village here called Kokari. So the conditions were extreme. In this graph here, they shows a kind of cross-section, and they show that shows that the northern part of the island is just above the tip of this magnitude 7 fault. A fault which produced a magnitude 7 earthquake. So in this environment here, in this location here, normally some important damage is expected. It's not possible to have all these events here, this earthquake, and nothing and no more damage here. Still, because on these conditions, the Samos earthquake was a kind of surprise, which I could say was characterized by a bimodal pattern of structural damage. In the near field, there was actually a damage deficit in the area of Samos. Limited damage for the conditions and for the specific earthquake. And the worst of all, of course, is that in the far field, about 70 kilometers away, in a part of Izmir, there has been localized destruction, which is something incredible, incredible loss, so many people, etc. And all this was produced by a moderate background acceleration. The maximum acceleration measured somewhere there from 3, 4, or 5, I don't remember well, accelerometers, was 0.11 G. It is very moderate value of background acceleration, and to have such great damage and death toll. I believe that this pattern of earthquakes is not a very unique, and we have some other examples, perhaps in smaller scale. In 2014, in the Northern Aegean, there was another earthquake. It was the Samothraki-Kokcheada earthquake, again of magnitude close to 7, which was characterized equally by damage deficit in the near field. The islands around Samothraki, around the fault, as I'll show later, were suffered no damage at all. And there was some moderate damage in the far field. This figure here explains the situation based on high rate GPS data on dynamic displacements. So this is the fault modeled in cooperation with some Turkish colleague from Istanbul. And what we found is that the dynamic displacements recorded by high-rate GPS were relatively small for the whole earthquake. Here is recorded the amplitude of displacement, the total amplitude of displacement, not component, total amplitude, as a function of time. As you can see, there was a kind of increase of the displacement, and then there was nearly stability. This can be mostly measurement noise. This comes from Samothraki. Also from Limnos on the other side, it is again the same thing. But if you go about 50 kilometers away from the epicenter, at Çanakkale, at the station Çana, you shall see that there is more or less smaller amplitude of displacement, but then there is all this kind of waving, which indicates some amplification of seismic waves producing seismic displacements, oscillations on the top of the ground. So this was really important because it shows that in certain areas we can have this kind of amplification of seismic activity, and this scale shows that this amplification was observed for about 30 seconds, and if this was, if the amplitude of this oscillation was higher, it would be destructive for the area of Çanakkale. So a question arising is it possible to use this knowledge from the Samos earthquake and perhaps other earthquakes like the Samothraki-Kokcheada earthquake to improve our understanding of historical earthquakes? I shall try to contribute in this problem, presenting some true and hypothetical scenarios. A first case is that, okay, if a background acceleration of only 0.11 G at Bayrakli was transformed into destruction potential for relatively long period structure, high-rise buildings, then we can assume that in the past, earthquakes with similarly low acceleration could have been the cause of collapse. The collapse of ancient high-rise long period structures like ancient temples. And for most of these temples, ancient Greek and Roman temples, the causes of their destruction, whether they are affected by earthquakes or not, is a matter of debate by structural engineers in our days. And what actually suggests is that they need extreme accelerations to be destroyed. In fact, the recent case of Bayrakli indicates that we may have catastrophic effects with smaller background accelerations. And an example of this case is the Sunion Temple, which is very close to Athens. Another case is that studies of Ambrasis and others from Iran and also from Mediterranean area have revealed that the true epicenters of earthquakes are located within 30 kilometers from the area of maximum intensity, from their macroseismic epicenter. In the case of this of the Samos earthquake, we have these two distant areas. So this model for identifying the maximum intensity is not easy to be applied. Each of these areas here indicates perhaps a different earthquake, but still we know, because we have the modern seismological evidence, that it was just one single earthquake which produced this problem. And this problem is not very theoretical. It is something very important for the earthquakes in the Aegean Arc. Let's see some other cases. For example, this is an earthquake, the mesoseismal area of an earthquake about 2,200 years ago, which affected both the modern Greek and Turkish areas. As you can see,
Stafi, you have muted your microphone.
Sorry.
Yeah, great.
So this is a case 3, which examines another earthquake which occurred 2,200 years ago and which affected this area in covering parts of modern Greece and Turkey. From our modern experience of earthquakes, including the Samos earthquake and the Kos earthquake, etc., we cannot expect that a single earthquake can have produced such a large destructive mesoseismal zone. So we may examine different scenarios for that, perhaps mixing of different events, exaggeration of events, or even the possibility of remote triggering of kinds of earthquakes like that in the case of Samos in the area of Izmir. Two other earthquakes, which occurred with a difference of many centuries, but seem to have a very similar mesoseismal area. This is peculiar, but still, I believe that this cannot be a single earthquake to have affected or produced much damage from the north, from the south western part of Rhodes to this part in Turkey. Also, this here. Again, I'm suspect that these earthquakes can be perhaps exaggeration, a mixing, or a problem of like that of far-field localized effects. And I'm going to reached near the end of this presentation, going back to Samos. And I shall discuss not the problem of just earthquakes, which are used to understand and compute the seismic hazard, etc., of various areas in the Mediterranean area, but also the problem of monuments and the problem of the health of ancient remains. In Samos, there is an ancient temple built about 500 years before present era. And this is one huge column here is preserved. It is interesting that the drums, each of these parts there, is offset next to the other. The only explanation for these drums is that they originate from oscillations due to ancient earthquakes. We don't know how many, but we know that there were earthquakes. And these earthquakes produced a kind of pattern in the oscillation. And this was a way for the ancient monuments, with the ancient columns, to be preserved erect, to survive the earthquakes. So in this case, we have two different scenarios. Either that this oscillation, which produced the offsets, is associated with very high background accelerations. This acceleration can be associated, for example, with the raised shorelines, with earthquakes which produced the uplift of shorelines in this area here, and they are in an area of a few kilometers away. This is one possible scenario. And the other scenario, which is in analogy to the Bayrakli effects, is that a moderate earthquake, an earthquake that produced moderate seismic intensities, was in position to produce all this oscillation in this long period structure, as exactly has been observed in some parts of Izmir.
That is
So,
1 minute left, please.
Yes, thank you. Summary and conclusions is the recent earthquake was very particular because it was characterized by damage deficit in the near field, but localized extreme damage surplus in the far field. This particularity in damage distribution may not be unusual and may help in the reevaluation of ancient earthquakes and perhaps to understand and protect ancient monuments. And what is presented here was actually a reverse process, because till now ancient earthquakes were used to understand modern seismicity. In this case, we used modern earthquakes to understand ancient seismicity. Secular.
Thank you very much, Stathis, for this very nice presentation. I see no question in the question icon. So if there is no question from the panelists which could be expressed orally, is there any? No, then I think that we can thank again Stathis Styros, and we can slowly move to the next presentation. Stathis, you can now stop sharing your screen.
Thanks very much.
Thank you.
Thank you.
Ioanna Diadafilou, you're ready for your presentation? Yes, please, you can now share your screen.
Yes, of course. Thank you. Okay. First of all, I would like to congratulate on your efforts to organize the conference. And I would like also to thank you for the invitation. Okay. Just a minute to share my screen. Okay. Today I will present you the strong Samos earthquake of magnitude 6.3 on 11th of August 1904 and its aftershocks revisited. The outline presentation includes the last October 2020 earthquake and tsunami in Samos Island, following the historical seismicity of Samos Island, the 1904 seismic sequence. Then I will refer to the focal parameters from previous catalogs for this sequence. I will continue with the microseismic effects of 1904 earthquake sequence. Then I develop the methodology about the magnitude redetermination of the first decade of the early instrumental period in Greece. And then I will provide epicenters and magnitudes above this methodology, according to the above methodology for the 1904 earthquakes. And I will stop with our conclusions so far. So, on 30th of October 2020, a strong earthquake of magnitude 7.0 struck the eastern Aegean Sea and caused important structural damage in Samos and in Izmir area. The earthquake caused also rockfalls, landslides, liquefaction phenomena, and seismic uplift in the island. Tsunami also observed and measured in Samos Island and in western Turkey. So for these reasons, this earthquake attracted interest about the historical seismicity of the area. The historical seismicity of Samos Island is in the map, shows on the map with the red circles, which represent the earthquakes from antiquity up to 1955. The white star shows the last earthquake on the north of the island. The red lines show the main faults of the area. And one of the strongest historical earthquake is the 1904 with magnitude 6.8. The 1904 earthquake sequence starts with the main shock on 11th of August 1904. Then followed by two strong aftershocks on 18th of August and the 10th of October. So we re-examined the macroseismic effects of this sequence based on several contemporary reports. And we redetermined magnitudes and epicentral coordinates for these three earthquakes. So regarding the focal parameters of the three earthquakes are listed in various earthquake catalogs. However, parameters inserted in some catalogs are copied from previous ones. In addition, it is not very clear how parameters have been determined. For example, the magnitudes for the main shock varies from 6.15 to 6.8, and for aftershock A1 from 5.9 to 6.0, and for aftershock A2 varies from 5.8 to 6.0. In the map, you can see that with the red circle, we have the main shock and the suggested and the earthquake epicenter that are listed in various earthquake catalogs, 1, 2, and 3. For the aftershock A2 with the green color represent the epicenters for the aftershock A1. We have also again 3 solutions, 1, 2, and 3. And for the aftershock A2, we have only 2 suggested solutions from the various earthquake catalogs, one in the southwest and the other on the northeast in the Turkey. Regarding the macroseismic effects of the 1904 earthquake sequence, we used the unpublished Book of Earthquakes from National Observatory of Athens. We used also several press reports and the bulletin of NOAA. The main observation from this sequence is that 4 shocks reported from a 28th of July. The damage zone was mainly observed in the southern side of Samos and in the Furni Island. 540 houses in several villages destroyed, while 10 persons were killed and 20 people injured. In Shoke, west of Turkey, some damage caused also. Felt also in Izmir, Nea Ephesos, Idinion, Ikaria, Patmos, Naxos, and Santorini Islands. No damage was reported after the strong aftershocks, and no tsunami was reported also. So, in the frame of my PhD thesis, I redetermined magnitudes for the period 1900-1910, including the 1904 Samos earthquakes. We utilized seismic records of Agamemnon-type seismographs in Athens and other stations in Greece. In the map, Chalkida Station, Aegean Station, Zante Station, Kalamata Station. These instruments were intermediate natural period, that means were similar to Minka and Vichert instruments that operated in Athens Station after 1910 and 1948 respectively. So we used the amplitudes in millimeters of seismic waves recorded by Agamemnon seismographs. The data are taken from the bulletins of NOAA, and we redetermined the 52 earthquakes calibrated over surface wave magnitude of the period 1911 to 1963, determined by Papazachos and Komninakis from Minka and Vichert records, by using the next 2 formulas, one for the shallow earthquakes and the other for the intermediate depth earthquakes. The 3 earthquakes of 1904 are among the 52 events for which magnitudes redetermined in the black frame, as you can see in the map. Then we correlated the magnitude of Agamemnon with the magnitude of earthquakes are listed in the catalog of the university in Thessaloniki, which is the most complete for this period, 1900-1910. So we found good correlation for both shallow and intermediate depth earthquakes. By using this methodology, we suggested a new solution for this earthquake sequence. First of all, we tested main shock epicenters from previous catalogs and found magnitude equals to 6.4. So for the next step, we tested a new epicenter, and we adapted that is should be placed offshore South Samos, close to the macroseismic epicenter, Hora town. Here is the Hora town, and to Shoke in West Turkey. From the wave amplitudes in the Agamemnon records, at Athens station, and for epicentral distance 305 kilometers, we get magnitude equals 6.3. This magnitude is consistent with most of magnitudes determined in the previous catalogs, but is different from the magnitude listed in the catalog of the University of Thessaloniki, 6.8. For the aftershocks A1 and A2, the best solution corresponding to wave amplitude provide epicenters offshore northwest Samos with magnitudes 6.2 and 5.9. It should, however, should be not ruled out that aftershocks A1 and A2 did not represent real aftershocks, but the activation probably of a different seismic source. Okay, now our conclusion so far is that the 30 October 2020 earthquake was the strongest in Samos, at least in the instrumental period. In 1904, 3 strong earthquakes occurred in Samos area. Inconsistent magnitudes and epicenters have been determined in previous catalogs. The main shock caused damage mainly in the southern part of Samos Island. Damage also reported in the west of Turkey too. The Agamemnon magnitude correlates well enough with magnitude MS of AUTH catalog, University of Thessaloniki catalog, for the period 1900-1910. Using main shock epicenters from previous catalogs, we found magnitude equals 6.4. A new epicenter offshore southeast of Samos was adopted and found magnitude equal 6.3. Following a similar procedure, the magnitudes of aftershocks A1 and A2 were calculated and found 6.2 and 5.9 respectively. This solution corresponds to epicenter offshore northwest of Samos, and this may imply the activation of a new seismic source. So, regarding our research for the Samos 2020 earthquake and tsunami can be found in the following papers, and I would like to thank you for your attention.
Thank you very much, Ioana, and also thank you for saving us some time. I see no written question in the Q&A icon. So as we do have some time left, is there anybody who wishes to express a question orally?
Yes, I think we have a raised hand, as I can see.
I saw that. Christos Papaioannou, is that correct?
Yes, I think Christos has raised hand.
Christos, can you hear us? No response.
He's not able to speak with the microphone. He should write in the chat, please.
So Christos, if you hear us, you can type the question in the chat or in the QA. Is anybody else who would like to pose a question?
Dimitris, if you like, we can maybe have a short break just to start on time the next talk.
Yeah, because we are almost 10 minutes,
yeah,
before the timetable.
That's right. So we can maybe short break if you wish.
Yeah, fine. So we can reconvene at 16:45. So
Or just 1 or 2 minutes before, yeah?
Yeah, okay.
Okay.
So 16:42, please be back. Have a short coffee and be back again. Thank you. So Joanna, you can stop sharing your screen. Thank you. So I guess we can continue after this short break. And we move on to the third presentation of this session. It will be delivered by Ileana Karkani, and it's again on the Samos earthquake of October 30th. So Ileana, please, you can share your screen and the microphone is yours.
Thank you. Okay, I will share my screen now. Okay, I hope that everyone can see.
Excellent.
Okay, perfect. So good afternoon, everyone. My name is Ileana Karkani. I will be doing the presentation on behalf of our team. First of all, I would like also to thank the organizing committee for the invitation to present our work and congratulate you for this very interesting workshop. So our research is focused on the relative sea level changes and the impacts of the coastal zone caused by the recent earthquake of October in 2020. Our research aims to re-examine the various sea level indicators that we find in Samos Island by comparing past with new measurements in order to understand and quantify the co-seismic movements caused by the recent earthquake and try to shed some light to the tectonic regime of the island. Now, since many speakers previously have discussed about the Samos earthquake, I can just skip the details. So just an overview of the main tectonic structures that we find on Samos Island, on and around the island of Samos, which influence the geomorphological characteristics of the island, both on the coastal zone as well as inland. So the carbonate rocks around the coasts of Samos favor the development and preservation of tidal notches. Tidal notches are undercuttings that are a few centimeters to several meters deep, and they are commonly cut in steep calcareous cliffs near the sea level. The profile of a tidal notch is an excellent sea level indicator because it provides information on the duration that the mean sea level remained at the level of the notch vertex, which you can see here in the slide. And it also provides information on the speed of its emergence or submergence, depending on if we find the notch immersed or submerged. So if we have a look at the history of relative sea level changes in Samos, it is characterized by a complex history. There are evidence of Holocene uplift as the result of past earthquakes, noted by previous researchers, such as Professor Spiros noted also before, mainly in the form of tidal notches, benches, or even biological indicators. These evidence are mainly found on the northwestern coast of the island. Conversely, if we look at the south and the southeastern coasts, subsidence has been noted based on the presence of submerged geological, geomorphological, and archaeological indicators. And in 2015, our team had mapped submerged tidal notches on the southeastern part of the island, which had remained unpublished until today. So during our research, we performed extensive fieldwork in April of 2015 and in November of 2020 along the coastal zone of Samos, both on the coast and underwater. The underwater survey in both years was accomplished by snorkeling, but also by freediving equipment. And we also used the boat in order to facilitate our access at all sites and establish their continuity. The sites we examined in 2015, we revisited and remapped in November of 2020, along with some additional sites around the island, in order to try to document the possible vertical changes caused by the recent earthquake. We also performed some measurements on sites with evidence of former uplift reported by Spiros and his colleagues in 2000, in order to try to better quantify the new vertical displacements. We deduced the former sea level positions mainly from tidal notches, benches, and biological indicators. And taking into consideration all the different tools that we use, we consider an error range of approximately 5 centimeters. So this slide summarizes our field measurements with the site locations, the sea level indicator type used, the main characteristics for each indicator, and the primary source of the evidence. And in the following slides, I will show you just an overview of the different sites that we have mapped. So we start from the south part of Samos, as we can also see on the map, and we will move counterclockwise to the east, to the north, and then the northwest. So in the south part at this site, SA1, in 2015, we identified 3 submerged tidal notches. Only the 2 are visible in the photograph, and a slightly submerged notch at -5 centimeters. In 2020, the latter, the slightly submerged notch, was found raised at 18 centimeters, suggesting an uplift of 23 centimeters. Moving on to a little bit farther to the east, at Pythagorean town, at the contemporary breakwater, we found evidence of the recent uplift as a result of the 2020 earthquake. Measurements that we performed on the former mid-littoral zone, as you can see in the photograph, that is now exposed above the mean sea level, suggests 15 centimeters of uplift. A little further to the east at Samos, site 28. At this site, we found marks of an uplifted shoreline at 10 centimeters at the eastern part of Samos beach, which did not exist in 2015. We found exposed limpets, vermatids, and dead algae, which are indicative of the mid-littoral zone, and which are today, they are found above the mean sea level. If we look at the other side of the beach, a little bit to the west, we also found marks of an uplifted shoreline at 13 centimeters. Going to the next site, near Klima village, site SA9, you can see its location on the map on the top right. In this site, on a carbonate headland, we had identified 2 submerged notches in 2015. An upper one was located at -20 centimeters and a lower one at 115 centimeters. During the 2020 fieldwork, we found the upper notch at -21 and the lower one at about 120, suggesting that no vertical displacement has taken place in this site since 2015. You can see the location of the upper notch indicated by the arrow, and the lower notch is indicated by the diver. At this site, SA10 in east-southeast Samos, we measured in 2015 a submerged notch at -30 centimeters. The same notch was recorded at -17. You can also see a representative sketch of the 2 measurements. And in 2020, the same notch was found at -17 centimeters, suggesting an uplift of about 13 centimeters. Moving on to the northeast part of Samos, at Murtia site, on the carbonate cliffs at this site, in 2015, we identified a submerged fossil shoreline through a tidal notch at -40 centimeters. We revisited the same site in 2020, and we measured the notch depth at -32 centimeters, indicating a slight emergence of about 8 centimeters. This notch is visible continuously for more than 1 kilometer along the coast. At the next site, at Kokari, you can see also its location on the map. At the port of the town, an uplift of 22 centimeters was measured based on the exposed mid-littoral zone, as you can also see in this photograph. This was found on a small outcrop of marbles. The next site is located also at the northwestern coast of Samos. It is Potami Beach. At the eastern part of this beach, there is evidence of 3 raised notches, which are indicated by the 3 arrows in this photograph here. However, their profiles are not very well developed. We deduced an uplift of about 20 centimeters based on the position of the lower notch and the exposed mid-littoral zone. On the western part of the same site, as we can see on the right photograph, measurements of the exposed mid-littoral zone support an uplift of about 80 centimeters. We can see the former mid-littoral zone with the characteristic vegetation consisting of limpets and brown algae, which is now found above the present sea level. Another interesting site is Punda, just to the west of the previous site. You can see in the photograph that it hosts 3 raised fossil shorelines indicated by the 3 arrows corresponding to 2 benches and 1 tidal notch on the top of the photograph. Our measurements in November of 2020 showed a clear uplift of the area after the recent earthquake. The lower and the upper bench were measured at 82 and 132 centimeters above the present sea level, respectively, supporting an uplift of 22 centimeters in comparison with the values provided by Styros and his colleagues in 2000. You can see a representation in the sketch in the bottom corner of the slide. Going to the northwestern part of the island at the Megalo Seitani site, we also found signs of an uplift of about 22 centimeters, where also the former mid-littoral zone is left exposed above the present sea level. Last but not least, the last site is at Agios Isidoros, at the northwestern tip of the island. This site hosts evidence of former uplift in the form of a bench and a tidal notch, reported also by previous researchers. At the center of Agios Isidoros Bay, a colony of Cirripedia was found freshly exposed and was measured at 35 centimeters above the sea level. It was on the edge of a tidal notch base, suggesting an uplift of approximately 35 centimeters. So in order to summarize all the previous sites, on this map we present the main results of our findings. The red numbers correspond to the quantification of uplift in centimeters. And we mainly focus on the best evidence, which mainly come from the revisited sites and the comparative measurements. So if we have a look at the map, on the north part, we mainly discuss 7 sites based on our findings. The northwest part of Samos, so this part, from Vathi, which is the site here, to Agios Isidoros, which is the site here, has been seismically uplifted by 20 to 35 centimeters. This part of Samos has been uplifted at least 3 times in the late Holocene. In particular, Styros and his colleagues have identified 3 raised paleoshorelines corresponding to 3 earthquakes that have taken place during roughly the last 3,000 years, as already discussed by Professor Styros before. If we have a look now at in the south and the southeastern part of Samos, we discuss mainly 6 sites. The examination of the same submerged tidal notches in November of 2020 in comparison to 2015 revealed that they have been uplifted, but they remain drowned. And based on the comparison of their depth values between the 2 years, it is clear that the uplift is higher in the southern part and progressively lowers towards the east. This is also evident if we have a look at the map and the corresponding uplift numbers. To sum up, we can conclude that the island has been seismically uplifted, but with different magnitude. The largest uplift was found on the northern part of the coast, with the highest value at the northwestern tip of the island, a value of 35 centimeters. And we can also note that although the southern part of Samos has experienced many submergence events in the past. During the earthquake of October of 2020, it has been uplifted by up to 23 centimeters, while it is evident that this uplift fades out towards the northeast. And before I close the presentation, I would like to share with you just a very small video on a story map that was developed by our team for the recent Samos earthquake. The story map basically focuses on the main findings of our research. So if you're interested, I can provide the link in the chat. The story map, you may find interactive maps with details on the sites we have studied, details on our measurements, as well as photographs from each of the sites. So thank you very much for your attention.
Thank you very much, Ileana. It was really very nice.
Thank you.
I see no question. Also in the chat room, there is no question. If anybody wants to ask orally a question, well, probably not, but I would like to ask a question or probably make a statement. From your data, actually, it seems that the entire island has been uplifted. More in the western part, less in the eastern part. If I'm correct, I remember from the interferometry that it has observed a kind of subsidence somewhere in the northern middle part of the island. Is that correct? And this has not been confirmed by your data.
Not by, okay, the main issue is that because of the type of research that we did, we mainly focus on the carbonate coasts. So the subsidence was not noted on a part of the island that we could do, that we could find tidal notches or benches or something similar. So it's not a question of, we cannot say that the subsidence has not happened, but that we don't find the type of sea level indicators that we would expect to measure in order to document it from the geomorphological point of view.
I see.
Yeah, but it's not something that we cannot reject, because we do not have the type of geomorphology and geology in order to be able to find the according sea level indicators, I would say. So this is why you can also see that there are some parts of the map that are not, we don't have measurements, because we have different types of rocks, so we don't have tidal notches. So we skip this area. There is no evidence to find for this sort of research.
Great, good. So this also raises the issue of comparing different methodologies and the results that we obtain from them, and it would be really great to make this comparison. Thank you very much, Ileana.
Thank you.
I think, yes, please.
Just a question. Did you try to make a model of the causative fault of that uplift?
I'm sorry, I didn't hear very, can you repeat?
Yeah. Did you try to generate a model of the causative fault?
No, because, well, this was the first part of our research, which is only based on the geomorphological observations. So we haven't input any other type of data or models. This is the next, we hope that this is the next step in order to better combine the field data with the modeling part. And I think it will be very interesting to see what type of results we can find.
Okay, thank you.
Thank you.
Any other question from anybody? So, you know, we have this nice problem that all speakers keep their time, or even they are faster than the time they have. So we are ahead of the schedule. Anyway, I think we can move on to the next speaker, to the next presentation that will be delivered by Dimitris Galanakis. Yeah, Dimitris is connected.
Yes. Yes,
welcome, welcome, Dimitris. You can share your screen, and the microphone is yours.
Okay. It's okay?
Great. Good.
Okay. Thank you. And I'll present the work from Hellenic Survey of Geology and Mineral Exploration to support the Civil Protection Authority. So we have some microseismic and geotechnical observation after the seismic sequence of 30 October 2020, a 6.7 magnitude in Samos earthquake. With colleague Sotiris Boras and Kondodimos Konstantinos. Okay. The destructive 6.7 earthquake with epicenter offshore, a few kilometers north of Samos Island, caused several secondary ground deformation, such as phenomena rock falls, landslide, ground ruptures, and increasing the impact of the and the hazard of the sediment of the settlements and the infrastructures, and tsunami involved in the northern shores of several meters. At land sites at Samos Island, in sites Avlakia, Stavrinidis, Pythagorio, and Kodakeica village, the local road network was cut off, and extended damages occurred on old buildings and Thames buildings on loose geological formation and alluvial deposits. Co-seismic phenomena were also observed on Ikaria Island, as well as several 10 of kilometers west-southwest of epicenter, along an onshore east-northeast, west-southwest striking active fault, where a significant geothermal field is developed, and the outflow of the geothermal fluids was immediately increased after the main shock. Scattered rock falls and the landslide occur along the island and the sea, and in the harbor of Agios Kyrikos showed a circular turbiditic flow. Have a look in a maps in Aegean Sea and the epicenters and the tectonic map. A recent issue of tectonic map by Boras et al. Show the regime, the geodynamic regime in the area of Aegean Sea. The affected area is located in the eastern part of Greece, and where affected is near the coast of Turkey, and show this affected area in geotectonic map of Greece. The neotectonic map of Samos, which consists of Paleozoic schist, gneissic schist, and dolomite, and Neogene lacustrine deposit and quaternary deposits. We have the red line is the active fault. The green line is the potential active fault, and the orange is the inactive fault, which affected the landslide Avlakia, where we'll see next. And in the Ikaria island, which consists from gneiss and granite and Miocene granite and dolomite, Triassic dolomite. At some places with small places with a Neogene quaternary deposit with affect by the Agios Kyrikos fault with northeast direction. Here the maps show the historical events by Papazachos, and by Kiradzi the fault place solution of several seismic events, and the co-seismic existence of strike slip and normal deep slip kinematic supports the dynamic seismotectonic complexity of the region. The seismic sequence in 30th of October 2020, the fault-lay Planus solutions we have it in this map and relocated in the small map, and we see some facts in direction to the Ikaria Island. So, microseismic observation in Samos Island. They have co-seismic ground deformation phenomena, ground ruptures in Agios Nikolaos area. Is the northern part or central north part of Samos. It is there are in the boundary of the Neogene basin, and landslide phenomena in Avlakia in the central part of island, and the ground rupture. This is the tectonic map with the fault active fault eastward direction, and the fault of Avlakia fault where we have the landslide. In Agios Nikolaos area and the northern and central part of Samos Island, is a series of ground ruptures were observed striking from north 40 to north 70, demonstrating of a throw of 5 to 8 centimeters. They also transect the main road that connect Vathi to Karlovasi. These ruptures are related to the western tip of the seismic fault as a superficial expose of many of co-seismic surface ruptures were observed in the Agios Nikolaos area. Is at a distance about 5 kilometers from Karlovasi port. These ruptures connected the direction of Karlovasi fault. Also, co-seismic surface ruptures were observed not only in the field and roads, but also is slopes as a result clear offsets of several centimeters, both of horizontal and vertical movement. Co-seismic surface ruptures are offsets in olives fields and located south of Agios Nikolaos. In Stavrinidis village, in the broader area, there are rock faults and landslide phenomena in this area, and local road network was cut off. Slope failure in the Avlakia area is strongly affected by northwest southeast strike normal faults based on the tectonic map of Samos Island. And this normal fault, the red arrows, they have been considered as inactive. To resolve the problem with the landslide in this area, we suggest a concrete barrier and made a great barrier with a large concrete block, and along the base of the affected slope, in order to protect the road from the further slope failure and surface deformation during the aftershock sequence. They help block the rocks and debris from reaching the road. The unstable landslide material is now accumulated behind the barrier. Ground deformation is Kondakeika village. Is located south, it's between Karlovasi and Agios Nikolaos area, and suffered damage to its buildings. The village is located in an area with existing ground stability problems. Is an old landslide, a big great landslide. Rafts were being avoided by the quake. The observed damage include not only non-structural damage comprising extensive cracking of wells, but also heavy structural damage in their columns. In Pythagorio village in the southeast part of Samos area, characterized by favorable conditions for the generation of slope movements, including mainly rock falls. This certifiability of this is also certified by previous generation of such phenomena, resulting in the damage of vehicles. So, seismic phenomena were also observed on Ikaria Island, several 10 kilometers from west-southwest of the epicenter. This is the map of morphology map in Ikaria Islands, and so an asymmetric ridge formation implies differential slip rates on two boundary faults. The southern fault is the fault of Agios Kyrikos fault with geothermal activity. Along this fault, we observe effect on Neogene deposit and quaternary deposit with clear fault plane and slickest lines, two generation. After the main shock, we have along the Agios Nikitas, along the Agios Kyrikos fault, we observe that the geothermal water uplifted in all basements of the buildings along the coastal zone up to 25 to 30 centimeters, and this phenomena. It was for 2 months. Which also created the rock falls and landslides occur along the island of Ikaria Island, and the sea in the harbor of Agios Kyrikos show the circular turbiditic flows. Conclusion. Surface deformation has been detected mainly in the northwestern and southeastern part of Samos, and cause damage on settlements and infrastructure in loose geological formation and alluvial deposits. Old landslides reactivated in Avlakia, Stavrinidis, and Kodakeka area. Rockfalls observed along the slope of the road leading to Vathi, located in the northern part of Samos, to Karlovasi, in the northwestern part. Seismic phenomena rupture has been also observed in the northwestern part of Samos Island, and more specifically in the Agios Nikolaos, Agios Ilias, and Brodet area. They are almost continuous with total length up to 1 kilometer. In Ikaria Island, the outflow of the thermal fluids has immediately increased after the main shock. Scattering rock falls, landslide occur along the island, and the sea and the harbor areas Nikita show the circular turbiditic flow. Question. Is the 30th of October 2020 seismic fault connected with the active tectonic structure of Eastern Ikaria Island? If yes, how? And possible answer. The 2020 aftershock distribution at the ground rupture in Samos Island indicate western extension of a roughly north to northwest dipping fault. Thus, what the role of the Agios Kyrikos south dipping fault? Thank you for your attention.
Thank you very much, Dimitris. That was really nice, and I think that the way that you finished also opens the floor for discussion and questions. Since I see no question in the question and answer window, I invite whoever wants to pose a question to do it now orally. Is there any question? Well, if not, and is there any question? So if I would like to ask a question to Dimitris. Actually, it's not only to Dimitris, but also probably to seismologists who attend this workshop. Dimitris, you saw the very nice map with the focal mechanisms of the aftershocks, and in the western cluster of the aftershocks, we also see focal mechanisms which indicate strike slip motion. And you also saw very nice pictures from the northwestern part of the island, if I'm correct, which also show fractures with lateral movement. Is there any way to explain these strike slip focal mechanisms and the fractures with lateral dislocation with the main focal mechanism of the main fault, the main shock, which was normal fault?
We connect these fractures, ground fractures, with the Karlovasi fault. But after the study of Ikaria fault is a oblique slip fault with left lateral movement. Maybe we connect with either direction of an oblique slip or strike slip structure.
Yeah, this is what I think as well.
It's we needed to start to study this area, not only the geological data, but the seismological data to connect these observations.
Yeah, I mean, I wonder whether the main shock, the normal focal mechanism, has reactivated the northeast striking faults, like the ones of Agios Kyrikos or Karlova Sea, or even some offshore faults which run in this direction. That will be something for future work.
Yes, exactly.
So thank you very much. If there is no other question or comment.
Dimitris,
yes.
Christos raised hand among the attendees, you see. Christos Papayonou, I know.
Yes.
The first one from the attendees.
Yes.
So we can allow him to talk.
Absolutely. Christos, please.
I have a question. First of all, Dimitris, a very nice presentation, excellent material, but very few comments. First of all, 6 months after the earthquake, we know, everybody knows that the moment magnitude of the earthquake was 7, not 6.7 as the preliminary one. This may influence some correlation of field data with the moment magnitude. Especially for your presentation, it would be very useful, extremely useful, because they are very useful also, if you could annotate the north direction. So we, the people who were not there, we may have an idea which is the strike of the ruptures you saw. And last question is the ruptures at Stavrianidis area primary or secondary? Thank you.
Not is not Stavrianides. Is Kodakeka.
Maybe I.
And Agios Nikolaos, Kodakeka area is this area. And this is at the same time. Stavrinidis. In Stavrinidis area, we have landslides.
Landslides.
And, yes. But in Kodakeka and Agios Nikolaos area, we had ground ruptures.
Which are not primary, of course, as do not coincide with the strike of the fall.
Because it's a primary.
Primary?
Yes.
But it's completely different strike than the fall.
Yes. I suppose that is at the end of the seismic fault, so change direction parallel to the Karlova Sea fault, and maybe continuously to the Ikaria Agios Kyrikos fault.
Okay, may I have? Can I make a comment?
More data about this.
May I ask something?
Results and macroseismic observation. We need some instrument support.
Yes, Christos, you can ask.
What I can see right now is in the right picture with a large part of the island, at Agios Nikolaos, the coastline is, I could say, parallel to the fall direction. But in the area of Karlova Sea, we have a change in the strike of the coastline, quite similar to the red lines of the co-seismic, as you say, surface rupture. My comment is the following. If you see the aftershock distribution of the Lesvos 2017 and Kos-Bodrum earthquake aftershock sequence and the Samos aftershock sequence, there is a change in the distribution of the aftershock zone from an east-west, which is the primary direction of the active fault, to a direction south west, which is similar to the striking directions of the ruptures, and with the striking direction of the Caria fault. It's just a comment I would like to make. It's up to you, the geologist, to examine what it happens. Thank you.
Well, on behalf of the geologists, we thank you for this challenge, Christos.
I am also a geologist, don't forget it.
Thank you very much.
Thank you.
Okay, is there any other question or comment? We still have some time. Okay, if not, then I think we can move to the last presentation of this session. Dimitris, you can stop sharing your screen. Thank you very much. And we move on to Osgur Ocelik. Well, I hope I pronounced correctly your name.
That's okay. It's a very good try.
Thank you very much. The microphone is yours.
Yes, thank you very much, Dimitris. Before starting, for those who are Italian among us, I want to say something in Italian just to, show my very poor Italian skills. Voglio dire qualcosa in italiano per I nostri amici italiani. Buongiorno a tutti, speriamo di vederti qui di persona. Because I see that they're a little bit silent, maybe this will cheer them up. So, urgency of building inventory studies for seismic risk prioritization towards hazard resilient Izmir is the title of my presentation. The outline is as follows. I'm going to take a look at a general look at what is disaster, what is risk. I'm going to look at world and Turkey and Izmir in particular. Then concepts of resistance versus resilience. Then what is an earthquake loss model and why do we need them? I will try to answer that question. Then a particular study I'm going to talk about, which is something that we have done back in 2012, which is the building inventory work and risk assessment for Balçova and Seferihisar districts. And I will present some results and what needs to be done towards more resilient Izmir. As we all know, there are different types of hazards, right? There are natural hazards, geological, hydrometeorological, anthropic hazards like chemical, technological, or socio-organizational, and there are astronomical hazards. If we take a look at them very quickly, some of those are earthquakes on the geological side, landslides and falls. On the hydrometeorological side, we have hailstorms, tropical cyclones, we have fires, we have ecological side, we have water pollution, and socio-organizational side, we have mass movements, terrorism, vandalism, and so on and so forth. So let's look at what is risk, okay? Risk has some elements. First, you need to identify a hazard, and that hazard can be natural or anthropic hazard. Then, what is at risk due to that hazard? And it can be people, it can be, property, including buildings, critical infrastructure, or reputation, right? Reputation of, or confidence in an entity. That is the vulnerability assessment part. And there is the impact, the casualties, impact on the people, the business interruption, or environmental contamination. So what has been done in the world? Some of those were kind of, you can trace back to Hyogo framework, which was a conference and World Conference on Disaster Reduction. And there, a framework was set in motion. And Turkey was one of the signatories of the Hyogo framework. In the Hyogo framework, the reason I'm mentioning this is because a paradigm shift happened. And the paradigm shift was from resistance to resilience. And why resilience is important, I will try to summarize that. More than half of the world population live with different types of hazards. Therefore, we should do more than providing just resistance. The concept of urban resilience means bouncing back rapidly from the losses inflicted due to disasters by developing skills and planning so that cities are back to being livable again in a short period of time. So resilience is a more complete framework. It doesn't just provide resistance, but it also provides kind of adaptive learning from that resistance so that you can build better. So there are 4 elements of resilience, of a resilience framework. First is context, which is resilience of what? A system or a process or a building or a, a system of buildings. Then you ask the question, resilience to what? In terms of built environment, resistance to earthquakes or resistance to tsunamis or combination of these hazards, yeah, multi-hazard perspective. Then capacity to deal with disturbance, and that has certain elements, exposure, sensitivity, and adaptive capacity. And the 4th element is the reaction to disturbance. How do you react to that disturbance? And you can do it. You do this in several ways. You can collapse, you can recover, but worse than before. You can bounce back to the same level, or you can do better than that, bounce back better. So after the Hyogo conference in 2009, AFAD was established. AFAD is the Disaster and Emergency Management Department of Turkey. This was an important step for us, for Turkey, because AFAD has moved the lever from crisis management to risk management. With that, it promotes the model called Integrated Disaster Management Model. And with this model, the department aims in hazards and risk to be studied and understood in advance, providing effective intervention and coordination, and performing concerted post-disaster rehabilitation and improvement of efforts. So it is not just crisis management, but it's a risk management, and it's an integrated model. AFAD for earthquake, it published a very important, a visionary document called National Earthquake Strategies and Action Plans. And it covers the period between 2012 and 2013. It was a very visionary document. And one of the efforts within this document was building inventory works for cities to be finalized by 2017, in which the responsible entities are designated as city municipalities, and AFAD being acting as the observing and controlling entity. So building inventory work for major cities in Turkey, it was, obligatory to finish by 2017. After Hyogo, Sendai framework has been set, and the subtitle was Disaster Resilient Cities. And there were certain priorities put forward. The first one was understanding disaster risk, which was disaster risk management needs to be based on an understanding of disaster risk in all its dimensions of vulnerability, capacity, exposure of persons and assets, and hazard characterization. The second priority was strengthening the disaster risk governance, which is like what is AFAD. AFAD is within this priority. Investing in disaster risk reduction and enhancing disaster preparedness for effective response and building back better. And the final work that I followed, at least, was a conference held in 2017, Global Platform for Disaster Risk Reduction, which was held in Cancun, Mexico. And the subtitle was Commitment to Action. And here, other aspects of disaster management was stressed. And what was important in this conference was it stressed the inequality aspect for inhabitants of cities exposed to disasters, such as economic inequality, gender inequality. And there are some non-governmental initiatives for resiliency work, for resilient cities. One of them is shown here, which is 100 resilient cities. If you look at Turkey, this work was done by the United Nations Office of Disaster Risk Reduction. And this was a country report. If you look at Turkey, you know, the flood and earthquake are the two major hazards. And Izmir, which is here as shown here, if you look at the ordering of the cities, Izmir has the highest risk in terms of annual average of affected GDP. If you look at other cities in Izmir in terms of earthquake risk, Istanbul leads, of course, and the second comes Izmir. So, how do you do the risk assessment of building type structures? In order to assess earthquake performance of existing buildings, the following steps are taken. The first, soil and material characterization, also hazard characterization maybe should be done before. The second, developing a realistic nonlinear numerical model of the building and perform either static pushover analysis or nonlinear time history analysis. Then either retrofit or rebuild the ones which are unsafe. This roadmap is very cumbersome, time-consuming, and requires high level of expertise. So if you were to do such a thing for all the buildings in Izmir, then the question arises, how many buildings there are in Izmir? Based on a recent survey in 9 districts, there are approximately 1 million buildings in Izmir. So we can say that to do such an assessment work, this requires a lot of time and a large budget to perform a detailed analysis as described above. Just to give you an example, just for Istanbul, this kind of analysis requires 25 years and $25 billion to be specific. This work was done by Spence in 2017. So the question is, so this takes a lot of time, right? Which building group to start from? Because some of those buildings that you see on this picture are riskier than the others, right? So if I show you a picture like that and ask you which ones to start from, well, that's a hard question to understand. So the problem we are facing is as follows. The existing building stock is too large. Time required for data collection and assessment is too long, and the necessary budget to perform these tasks is very large. It's too hard to find the necessary budgetary sources and time. Then what to do? Well, staged or progressive assessment. These methods can be used as an alternative. This is a more sustainable and a manageable approach. So what is staged assessment? First level assessment. An expert collects data by visual screening of buildings. The data collected will allow to perform a preliminary risk assessment and provides a rudimentary prioritization. Then, once you have this rudimentary prioritization, you can apply second level assessment to those which are riskier, which are found labeled riskier within the first level assessment. So second level assessment, based on the results of the first level assessment, more in-depth data is collected from the prioritized buildings by entering into the buildings and surveying them from inside. And actually, project data is used to augment the data collected at this stage. And the third level assessment, based on the results of the second level assessment, static pushover or nonlinear time history analysis are performed on the selected buildings. What do you do with the important buildings? Well, for the important buildings, such as schools, public buildings, hospitals, which are buildings necessary right after a disaster, are directly subjected to the third level assessment. So what is an earthquake loss model? Earthquake loss model, risk model is used to estimate losses after a damaging earthquake, to plan the work required before and after an earthquake, to prioritize buildings in terms of their earthquake risk in order to prevent loss of lives. So the main objective of an earthquake loss model is to combine regions earthquake hazard with regions building stock vulnerability, so that damage distribution in regional scale can be estimated. So just to summarize it, you combine or you convolve seismic hazard with the vulnerability of that specific building stock to estimate damage. What is the outcome of such a work? Well, the outcome is earthquake risk maps. The region, so you can have several things for these earthquake risk maps. The first one is the region can be divided into grids with certain size, let's say 2 kilometer by 2 kilometer. Then a single risk level is assigned to all the buildings within that cell. This approach has coarse, very rough resolution. This was done in Istanbul and also in also in Izmir back in 1999. The second approach would be individual buildings are assigned a risk level based on their address, which is called address-based approach. This approach has higher resolution, right? Which is the method chosen for Izmir, Balçova, and Seferihisar pilot project, which I will be presenting now. This was the coarse resolution map, the risk map. As you can see here, you see only one risk level assigned to a certain cell. So what did we do? The name of the project was Development of Building Stock Inventory and Earthquake Risk Assessment of Buildings, which was a pilot project which we performed for Balçova and Seferihisar districts. This was done by the Izmir municipality, by 9 Eylül University, and Chamber of Civil Engineers of Izmir branch. So what methods are used? For the first level methods, we used a rapid visual screening method. This was developed specifically for buildings in Turkey because every city or every country has a certain construction practice, okay? So vulnerabilities of that country, the building stock of that country is different than another country. So you have to develop specific methods for a specific country. So second level methods, we used 3 methods, Hasan and Sözen methods, improved discriminant analysis methods, and the third one was P25 methods. And these methods were also specialized for Turkish building stock. So what is the difference between first level and second level methods? First level methods, they are also called visual screening methods. These methods do not need project data. Many buildings are assessed in a very short time, okay? But the results are relatively less reliable. Second level methods, they require project data and or material data. They require more time and resources, but the results are more reliable. So this is the classic decision schematic. So you have many buildings at this stage. You perform first level methods. First level methods divide the building group into low priority buildings and high priority buildings. So this is high priority buildings are fraction of the total building stock. then you apply second level methods, and usually second level methods, they classify the buildings into 3 groups: low priority, medium priority, or high priority. Then for the high priority buildings, which are fee buildings, then you apply third level methods, and then you label them safe or risky. For the project that I'm presenting for Balchova and Seferihisar pilot project, we did a little bit different than the classic schematic. So we only consider reinforced concrete buildings. There were buildings which are out of scope, so we put those aside. There were buildings without projects. So without projects, you can only apply first level methods. And the first level methods, they classify low priority and high priority. And for the high priority methods, you can, either you can apply second level method if you have time and budget. For buildings with projects, you can directly apply second level method, and those classify the buildings into low priority, medium priority, and high priority. So what the difference was, without applying first level methods to the buildings with projects, we directly apply the second level methods because they are more reliable. Here, the medium priority group are very uncertain. So here are the results. Visual screening for Balchova district, by visual screening, which is a first level method, we found that 34% of those buildings are high priority and 66% low priority. For second level methods, improved discriminant analysis, you have 18% more high risk or more priority or high priority, let's say, 57% medium priority and 25% low priority. Another second level method, which was P25, you see that you get different ratios, different numbers. For Seferihisar, which is we get 17%, which by visual screening, we got 17% high priority, 83% low priority. By using improved discriminant analysis, we got 11% high priority. By using P25 method, we got 7% high priority. So the first problem is this: different methods give different results for the same building group. And among methods, different levels of matching is observed. What I mean by that is, for a particular building, improved discriminant analysis may say this is medium level priority building, but P25 methods may say, oh, this is a high priority building. So let's look at the result of second level methods for buildings in Balchova. And you see the y-axis is the percentage of building, and the colors are: the red is high priority, yellow is medium priority, and green is low priority. And the x-axis are the second level methods. So we use 3 different second level methods. As you can see, in all of these results, there is a fat medium region, which is a very uncertain region, because we cannot say to those buildings within the middle region whether they are safe or not. So a large fat medium priority region. So this is another result which is kind of interesting. This is for Balchova buildings. We applied first level method to all of those Balchova buildings, and those which are labeled low priority, to those buildings we applied the second level method. And as you can see, the first level methods, they miss some of the high priority buildings labeled by the second level methods. Okay, so buildings are missed by the first level methods. So the third problem is there are buildings classified as high priority by the second level methods among the buildings in which the first level methods classify them as low priority. So how to solve these three problems? We came up with a decision matrix, okay? So what the idea was, this idea behind the decision matrix was as follows. More reliable aspects of different methods are considered given the data in hand, and 3-level priority ranking is increased to 5-level ranking. Therefore, priority classes are refined and be made more manageable. So basically we used strong sides, different strong sides of each method to come up with a more reliable estimate. And once we've done that, for Balchova, we have 5 priority levels. And for Balchova buildings, reinforced concrete buildings, only 12.6% were within priority level 1. And the second level was 11.5. And as you can see, the fat medium level buildings were kind of were made leaner, right? For Seferihisar, only 5% of those buildings were within the priority level 1. And the second level was 7.2%. Another result was here shown for Balchova and Seferihisar. The x-axis is the story number, okay, and the y-axis is the building percentage. And as you can see here, as earthquake risk increases with increasing story number, right? A second result was here x-axis is the year in which that building is built, and the y-axis is the building percentage. And as you can see, older buildings have higher priority. So a potential synthesis from this work was older buildings with stories 6+ and higher, 6 and higher are riskier. So if you were to tell me which building group to start from, I would say go to older buildings with stories 6 stories and higher. Okay. And this is the earthquake risk map for Balchova. And as you can see here, individual buildings are assigned a risk level. Okay. So you can see here that building is riskier than the other, and so on and so forth. And this is for Seferihisar, a more refined map. You can do a lot of things with this, with all these results. For example, you can come up with total construction building area. If you look at priority 1 buildings, you have 370,000 meters square construction area. If you include the priority 2 buildings, then you get this much additional construction area. If you add the second priority level buildings, you would get 116% increase, okay? So what should we do for the prioritized buildings? Buildings are classified based on their priority levels. They must be assessed with a third level methods, right? Based on the outcome of the third level assessment, buildings must be either retrofitted or demolished and rebuilt. And we may have to look at, for example, simplified retrofitting methods. They may be considered for low-rise, high-priority buildings. Is it only a priority map, what we did? No. We established a digital archive with projects, title deeds, licenses. Individual building specific data used to assign risk levels. Cost estimation can be done for high priority buildings. An estimation has been done to assess the size of post-disaster work. What to do next? The work must be extended to other districts of Izmir. Methods to be developed for economical retrofitting of existing buildings, city planning aspect, legal aspects, financial aspects, social risk, and disaster management aspects must be studied. Thank you for listening. I think I extended my time a little bit. Yeah, thank you for listening. If you have any question, I would be more than happy to answer.
Thank you very much, Özgür. I think we are still on time, according to the schedule. So if anybody wants to ask a question, I see no written question, so we have a couple of minutes for any question now orally. I don't see anybody interested in posing a question. So thank you very much. I would like to thank all of the attendees for attending this very interesting session. I hope you enjoyed it. I think we learned something more than what we knew so far. Orhan,
okay, thanks very much, Dimitris. Thank you, Özgür, for your nice talk. So we had a very intense and useful sessions today. We will start with the tsunami session tomorrow at 9:30, which is an interesting session of the workshop. So thanks for joining us today, and stay safe and healthy, and have a good night, have a good evening, and see you tomorrow morning.
Ricardo, you have anything to say?
No, to stress what you say, stay healthy.
Okay,
COVID-free.
Spiros, and open your microphone, please. Microphone.
Orhan, tomorrow we will summarize all the workshop because there are very interesting new directions and a lot of information about the active tectonics and especially the Samos earthquake. So tomorrow, I think we'll spend half an hour at least to discuss and to summarize all the presentations.
That will be very nice.
Yeah, so we should do that tomorrow after the final session of the workshop. Yes, we can do it maybe in 15 minutes or half an hour.
Yes,
we will do that. Okay, thank you.
See you tomorrow.
Okay, so
bye.
Thanks for joining us.
Italians, it's 8:30, I remind.
Okay, so we have some time to enjoy.
Early start in Italy.
Okay.
So see you tomorrow morning. Bye-bye.
Bye-bye.